இந்த பேப்பரை கொஞ்சம் தூரம் எடுத்து பேப்பர் டிஸ்பிளே
I now request Dr. T. Mayalagan, convener, IWESTE 2021, to deliver the welcome address.
Good morning and a very warm welcome to all the speakers and participants. It is indeed a great pleasure and honor for me to invite for the opening of the international workshop on energy storage technologies for e-mobility, that is IWEST 2021. On behalf of SRM Institute of Science and Technology, on behalf of Department of Chemistry, and behalf of my own, I wholeheartedly welcome all the speakers from various countries, eminent professors from various institutions, and my dear participants. The ultimate aim of the workshop is to focus innovative, futuristic views on energy storage technologies. There is no doubt that the energy storage technologies play a critical role in 21st century towards the energy security and inclusive growth of the society. So lithium-ion batteries are not only used in laptops and smartphones, but also used in the high-end vehicles in like Tesla cars and grid storage. So the great quest in the e-mobility market is to develop high energy density electrode materials to reduce the upfront cost, increase the e-vehicles operating range and safety aspects. Before I conclude, I would like to take this opportunity to thank SRM Institute of Science and Technology and then Scheme for Promotion of Academic Research and Collaboration, SPARC, for supporting and making this workshop possible even in the pandemic situation. Let me express my most sense of gratitude to the Scheme for Promotion of Academic and Research Collaboration, SPARC, for the financial support to organize this event. Thank you.
Thank you, sir. It is my pride and pleasure to invite Director Research, Professor K. Ramasamy, to deliver the felicitation address.
Very good morning to everybody. At the outset, on behalf of the SRM University, faculty and student friends, I welcome you all for this international conference organized by Dr. Mayalagan towards the fulfillment of the requirement of the SPARC program funded by the UGC through the Ministry of Education. It is a pleasure to indicate in a changing world, change is very permanent, but the energy regulation is going to be the alternative system. Fortunately, Indians are the one who regulated the system of 7 chakras to preserve the energy and bring the energy to the required level when it is required. Unfortunately, this technique is missing today, but everyone is interested to change themselves to adopt the recent techniques. In 70s, we introduced a course called For Future System of Science and Economy, which is named as a futurology course. In fact, India developed much in the agricultural sector in those periods and in the atomic energy in those periods. After that, we wanted to follow the Western techniques and Western tools. By adapting that one, we have missed what was best available with us. Even today, your yoga is practiced outside the world at a cost, whereas we are not really interested to follow it and regulate our own energy system. Whereas Maharishi has shown by regulating your fingertips with the 3 mudras, you can reduce your respiratory system and regulate your energy. With 70% of energy utilization, you can always achieve what is your requirement and your delivery for any of the knowledge-based system. And this has led to the lifelong longevity of the life to the tune of 120 years. In fact, by practice, Japanese always bow down. By that time, your Uddiyana is always taken inside. By that, their average age is prolonged like anything. Leaving the present system of human regulation of energy, let us think what is the future for the energy system. Having started with the direct fuel, burning of the biomass, then reserved coal, then liquefied coal. Starting from the solid to liquid we went. Again, we are coming back to preserved static batteries or the lithium ion batteries. When we go for the lithium ion batteries, the science is improving a lot for sodium ion linkage. At the same time, we are also linking for the preservation of energy for the mobility. It is already working in laptops and it is also working in your smartphone. But is it possible to use it on a larger scale in the railways, in the automobile sector, or in the transport sector? We are very successful in that one. Our Indian government has invested 1,000 crore for using the hydrogen-based energy or battery-based system. Are we going to utilize this investment in India for Make in India program or to enlarge our futuristic change in scientific caliber? No doubt we are the 3rd largest technical manpower in the world, but our contribution is 46th in terms of innovation and 126th in terms of patent and registration of our new ideas. Is there a possibility to improve? Other than the universities, which one is going to take us to the next level? Please realize this. I request all our young colleagues, you please bestow your kind attention how to take this energy level, because nothing is impossible without sun. Sun's energy is stored as food material through the chlorophyll. And today, the battery is going to be the talk of the town for the next 15 years. By 2030, all vehicles will run only on battery-based system or hydrogen-based fuel. How are you going to store the hydrogen? How are you going to store the energy? I'm sure that international guests with us definitely take you to the near contribution and near success, because nothing is permanent in this world excepting change. We are marching towards the change. Our youngsters with 58 crore population below 25 years of age, they are going to lead the whole world by contribution and equipping themselves. Canada has come forward for the future investment in terms of energy. Their investment, research, focus, futurology is very clear. The roadmap is very clear. Whereas in India also we are developing in such a way so that our contribution will lead to a maximal success throughout the world. We have to go back in certain stages. How Britishers trained us in mathematics and English and used us in 92 countries. I'm sure that technical manpower is provided to America next to China and Japan, Korea, Israel. In all these countries, our postdocs and doctoral students are contributing. Please share your experiences, develop this country, contribute to the development of the rural population. Wish you all good luck. Let us learn from the learned community. Once again, I thank all the participants and the learned colleagues for sharing your rich experiences to help our younger generation. Wish you all good luck. Thank you.
Thank you very much, for your thoughtful address, sir. I call upon Professor Ramasamy Murugan, President, Energy Science Society of India, to introduce our chief guest.
Good morning, good afternoon, good evening. Suppose I have to say very early good morning and very late good evening also to some of the participants. On behalf of Energy Science Society of India, we are glad to welcome you all to Professor Mandiram for these wonderful events. So last year, Energy Science Society of India planned to organize an international conference to felicitate Professor Goodenough at IIT PHU. Fortunately, we couldn't make it because of this pandemic. So last 1 year, we didn't organize any programs. So when Professor Mayalakan introduced this concept, we thought that it's the right time to organize this. Particularly, I'm very much impressed by this Dr. Mayalakan's work. With this short notice, he able to make this event wonderful. I hope everyone will enjoy it and learn from each one. So I congratulate the administration of SRM, Institute of Science and Technology, and Dr. Mayalakan for organizing this. My role here is to introduce Professor Arugam, that's what I mentioned. But I don't think Professor Mandiram need any introduction for the international community, particularly battery people working in this world is concerned. But anyhow, so I'm very glad to, on behalf of PSSA welcome Professor Arugam Mandiram for this inaugural function as well as to deliver a keynote address in this international workshop. Professor Arugam Mandiram is the Director of Texas Materials Institute and Director of Material Science and Engineering Programs. His research is focused on development of affordable, efficient, and durable materials for electrochemical energy conversions and storage, specifically on materials for batteries and fuel cells. His major contribution is the polyanion oxides cathode for batteries, which is one of the 3 families of cathodes used in commercial lithium-ion batteries. They are also pursued as cathode for sodium-ion and multivalent ion batteries. His group is advancing the viability of lithium-sulfur batteries. He is having several international awards and recognitions. As far as me is concerned, the biggest award is his 2019 Chemistry Nobel Prize lecture on behalf of Professor John B. Goodenough. He is a person who is associated with the longest association with Professor Goodenough. I had a very small opportunity, after 3 months or 4 months opportunity to interact with him during my stay in Professor Goodenough lab in 2011. So with small introductions, since already we are late, so I welcome you all for this wonderful event. Thank you very much for.
Thank you very much, sir. It is my honor to welcome our chief guest, Professor Arumugam Mandiram, Director, Texas Materials Institute, University of Texas, Austin, USA, to deliver the inaugural address.
Very good morning. Can you all hear me?
Yes, sir. Good morning.
Good morning. Fellow scientists and engineers, friends, students and researchers. It's a pleasure to be here, and I'm glad conferences like these are happening in India because our future depends very much on energy. Energy is a central societal issue. It impacts our way of life, economy, and public health. So I show here the world energy consumption at the present time. Sorry. Do you see the full screen?
Yes, sir. Yes, sir.
So as you see here, the energy use is skyrocketing. And I also show here the population in 3 countries. China and India have similar populations. US has 0.33 billion, whereas China and India have population close to 1.4 billion. If you look at the energy use, China uses 24%, US uses 17%, and India uses 6%. China and India have similar population, but the energy use is very much different. We use much lower percentage in India compared to China. So supposing if the lifestyle and industrialization in India catches up with China, India will need 4 times more energy than what we use in India now. The same way China catches up with USA, then they will need 3 times more than what they use. Finally, if India catches up with US in terms of industrialization and lifestyle, India will need 12 times more energy than what India uses now. So that tells you the road we are taking as we move forward. So right now the energy use is dominated by fossil fuel. That has 2 problems. First, fossil fuel is limited. It is not infinite to keep on coming. So at some point there may be shortage. We don't know, it may be 50 years, maybe 100 years, or it may be 200 years. There will be some issue with that. The second problem is air pollution, and that creates a lot of public health problems and other things. So what is the solution? The solution is renewable energy, solar and wind, free. It comes in most places, or all places, but they are intermittent. We have sunlight during the day, but we do not have sunlight during night, and wind wants to come when it wants to come. So we need to collect electricity from renewable energies like solar and wind and store them and utilize the electricity economically and efficiently. So actually, solar cells are now available. The bottleneck is actually the storage, that is batteries. So batteries are the most viable option to store electricity produced from renewable energies and utilize. The other thing on which the conference is focused is transportation. For transportation, there are not a lot of choices. You cannot use wind energy or solar energy directly in the car. So the only way we can have fossil fuel free vehicle is either operated with batteries or operated with fuel cells with hydrogen fuel. But I teach a course, I used to tell fuel cells have 50 problems to solve, batteries have 5 problems to solve, at least at the present moment. So that's why a lot of action, a lot of funding, a lot of research, both at the academic institutions, national labs, as well as in the industry is happening on battery technologies. Although it looks simple, battery has its own problems. I have listed 6 of them here. How much energy you can store in a given volume or given weight, how fast you can charge, discharge, how many cycles or how long we can use the battery before we have to replace, and what kind of safety they are going to have when they are on the road or when we use them for grid storage. And there are materials, some of them may be toxic. There are processes which may use additional chemicals. So what kind of impact they are going to have in terms of toxicity on the environment. And finally, cost, that is the most important parameter. All these factors contribute to cost. Cost is not just raw material cost, it's everything. And all of these 6 factors I have listed here, they are linked to severe material challenges, and that is the chemistry and physics of materials. What kind of structure they have, what kind of atomic arrangements they have, how do the atoms interact between themselves or among themselves, how are their energy levels arranged in different solids. All those physics and chemistry contribute. Then engineering comes into the picture. So once we have the right material, we have to do the right engineering to make it work. So it is very challenging. Also, although battery looks very simple on a piece of paper, you can draw the diagram. So I'm glad conferences like these are happening. Again, it is one thing to do the battery, make the cell in my lab, but it is another thing to make it in an industry and practically make it viable. There are a lot of know-how. Much of them are not published. It's all industry. So it involves 4 levels actually. First, materials development. Second, cell manufacturing. Third, cell integration. Fourth, infrastructure development. The issue with India right now, the issues are the first two. Material development happening to some extent, but not quite to the extent it is necessary. The second level is cell manufacturing. That is a big challenge at the moment for India. So more know-how, more education, developing the workforce with proper education, chemistry, physics, engineering, that is very critical. That is why, in addition to having conferences like this, it is also important that large number of students are educated on the basic fundamental chemistry and physics, how things work, so that if they are employed in the industry, if they go to industry, they will have a much better understanding and move things faster. Thank you very much.
Okay. Oh, okay, shall I proceed? Yes,
Yeah,
yes,
you
please.
can proceed.
Yeah. So, Honorable Vice Chancellor of SRM University, the Registrar, Director Research, Dean College of Engineering and Technology, Dean School of Basic Science, Dean Research, my dear colleagues, students and participants. It is my great privilege to deliver the vote of thanks and be part of this virtual international workshop on energy storage technologies for e-mobility in 2021, sponsored through the Scheme for Promotion of Academic and Research Collaboration, that is for Government of India, in association with the Energy Science Society of India. On behalf of organizing committee and the Department of Chemistry, I must mention our deep sense of appreciation for SRM management for providing constant supports and encouragement to accomplish our research goals. I also extend my thanks to funding organization, Government of India and the Energy Science Society of India for their financial and moral support. I must extend our deep sense of appreciation to Professor Arumugam Mantiram for readily accepting our invitation as chief guest and sparing his valuable time and experience with us in spite of his busy schedule. We would also like to express our sincere thanks to all invited eminent professors from all over the world for gracing this occasion and sharing your scientific innovations, opinions, challenges, and opportunities in this thirsty area of research. We thank you for being with us this morning. Finally, we also thank all my departmental colleagues, research communities from various organizations, technical staff, and student participants from all over India. I must mention at this juncture that the response for this workshop is overwhelming. The number of participants already registered has already crossed more than 1,800, which indeed what is called emphasizing the importance of this current workshop. At this juncture, I request all the student community to utilize this opportunity as effectively as possible and enrich your knowledge in the emerging field. Thank you, one and all.
Thank you, sir. I now hand over the session to Chair Professor N. Sasidharan and Co-Chair Dr. Ashok Kumar Sundaramurthy. Thank you, sir.
Okay, so welcome again. So the first session of the talk is so that is the keynote speaker by Professor Arumugam Mantiram from the University of Texas, Austin, USA. And those who are working in the energy storage devices and battery community, no need of any introduction. And anyhow, for the general audience, so I'll give the brief introduction about the professor. So Professor Arumugam Mantiram, he is the Cockrell Family Regents Chair in Engineering and the Director of Texas Material Institute at the University of Texas at Austin. After receiving his PhD in chemistry from Indian Institute of Technology at Madras in 1981 and working as a postdoctoral researcher at the University of Oxford and the University of Texas Austin with
2019 Chemistry Nobel laureate John B. Goodenough, he became a faculty member in the Department of Mechanical Engineering at UT Austin in 1991. His research is focused on batteries and fuel cells. He has authored 830 journal articles with 74,000 citations and an H-index of 134. He has mentored 265 students and postdoctoral researchers, including the graduation of 63 PhD students. So Dr. Mantiram is a fellow of 6 professional societies: Material Research Society, Electrochemical Society, American Ceramic Society, Royal Society of Chemistry, American Association for the Advancement of Science, and World Academy of Materials and Manufacturing Engineering. He is an elected member of the World Academy of Ceramics. He received the university-wide one per year Outstanding Graduate Teaching Award in 2012, Battery Division Research Award from the Electrochemical Society in 2014, Distinguished Alumnus Award of the Indian IIT Madras in 2015, Billy Clare or Ancourt Distinguished Centennial Engineering Research Award in 2016, Honorary Mechanical Engineering of the ME Academy of Distinguished Alumni Award in 2019, Henry B. Linford Award for Distinguished Teaching from the Electrochemical Society in 2020, and the International Battery Association Research Award in 2020. He is a Web of Science highly cited researcher every year since 2017. He delivered 2019 Chemistry Nobel Prize lecture in Stockholm on behalf of Professor John B. Goodenough. So with this brief introduction, I invite Professor Mantiram to deliver the talk. Thank you. The floor is open.
Thank you very much for a long introduction. Okay, can you see the screen?
Yes, sir. Yes, sir. It's
okay. So my talk is going to be focused on sustainable battery chemistries for particularly e-mobility. It's very hard to separate e-mobility from grid storage. So some things will be common, or some technologies may be used for both. So as I mentioned earlier, cost is the most important issue as we move forward to employ battery technologies, both for e-mobility as well as for grid storage. So first, those of you who may not be very familiar with how the battery works, so I'm taking the lithium-ion battery as an example and show what exactly is happening as far as the chemistry and physics is concerned. A battery will have a negative electrode called anode, a positive electrode called cathode, and then they are separated by an electrolyte that will allow the charge transfer only in the form of ions. The electrolyte should be electrically insulating. So during charge, the lithium ions move from the cathode to the anode through the inside the cell, while the electron moves through the external circuit from the cathode to the anode. During discharge, exactly the opposite will happen. During that process, ion and electron motion, you can also see the physics. During charge, let me wait for a second. During charge, we will be taking electron, using the electricity from the electrical outlet from a lower energy in the cathode and putting it at a higher energy level in the anode. During discharge, the electron will fall from this anode at a higher energy level to the cathode, and the free energy released during that process is taken out as electricity. You all know thermodynamics, the students. You study about delta G is equal to minus NFE. Sometimes when we learn thermodynamics, we may hate because it's a lot of abstract, first law, second law, so many things. But it's very fundamental thermodynamics, so you know how they are related. So the user time is actually the energy density, how long you can use it before you have to charge. And that depends upon two terms, the cell voltage times the amount of charge you can store in these materials per unit volume or per unit weight. So to maximize the cell voltage, this has to be as low as possible and that has to be as high as possible. But there is a constraint. These two energies have to lie within the band gap of the electrolyte. Otherwise, you will be doing unwanted oxidation or reduction on the electrolyte. For example, if this is below, the cathode energy is below the highest occupied molecular orbital of the electrolyte, then during charge, you will be pulling the electron from the electrolyte rather than from the cathode, so electrolyte will undergo oxidation. The same way, if the anode energy level is above the lowest unoccupied molecular orbital of the electrolyte, we will be putting the electron into the LUMO of the electrolyte and reduce it rather than putting it into the anode. So in the case of other batteries like lead acid or nickel cadmium, nickel metal hydride battery, they all have water-based electrolytes. In the band gap, when you use water-based electrolyte, the band gap is limited. So we cannot get more than, or the separation between LUMO and HOMO is smaller, so we cannot get more than 2 volt. In the case of lithium-ion batteries, we use water-free, non-aqueous electrolyte. So the electrolyte stability window is widened. So this is as low as possible. This is as high as possible. So we are able to get up to 4.3 volt per cell. So when we go from these cells to lithium-ion cells, the voltage is doubled. You can see. Therefore, the energy density or user time is at least doubled between charges. That's why all the action is on lithium-ion batteries, and lithium-ion batteries are also replacing these kind of batteries. Except in the car, we still use lead acid. That's very well established technology, low cost. So we still use that. So conventional lithium-ion batteries, when it was commercialized, it used the lithium cobalt oxide that has the layered structure as you see here, and a graphite anode that has also a layered structure as you see here. So how did this all happen? How did we get the lithium-ion technology for us to use now? The first rechargeable lithium battery concept was demonstrated by Professor Stanley Whittingham at Exxon Corporation in the United States. That was published in 1976 in Science, by using layered titanium sulfide as a cathode and lithium metal as the anode. So that had 2 issues. So concept was demonstrated, but it had 2 issues. First, we cannot lower the cathode energy below the top of the sulfur 3p band. So the voltage of any sulfide cathode will be limited to less than 2.5 volt or largely less than 2 volt. That's the first issue. Second issue, titanium sulfide does not have any lithium. Therefore, we are forced to use lithium metal as the anode. So that has its own problem in terms of cycle life and safety. So that was 1976. Professor Goodenough started his career in the 1950s, working on the physics and chemistry of all kinds of oxides. So he's very familiar how the energy levels are in various oxides. He started working on some lithium containing layered oxides. Titanium sulfide is layered, so you start with layered lithium containing cobalt oxide or nickel oxide. The reason is the oxygen 2p band is located at a lower energy compared to the sulfur 3p band. Therefore, you can lower the cathode redox energy to a lower state. So that means you can have access to higher oxidation states like nickel 3+, 4+, or cobalt 3+, 4+ in an oxide, but you cannot have these oxidation states accessible in the case of a sulfide, selenide, or telluride cathode. So suddenly the voltage was increased from less than 2.5 volt to 4 volt. And then also the cathode already contains lithium, so you do not have to take lithium metal as the anode. You can use lithium-free anode host such as a graphite as the anode. So that's how the lithium-ion concept was demonstrated by Akira Yoshino. So because of the concept demonstration in the beginning, oxide cathodes, that made the technology practically viable, and then demonstrating in practical cells the lithium-ion concept, they were given the 2019 Nobel Prize in Chemistry. So I was able to write an article last year, published in March 2020.
சொல்லுங்க boss.
You want to know more about how this whole thing developed and the chemistry and physics, you can refer to this article, that is open access journal.
ஐயோ மன்னிச்சுங்க.
If you put this title, you will see that article. It is open access in Google.
இருப்பேன்.
So that article has been already 47,000 times. So if you are more interested, you can look at that article. So now, how do we choose a battery technology? There are so many battery technologies. I will show you in the next slide. But in choosing a technology, at least we have to consider 6 parameters. I already mentioned this: energy density, power density, cycle life, safety, environmental impact, and cost. They are linked to severe materials challenges, and that is controlled by the basic physics and chemistry. So which technology we choose, which battery technology we choose, or which parameter I pay more attention depends upon the application. For cell phone and laptop, energy density is the most important issue. Life is not that critical because you tend to change your laptop or cell phone in 4 years or 5 years or even 3 years. When you go to electric vehicle, e-mobility, energy density is still important, driving range, driving distance, but it is a larger battery. Cost comes into picture, and it is on the road, larger battery, so safety comes into picture. And you also want to use it at least for 10 years so that you do not have to replace it. If you go to grid storage, it is going to be really a large battery, so cost is the most primary factor. Then life is important. Maybe you want to use it for 10, 20 years. And how fast you can charge, discharge, what kind of safety it is going to have. Even though it is on the land, you don't want to have any fire problem. If it is, the whole thing may be destroyed, then you will lose a lot of capital cost. So you see, the technology we are going to choose depends upon the application. So we need not think that one technology will take care of everything. In addition to that, operating temperature is important. If it is something like in Boston in the winter, it is going to be too cold. India, South India, it's going to be hot. Even Delhi in the summer will be hot. So they should be able to survive both low temperature and high temperature. And of course, we need the batteries to be able to do fast charging so that I can charge in 5 minutes and drive or use my laptop or cell phone, but not quite. We do not have that now. So that's a challenge. You know, when you charge your cell phone or laptop, it goes very slow. We become impatient. It is again the material we use, the graphite. So materials are the bottleneck. So I told you so many parameters. So pretty quickly, I will go over how these parameters are controlled by the material itself. For example, energy density is controlled by these 2 factors. That depends upon the electrode potentials or redox energies of the various things we use. This is actually solution. I also want to point out these tables are valid only for solution. So you can use it only as a guide. When you go to solid, the redox potential will vary a lot. For the same iron 2 plus 3 plus, we will have one redox energy in a sulfide, another redox energy in an oxide, another redox energy in polyanion oxide. And depending upon the structure, it will again change. The difference can be as high as 1 or 2 volts sometimes. It's amazing. So there is no redox potential table for solids. Redox potential tables are only for solution because that's a fixed coordination geometry in the solution. So I would like to remind that. So that's how you choose, you maximize your voltage, and the degree of lithium ion storage depends upon the crystallographic sites available in the cathode and anode. Power density is controlled by the electronic conductivity and the lithium ion conductivity in the case of lithium ion batteries. Cycle life depends upon how the structure is reversible and how stable it is when you keep on charging and discharging. Thermal stability is related to fire hazard and safety, and that is determined by all the three guys: dendrite on the anode, and oxygen release from the cathode, and flammability of the liquid electrolyte. So everything is together and cause a fire, but anode is the one which starts by forming dendrite. Environmental impact, materials processing and materials toxicity as well as processing toxicity. Cost is not only raw material cost, but it is all of the above. If I can make batteries with the high energy density, I have to make only 10 cells instead of 50 cells. So I save a lot of money. It is easy to control 10 cells as opposed to controlling 50 cells. So everything is cost, as an example. Now, as I said, lithium ion batteries are not the end of the world. There are so many other battery technologies we can think of, but there is nothing to beat lithium ion technology at the moment. Right now, it is based on insertion compound cathodes and insertion compound graphite anode. There is a lot of interest to use conversion reaction anodes like silicon or tin, but they have many more challenges. Sodium ion, analogous to lithium ion, early stages, lower cost, abundant, good sustainability. So they also use similar materials. They will always give a little bit lower energy density than lithium ion, but we have a big cost advantage. Multivalent ion batteries, lot of interest, because if you store one ion, you store 2 charges with magnesium, you store 3 charges with aluminum, but there are challenges. They will have lower voltage to start with compared to lithium or sodium. These ions will have a hard time with 2+ charge or 3+ charge to diffuse from one crystallographic site to another crystallographic site. There will be kinetic limitations or charging or discharging rate limitations. Also, we do not have good electrolytes. So challenges. So in my opinion, at the end of the day, for e-mobility, these are not going to make it. Metal sulfur batteries, you can think of with almost any of these anodes. Sulfur is plenty, abundant, low cost, but sulfur is a poor electronic conductor and lithium ion conductor. As you saw here, this is going to be problematic. And also sulfur is such an 8-membered ring. It forms polysulfides that is soluble in the electrolyte, and that crosses over through the separator from the cathode to the anode. And if you think of metal sulfur batteries with magnesium, calcium, or aluminum, they are multivalent ion. The challenge becomes even much more serious. Electrolyte becomes much more serious. So a lot of work is now happening only with lithium sulfur. Metal air batteries, non-aqueous systems, it is fundamental. Almost we can forget about it for application. Aqueous systems like zinc air has the potential for grid storage. Redox flow batteries, again, lower energy density, so mainly for grid storage, but they suffer from chemical crossover from one electrode to another electrode, causing efficiency loss problem. Finally, all solid state batteries, that is the holy grail of battery technology. Better safety, certainly. It could also provide higher energy density in principle, but there could be problems in terms of interfacial charge transfer. It is easy to transfer ion from a liquid to a solid or solid to a liquid, but it will be hard to transfer charges across the interface of two solids. That's a challenge. And then if you have a ceramic electrolyte, how are you going to make large area, large length solid electrolyte? Ideally, we want to have a polymer solid electrolyte, but we do not have one. So that is the challenge. So there is nothing is problem free here. Everything has pros and cons. So that's why I say for different applications, even for e-mobility, for different vehicles, different battery chemistries may be used. Some may need long driving distance, some may need short driving distance. So it depends upon a lot of different things to choose the right battery chemistry. So right now the technology is based on graphite anode, that's the only one. The cathode can be three of them, layered, spinel, and polyanion, and all the three were developed in the 1980s, or the concepts were developed in the 1980s by Professor Goodenough Group at Oxford, and then continuing to the University of Texas at Austin, involving three visiting scientists. Remember, three visiting scientists, they all had jobs in their country. Very interesting story. And they were fortunate enough to work with him. Mishishima had a job in Japan. He came, worked with Professor Goodenough as a visiting scientist / postdoc, did lithium cobalt oxide, lithium nickel oxide, left to Japan. Then Michael Thackeray came from South Africa, worked on spinel. Then he left. I finished my PhD. And then I worked 4 years in Madurai Kamaraj University in India. I thought my research career is over, but I had this slim of luck to go as a postdoc to University of Oxford to Professor Goodenough. So based on my PhD dissertation work, thesis work on lanthanide molybdates, I started working with him on molybdates and tungstates of iron containing, and that showed some interesting results. First, if you take iron oxide, the voltage will be less than 2.5 volt, largely 2 volt or less, Fe2O3. All having same 3 plus 4, 2 plus 3 plus redox couple, same redox couple. Simple iron oxide Fe2O3 less than 2.5 or less than 2 volt. As soon as you go to iron molybdate, the polyanion, voltage is 3 volt. You go from iron molybdate to iron sulfate, the voltage goes from 3 volt to 3.6 volt. Amazing. The same redox couple in an oxide 2 volt, you go molybdate 3 volt, you go to sulfate 3.6 volt. So based on the covalency of this sulfur oxygen bond or molybdenum oxygen bond, the iron redox energy is raised or lowered to different extent, so that makes a difference. I'm sorry, I will not have time to explain. I was teaching this in my course yesterday. I spent the whole class to explain everything for them. But if you need more, you can again look at this paper, which I wrote last year. You will have a better understanding. One interesting thing I want to point out. So they left, they went back to their country. I was the only one was able to not leave. Even though I was on leave from Madurai Kamaraj University, I was able to move to the University of Texas at Austin with Professor Goodenough in 1986, and ever since I've stayed there. There is one interesting thing I have to point out. So, as of now, as far as the insertion compound or the practical materials are concerned, there is nothing else available other than layered, spinel, or polyanion oxide. The polyanion family is very broad now, LiFePO4. Olivine, all kinds of materials, not only for lithium, but sodium, as well as for multivalent ion batteries. The whole concept, the whole thing, as far as practical things are concerned, they are still based on these three things. One interesting aspect, you see cobalt, the most expensive, the worst safety. Lithium manganese oxide, lower cost than this and better safety. This material, much better safety and much lower cost. Interesting to note, we care about a lot in the cost, but it is already there, progressively going from here to here to here. Good history. So with that, I'm quickly go over to 4 things. My topic is sustainable battery technology. So you can see here, the first thing we are now engaged in is cobalt-free lithium-ion batteries. Cobalt is the most expensive. So we have gotten rid of cobalt completely from lithium-ion batteries now. Next is lithium sulfur. where there is no transition metal at all. Third, there is no lithium because lithium could also become a problem. So cobalt-free sodium-ion batteries. Fourth, that is my dream technology. Sodium sulfur batteries, no lithium, no transition metal. That is the best you can think of. Sulfur is a byproduct from petrochemical industry. They want to really get rid of it. So you cannot think of anything better than this in terms of cost and energy density. Unfortunately, I will not be able to go over everything, but I will try to quickly go over at least these two. So in your cell phone, laptop, now we use a cathode which is layered like cobalt oxide, but we have three metal ions: nickel, cobalt, manganese, or NMC. The question is, why do we use three? Again, you can understand all these from that article, this article I talked about. Two primary factors. The first factor is the relative positions of these redox energies with respect to the top of the oxygen 2p band. Cobalt already overlaps. So if we charge more than 50%, if you pull out more than 0.5 lithium, you will oxidize oxide ion, meaning you will pull out electron density from oxide ion. So oxide ion will be oxidized to oxygen, it will be released. So cobalt has chemical instability problem. So only you can use 50% of its capacity. Your cell phone, laptop will say 100% charge. That is cheating. It is only 50% charge. But for customer, it is 100% charge. The other factor is the relative stability of these ions in the octahedral site versus tetrahedral site. You can use basic inorganic chemistry. Maybe all the chemistry students might have forgotten. If you have forgotten, go back to James E. Hughey book or Cotton and Wilkinson book. You will be there. Why I do this? This is what I was teaching when I was teaching in India for 4 years. So nobody has put anything like this before. So I've written all this here. So if you take cobalt 3 plus, all the 6 electrons are in the T2G band. If you take the difference between these two, that will tell you to what extent these ions love octahedral site or stable in the octahedral site. Cobalt 3 plus, weak stabilization energy. It really loves octahedral site. It doesn't want to move from the cobalt layer through a neighboring tetrahedral site to the lithium layer because it hates tetrahedral site. So cobalt is the best. That's why that was the first material, lithium cobalt oxide, used in 1991 by Sony because of that structural stability gift. Does not transform from layer to spinel. Manganese, small stabilization energy, so it moves very readily from that manganese layer, from this octahedral site through a neighboring tetrahedral site to that octahedral site. So it goes from layered structure to spinel structure. Voltage will be slowly decaying over many number of cycles. Car companies cannot handle it, so they don't want it, they cannot use it. That's the problem. Nickel, in between the two, in both the structural stability as well as in chemical stability. You see, nature is kind, God is kind, but we don't get everything we need. Manganese is good for one thing, cobalt is good for another thing. Unfortunate. And there are a few others listed here. Cobalt gives high conductivity, manganese is the most resistive. Manganese is cheap and abundant, cobalt is the least abundant. Cobalt is the most toxic, manganese is the least toxic, environmentally benign. Cobalt is most expensive, manganese is the least expensive. Nickel, very nicely in between manganese and nickel in all of these criteria. Basically, I'm teaching this paper. All of these criteria, that's why all the action is on manganese, nickel, by the battery community as well as the industry. Fortunately, nickel also gives high tap density. When the nickel content goes up in NMC.
Okay.
I'm sorry. I'm not creating this. Somebody else is talking. So nickel oxygen bond is very covalent. So it gives good electronic conductivity, although it is not metallic like lithium cobalt oxide. Issues are cycle instability, thermal instability, and air instability. That involves the bulk and surface of the cathode, as well as the electrode electrolyte interactions and crossover, all kinds of things. So that's where our research is focused. Now, it is important that when we do this, we make the right materials or make the material in right way. For example, the industry, when they will use secondary particle sizes of 10, 12 micron. Lot of small primary particles sticking together. This is not easy to synthesize. So my group has worked for 5-6 years. So we have perfected. We can make good material with any composition from 0% nickel to 100% nickel. We also have developed processes to dope hard to dope ions like aluminum and magnesium during this co-precipitation of hydroxides. So that's one good thing. We also do evaluate our materials with pouch full cells, not half cell, throwing lot of liquid electrolyte. Then that is good for academic research. And nobody is going to be interested as far as the practical industry is concerned. And as you see here, as the nickel content increases, the capacity increases, the energy density increases. That's why everybody is interested in using, in increasing the nickel content in these materials. But I'm comparing two material here. One has 80% nickel, another one has 94% nickel. You can see day and night difference in full cell cyclability. The 94 fades a lot, 80% is better. So the problem becomes exponentially severe as we increase the nickel content towards the end. Why? We get more energy when we increase the nickel content. Therefore, they undergo phase transformation that creates cracks. So that will affect the cyclability a little bit. But the more critical problem is this surface reacts with the liquid electrolyte. And that causes the dissolution of transition metal ions, which migrates from the cathode through the separator to the graphite anode, and that builds up thick ACA layer on the graphite anode. And we have done this by extensively developing and using the time of flight secondary ion mass spectroscopy that can also distinguish other lithium containing compounds from metallic lithium trapped on graphite anode, because that is the only one which will produce a lot of Li3 plus clusters. The others will produce these kind of clusters, and TOPSINS is mass to charge ratio, so you can kind of probe which species you have. So now here I am comparing the two anodes which were paired with this cathode, 80% nickel cathode and 94% nickel cathode. As you see here, everything is same. The only thing is the cathode is different. Electrolyte, separator, anode, everything same. In this graphite, you have the SEA layer formed only up to about 75 nanometer, whereas in this graphite paired with this material, you have 150 nanometer thick. Also, you have more nickel migrated from the cathode to the graphite anode in this case compared to that case. So metal dissolution increases, the deposition on graphite increases, impedance on graphite increases, so cyclability goes down. I also talked about thermal stability. All of these were charged to the same capacity. You can see this is 30% nickel, 33% nickel, 90% nickel, 100% nickel. The thermal stability decreases, safety becomes a problem as the nickel content increases. Air stability. Nickel 3+ is not very stable in the air. So when you expose the material to air, it forms lithium hydroxide and lithium carbonate on the surface, and that is called in the industry as residual lithium. If that residual lithium is more than 2000 parts per million, they cannot make good electrode, it will clog. It's very hard to make electrode on the cell. You see here, when I go to LiNiO2, the residual lithium is way up high, very hard to make electrode. So what do we do to overcome this? What do we do to overcome this? So that's where our research is focused. So I take the same problematic material, we put 2% aluminum for nickel, that is called high NCA. Without aluminum, it is called high NC. Again, we are analyzing the graphite. The cathode is two different cathode, everything else is same. The graphite that was paired with the cathode that did not have aluminum has more nickel on the graphite anode and more metallic lithium track compared to the anode that was coupled, paired with the cathode that has 2% aluminum. That 2%, 1% aluminum make a big difference in the cyclability as well as in the voltage stability. Amazing. It's not only aluminum, you can dope with lot of other different things. Every time this will happen. I compare here again, undoped material versus magnesium and aluminum dope, better cyclability, better thermal stability, better air stability. It's usually when you try to fix one thing, you will lose something else. In this case, you dope, you get better cycle life, thermal stability, and air stability. This is amazing. So why does it happen? What is the magic with magnesium or aluminum or other dopant? All these bands are next to each other. They have edge-shot octahedra, the metal ions see directly each other. So there is a good delocalization of the electron density. The metal dissolution involves metal ion, metal oxygen bond breaking. That involves oxygen mobility and electron mobility. So the oxygen mobility, electron mobility is very good if you do not have any dopant. As soon as you put a dopant, that's like a speed breaker that perturbs the electron delocalization. The lattice becomes more robust. So oxygen mobility and electron mobility decrease. Some metal dissolution is suppressed. That makes a big difference. The question is next, would all ions dissolve? It doesn't look like. Only those ions which have an electronic configuration that is susceptible to either dynamic or static Jahn-Teller distortion, having one electron in Eg band, they are all susceptible to metal dissolution. Cobalt, you see here, low spin, there is no single electron in the Eg band. It is not a Jahn-Teller ion. So that is another gift to the cobalt. It does not dissolve like manganese. Manganese is the worst. Nickel is intermediate. Cobalt is the best. You see again here, all fundamental physics and chemistry playing a role on everything. Finally, cobalt is the cathode is the most expensive. 50% of the cost, material cost is from cathode, and in that cobalt is the most expensive. And we have eliminated cobalt last year. NMA, 90% nickel, 5% manganese, 5% aluminum, no cobalt. That shows performance and safety, thermal stability, and rate capability as good as or better than cobalt containing material. So the conclusion, no more cobalt is needed. Cobalt is out. We can get rid of it. So we do not have to worry about it. My flow chart showed, this is number 2, going from lithium ion to sodium ion. Only one slide I'm going to show. The difference between sodium and lithium is sodium prefers both octahedral site and trigonal prismatic site. So when you charge discharge, there is a lot of phase transformation. That is an issue compared to lithium ion. So we need to work that out. Also, electrolyte stability, dissolution, lot of different things have to be done with sodium compared to lithium. Too many things have been done. So we have to learn from lithium and then apply to sodium ion. The third, lithium sulfur, the best, 10 times more capacity, but poor electronic ionic conductivity, low utilization, low practical capacity, poor cycle life, self-discharge, lithium metal degradation. It is a mess. So what does the academic community do to overcome the poor lithium ion and poor electronic conductivity? Put a lot of carbon, throw a lot of electrolyte, and that will reduce the practical energy density pathetically low. So what needs to happen? Something like this: low carbon, low electrolyte, and low lithium on the anode. These 5 5s. If you need more, you can know more about these from this article. And we should also do pouch cell instead of doing coin cell. Coin cell is no good at all for lithium sulfur batteries. Very much different performance you will see. So we have been focusing having these parameters in petrol and then making pouch cell. We also do anode free full cell, meaning on the cathode you take Li2S, on the anode, on the cathode you take Li2S, and on the anode you don't take anything. Bare current collector, that's anode free. So you eliminate lithium, so you do not have to worry about handling thin lithium foil. It maximizes the energy density, and the cells can be assembled without any self-discharge. And we also do some molecular engineering on the polysulfide, so you can turn it around. If you don't do all those, you have poor cyclability. If you do those, then you get better cyclability. We have also done a lot of time-of-flight secondary and mass spectroscopy. The reason lithium metal gets degraded in the lithium sulfur battery is lithium metal, the sulfide species moving from cathode to lithium metal anode is slowly converted from the sulfide species to oxidized species using the salt. So that is the problem. So how do we eliminate it? If we add small amount of tellurium to the sulfur cathode, you can suppress that kind of transformation from sulfide species to oxidized species. Again, if you want to know more, you can look at this paper. That gives you much better lithium deposition and much better cyclability. Finally, sodium, sulfur. This is a dream technology. I want to show one. I cannot go through any detail. At least I want to show the cyclability. This is the best you can see in any literature. Nobody has this kind of data with sodium sulfur, high capacity, at least 200 cycles. So we are very energized. I think there is a way to make sodium sulfur technology possible. Not tomorrow, not in 3 years, but down the road, I think medium term or long term, it can be made workable. I'll skip this. So finally, right now, current lithium ion is 250 watt-hour per kilogram. If you go to high nickel, it can go to 300. If you replace graphite anode with lithium metal, that can go to 400. If you go from lithium to sodium in this, if you go to sulfur, that can go to 500. If you replace lithium by sodium in all of these, you can have these kind of numbers. These will be 50 to 100 watt-hour per kilogram, less than the lithium analog. And finally, I would like to thank all my current students. This is my current group, as well as all the people who have worked with me over the years. 53 of them are faculty all over the world. I'm very grateful to all of them and all the funding agencies heavily funded by the Department of Energy, as well as some of the industries. Thank you very much.
Yeah. Thank you, Professor, for the enlightening talk on battery materials, challenges, and opportunities related to various battery chemistries. Now the session is open for discussion. Maybe 1 or 2 quick questions due to lack of time. Or you can also send an email to Professor, so he can clarify for your mail. And
Too much.
Yeah.
Too complex.
Okay, so definitely now the audience and participants, you can send a mail to Professor, and I'm sure that he will reply and clarify your doubts.
There is one question in the chat box. There is one question.
Can manganese replace cobalt in a long run? Someone posted it.
The problem is manganese dissolves, dissolution. We use LiPF6 with ethylene carbonate or dimethyl carbonate. LiPF6 creates HF. When you have trace amount of HF, manganese dissolves. So manganese dissolution is the major problem. That affects the graphite anode. If you change the anode, graphite, to something else, and if that is not poisoned or attacked by the dissolved manganese, then it is possible. Manganese also, layered manganese, if you take, it will transform to spinel. So there are challenges, but we have to judiciously think the system as a whole, electrolyte, anode and cathode and then C.
Sir, one more question, sir. Sir, my name is Dr. Ashok, sir. I am working in the Department of Chemistry. So you are, force of motivation. You are publishing very high impact papers. Can you give us some idea, so how to work like you?
The battery business looks simple, but it needs lot of know-how, lot of fundamental chemistry. Okay, and then how the experiments are done in the lab, right? So making good material like I showed, right particle size and making the right kind of cells to demonstrate. It's not easy. That is actually, I wanted to say that in my inaugural 5 minutes talk. I think we have a long way to go in India. Education is essential, training is essential. It is not easy to jump into and do it. I mean, I started my battery research in 1985, right? And it is 40 years and working with the best person on earth you can think of. So that helped me to understand with physics and chemistry together. I was fortunate enough, lucky enough to work with Professor Goodenough. So that shaped. Otherwise, I will be nowhere. Nobody will know me. That helps. And it also needs hard work. It's not easy. I do not have to have like 35 people in my group. No, I can have 3 students and get away with that. But it needs a lot of passion, a lot of hard work, and you transform that to your students, right? If you are lazy, then if I am lazy, my students will just follow that. So it is like that. So, I mean, I'm not. So to answer your question, it is very hard to say exactly. I kind of went over, but I think a lot of reading, the cultivating the students and the community is very important.
Okay, so
thank you, sir.
So thank you, Professor, for your suggestions and opinions. And so thank you once again, Professor, in spite of for the late night at Texas. So thank you very much. Thank you, sir.
Thank you very much.
Thank you very much. Bye.
Thank you very much, Professor Manthiram. Thank you.
So Mayalagan, the next speaker is there on the line.
Yeah, Professor Ashutosh Iriam.
Hello.
Yeah, Professor. Good morning. Yeah, just a minute. So very good morning, and it's my great pleasure to invite Yasutoshi Iriyama Sensei, Nagoya University, Japan. So Yasutoshi Iriyama Sensei is currently working as a professor of nanostructure design, Department of Material Design Engineering, Graduate School of Engineering, Nagoya University. His laboratory is mainly conducting research on new storage batteries. He has authored over 290 journal articles with 9,044 citations and an H index of 55. With this brief introduction, I invite Yasutoshi Iriyama Sensei to deliver the talk.
Okay, thank you very much.
Yeah.
Now, can I start?
Yeah, please share.
Okay. I will share the just a minute. Can you see my presentation file?
Yes, Sensei.
No problem?
Yeah, no problem.
Okay, voice is no problem. Okay. Yeah. Thank you. Good morning, ladies and gentlemen. So my name is Iriyama from Nagoya University. So first of all, I would like to say special thanks to the organizing committee, especially Professor Maya Ragan and Professor Murugan to give me this great opportunity. And today's my talk is challenges toward a large-sized oxide-based all-solid-state batteries. This is actually the challenges. We have not yet produced the all large-sized solid-state battery, just challenges. Today's my talk is this is outline. So at first, I will briefly introduce our motivation toward large-size oxide-based solid-state battery. And the second and the third topic is our results on these some topics. And finally, I will summarize my talk. So, as you know, the EV's research very actively demonstrated in the world. And most of them has applied lithium-ion battery using liquid electrolyte. However, some other efforts are also devoted to develop advanced batteries using solid electrolyte. So, for example, China's company NIO is developing some new electric vehicle with 150 kilowatt-hour solid-state batteries for 2022. So EVs will also play important role to reduce environmental pollution and also promote the effective usage of sustainable energy, and also to contribute new cities where the materials and some information are well connected. Of course, the batteries used in EV will be better to reusable for the used cars and some housing and others. So based on this concept, we think the oxide-based or solid-state battery is one of the candidates, because that is the safety, the high energy density, the long life performance, and high thermal stability. In the current state, the small size oxide-based or solid-state battery has been commercialized, and they are actually two types. The one type is a thin film type battery, where the cathode layer and the solid electrolyte layer and anode layer are sequentially piled up by sputtering and vacuum evaporation. The another type is the multi-layered or solid-state battery, where especially these batteries are now manufactured by Japanese company. They have applied ceramics condenser technologies, and they have multiplied cathode and solid electrolyte and anode layers like that, and cross-sintered and fabricate this kind of some multi-layers. So these batteries must be very beneficial for the usage for the IoT and wearable devices. However, in the current stage, the capacity is not sufficient. And of course, it's almost all these batteries basically use not high lithium conductive solid electrolyte. Then its application to a large devices has still limitations. So to develop large-sized oxide-based solid-state batteries, actually we have to consider how to prepare it. So based on several calculations and estimations, this ceramics processing has been considered as a candidate to develop large-size oxide-based batteries. And these techniques are categorized into three species based on the material input: the suspension type, gas phase type, sprayed powder type. For example, the multi-layered solid-state battery use this suspension type input. A thin film battery uses a gas phase input. But on the other hand, we are focusing on one of the sprayed powder input system. So that is the aerosol deposition. It's called as AD. So this is because the AD can realize quick and some wide area coating, ceramics coating without any substrate heating at some process situations. This is very good for preparing. actually fabricate some large size batteries using high lithium conductive solid. Before I explain that, let me briefly what is aerosol deposition. So as I mentioned, the aerosol deposition uses the powders as a source material for the coating. This red point is a powder, and this is a powder pot. So this powder pot is connected to vacuum evaporated chambers through the nozzle. And the substrate is located here, and this substrate moves back and forth during the deposition, but the substrate is not heated at all. When the gas is injected in the powder pot, the aerosol is generated, which is sprayed to the substrate. And then this kind of ceramics coating is realized. This is actually the cathode ceramics coating grades. So this AD has been applied to many materials. And for example, the transparent aluminum oxide coating is realized in this size by AIST Group in Japan. And also, Toto has commercialized the AD for preparing trim oxide film for semiconductor manufacturing system. So when the particle hit on the substrate, the particle actually deformed and crushed. And also local sputtering also happens. So these situations provide very high surface energy on the particle surface, and its reduction of surface energy is a powerful driving force for room temperature bonding. So in this case, the substrate is not heated at all. Therefore, the chemical reaction energy is not required for the bonding and densification. So to fabricate the large size oxide-based solid-state batteries, we need high lithium conductive solid electrolyte like LATP, LLT, and LLG. As you know, LLG is discovered by Professor Murugan and Professor Webner. And these are fragile and hard ceramics. And this is also true for the cathode materials like lithium cobalt oxide, lithium manganese oxide. When these two powders are mixed and pressing, they just form a point contact. And then this situation inevitably increases interfacial resistance due to less contact area for lithium transfer. Of course, sintering is a straight manner to densify the ceramics. However, both electrodes and solid electrolytes are composed of different elements. And then some heating, actually some sintering process often provide mutual diffusion layer as an interface, which often block lithium ion transfer. Again, high resistive interface is formed. Now the question is how to form low resistive cathode high lithium conductive solid electrolyte interface for large size oxide-based solid-state batteries. We think aerosol deposition make it possible. Now, firstly, I would like to introduce our results for the preparation of bulk type oxide-based solid-state battery using the AD. So bulk type solid-state battery, its schematic image is as shown here. The cathode layer is composed of active material, conductive additive, and a solid electrolyte. This situation itself very resembles with conventional lithium-ion batteries using a liquid electrolyte in place of the using of the solid electrolyte. In this image, so actually this is reported by Professor Tatsumi Sago's group. They have used sulfide-based solid electrolyte. It is ductile, soft material. Then this composite electrode layer is easily formed just mixing and pressing. However, as I mentioned, in case of the oxide-based all solid-state batteries, this is very difficult to prepare. To prepare this kind of composite electrode by the AD, we used this kind of a solid electrolyte coated cathode particles as the starting material for the aerosol deposition. The core electrode material is NCM111. The diameter is 10 micron in this case. And the coated powder is LICGC with 0.5 micrometer in diameter. This LICGC is manufactured by Ohara Incorporation, and its ionic conductivity at 25 degrees C is 10-4 volt. So to prepare this kind of coated powders, we use this powder mixing equipment and add 2 powders in it and mixing at room temperature. The other consequence, we get this kind of LICGC coated NCM powder. So when we use this kind of coated powder as a source material for the AD, so this kind of composite layer is formed at room temperature by the AD. The left figure shows a cross-sectional SEM image, and right figure is an EDX profile. The yellow part is the manganese corresponding to the NCM111, and the purple is the phosphorus corresponding to the LICGC. The blue is the substrate, it is stainless steel. So as you can see, this dark gray colored region corresponds to the yellow colored one. Therefore, this part is electrode area. And some dark gray colored region correspond to the purple color. This is solid electrolyte region. So from this image, we can distinguish, so where is the NCM, where is the LATP, and its volume percentage is actually estimated from this image. And the value is about 6 volume percent for NCM111. Also, by using 3D FIB SEM analysis, we can understand how this 3-dimensional connection is realized in the composite. So this is LATP, the 3D connection. As you can see, they look to connect. Actually, by image analysis, we can estimate the tortuosity, that is how the LATP region is connected 3-dimensionally, and its distribution we can analyze. So as you can see, that this tortuosity value is 3, and its distribution is narrow. So therefore, it's basically homogeneous, some composite electrode is formed. However, so as you can see, I showed some of the red points. So this red points is a voice over the some size of the 20 nanometers. So as you can see, in the current state, these voids still remain. This is actually the problem. However, the composite electrode itself is formed, as I showed. So when let's see the interface. So we check the mutual diffusion layer thickness. So this is a magnified TM image around the LICGC and NCM111. And as you can see, the mutual diffusion layer is estimated to be less than 5 nanometers. When the NCM111 is formed on the LICGC at 700 degrees Celsius, the mutual diffusion layer thickness is about 20 nanometers. So therefore, the thin some mutual diffusion layer is formed, and looks to be very nice as compared with the heating systems. Then we prepared these composite layers on LLG substrate and combined with a lithium metal anode and pressing them at 150 kilopascal. This layer was fabricated on the laboratory, therefore the size is very small, 1 square centimeter, 6 millimeters. and the thickness is about 20 microns. As you can see, the charge and discharge reactions are repeated at 100 degrees Celsius, and the stable reactions are maintained. So this is a rate capability of the battery operated at 100 degrees Celsius, and the charging current was always 0.05 milliampere per square centimeters, and the discharging current changed from 0.05 to 1 milliampere square centimeters. So as you can see, even at 1 milliampere square centimeters, we can get a capacity about 20 milliampere per gram. But of course, this current density is very low to the application for the large size device. Now, therefore, we have to consider how to improve this performance. Then my next talk is the low temperature sintering for low resistive interface for high power bulk type solid state batteries. So we have to reduce the resistance of the composite electrode. Now I consider two factors. The one is the electronic conductivity. So these are the figures of the electronic conductivity of NCM111 and lithium cobalt oxide. So the NCM111, its electronic conductivity is basically 10 to minus 7th and 10 to minus 3rd Gs per centimeters at room temperature. However, in case of lithium cobalt oxide, this electronic conductivity is 3 or 4 orders higher than that of NCM111. As a consequence, when we prepare the composite electrode, the electronic conductivity of the composite electrode also has 3 orders higher value than that of NCM111. So this will be effective to reduce the resistance of the composite electrode. The second problem is electrode and solid electrolyte interface. As I mentioned, the very thin mutual diffusion layer is formed between the cathode and solid electrolyte interface. However, I will show in later that this interfacial resistance can further reduced by low temperature annealing. To investigate such interfacial properties, the best way will be to fabricate a simple system. Then we just prepared a lithium cobalt oxide layer on plate state LICGC, which is called as LATP in later some presentations. Then we prepared a lithium cobalt oxide layer on LATPC. So in this case, we should select appropriate particle. The particle size is 2 micrometer in this case. It's mostly laboratory-made particles. The Raman spectroscopy, we can understand this is a layered structure of lithium cobalt oxide. So this is a surface SEM image of the lithium cobalt oxide from LATPC. The bottom is an EDX profile of cobalt. The cobalt looks to be almost uniformly formed, about 90%. So this is a cross section of the this multi-layers, and this part is lithium cobalt oxide, and LATP is the bottom. The thickness of lithium cobalt oxide is about 2 micrometers. And this film looks to be composed of small sized particles with a few hundred nanometers. So this is some same SEM image of starting powders with the same scale. So as you can see, almost same particle size is presented in the film. So therefore we can understand this film is formed by the some accumulation of these primary particles. Now, to check the reactivity between the lithium cobalt oxide and LATP, we investigated the XRDs and the Raman spectroscopy. So this left figure shows the XRD pattern of the multi-layers, where the multi-layer was heated at a different temperature. The black one is at pristine state, the red one is 300, the green one is 400, the blue one is 500, and the orange is 600. And also, as a reference, both LATPC and lithium cobalt oxide is shown. So as you can see, even at the room temperature, we can find the diffraction peaks from lithium cobalt oxide in this dotted region from 003 and 006 planes. And these peaks actually appeared even after the heating at 600 degrees Celsius. However, if the sample is annealed at over the 500 degrees Celsius, the diffraction peaks from 003 is actually shrinked. I'm sorry, it's not clearly shown, but actually decreased. So that means some side reaction takes place. This is clearly observed by Raman spectroscopy. We measure the Raman spectroscopy of these samples. So in case of pure lithium cobalt oxide, only the A1G and EG peaks are observed as shown in this black line. However, when the sample is heated over 500 degrees Celsius, so we can find cobalt oxide peak. So that means the side reaction takes place by the heating over 500 degrees Celsius. Next, we measure the cyclic voltammetry of this multi-layer by using this half cell. This LATPC is actually liquid-tight lithium conducting solid oxide sheet. And then we can immerse the liquid electrolyte opposite to the lithium cobalt oxide layers, and we can combine the lithium metal for the counter and reference electrodes. And the CV measurements were carried out at 25 degrees Celsius. So when the annealing temperature less than 400 degrees Celsius, we can find redox peaks, typical redox peak of lithium cobalt oxide at 4.0. However, once the annealing temperature exceeds 500 degrees Celsius, so very broad peak just appears. And in case of 600 degrees Celsius, almost disappears. That means the multi-layer becomes very, very resistant situation. To understand this CV phenomena, we investigated the interfacial resistance by EOS. The measurements were carried out at 3.0 volt and 4.0 volt. So as you can see, at 4.0 volt, we can find a newly semicircular arc at the low frequency region, and we can estimate the interfacial resistance from the diameter of this semi-sample. So this interfacial resistance was measured for each annealed samples. This is actually the variation. The room temperature sample, that means just prepared samples showed 400 ohm square centimeters, but which decreased to 100 ohm square centimeter levels. So by the annealing at 350 degrees Celsius. However, once the annealing temperature over the 400, the interfacial resistance increased and further increased at 500 degrees Celsius. So this means, reduction of interfacial resistance is realized by low temperature annealing. However, when the multi-layer is heated over 400, the drastic increasing due to the side reaction takes place. Actually, the 500 is a critical state. So to understand why this reduction takes place, this mild temperature annealing, we measured TM yields analysis. So this is some hardest stem image around the LATP LCO region for the pristine sample. The ELS measurements were carried out with a spatial resolution of 2 nanometers. So the ELS spectrum is actually the sum of the various spectrums, and that should be some reasonably separated. So reasonable separations, we use non-negative matrix factorization called as an NMF. Actually, this some reasonable separation was carried out by my colleague, Professor Noto Sen. If you are interested in this NMF analysis, I hope you read these papers. But anyway, so this analysis, the ELS spectrum was divided into 3 regions: LATP, LCO, interface region, that is spatially distributed as shown here. So LATP region is the left side, LCO region is the right side, and the interface region is presented in the middle. The same analysis was carried out for the 300 annealed sample, and its distribution was observed the same. Now, so let's see how the spectrum changed pristine and between pristine and annealed samples. The upper data is from the pristine samples and the bottom data from annealed samples. The blue spectrum are measured from interface region in each samples, and the red part is from LCO region, and black part is LATP region. So in this spectrum, so we focus on the titanium, oxygen, and cobalt peak. So among these spectrum, we focused on the interface region. In case of the pristine samples, we can find both titanium and cobalt is presented. This titanium peak position is slightly shifted to the lower angle as compared with the perfectly titanium 4+ state. So actually the pristine, the LATP sample itself still also shifted. So that means reduced. And also the cobalt, this cobalt peak is also shifted to a lower energy position. So that means LC as compared with the lithium cobalt oxide composed of cobalt 3+. So that means this cobalt is also presented as a reduced state. However, in the annealed samples, we can find no titanium peaks, and the cobalt is still presented, but they are still shifted to a lower angle. To see this situation, we can write this kind of schematic image. At the pristine states in the interface region, some artificial metastable interface composed of containing cobalt and titanium as a reduced state will be formed. That will be pyrolyzed just by the annealing at 300 degrees C, and probably cobalt oxide is formed. So the reason why this assignment is true is that when we look back the Raman spectroscopy carefully, we can find tiny peaks from the cobalt oxide even after the 300 degree annealing. However, the question is why the interfacial resistance is decreased even though the cobalt oxide is formed at the interface. So to understand this reason, we next focused on the plasmon energy loss spectroscopies. So plasma loss energy spectroscopies basically detect some density state of the sample, assuming the composition and chemical bonding situation is almost same. So this is some plasma loss energy mapping. The blue part is a lower energy, that means a lower density state. And some yellow part is basically high density state. But if the sample is different, of course, we cannot compare. But when we carefully see this plasmon energy loss mapping, this lower energy region is basically distributed in the LATP region. So this bottom figure is some NFM analyzed interface region. So you can see this blue part is dispersed in the LATP, mostly dispersed in the LATP region. So that means initial state is a less contact state. However, when the sample is heated to 300 degrees Celsius, this plasmon loss energy region is decreased. So that means the better contact state, I mean, higher density state is realized. So these results, we can consider that even though the resistive cobalt oxide is slightly formed, this is actually the negative factor. However, this rearrangement of some interface region probably improved the better contact and then reduce interfacial resistance. So this fundamental some data we next applied to the bulk type or solid state battery, where the cathode layer is a lithium cobalt oxide and LiCzC, and which are combined with LLC and lithium metals. And the charge and discharging reactions were carried out at 100 degrees Celsius. The upper one is a pristine sample. That means a no heating state. And this pristine state still provides 30 milliampere per gram capacity equal to 1 milliampere square centimeters. But this was improved to the 70 milliampere per gram by annealing at 350 degrees Celsius. However, degraded to the 20 milliampere per gram by the annealing at 500 degrees Celsius. So that means this low temperature annealing is effective to improve the battery performance. But actually, the battery charging discharging reaction in composite electrode is influenced on various factors. Then its detail should be clarified further. But in the current state, our best all solid state battery combined with LLG lithium, the battery can deliver the capacity even at 100 milliampere per square centimeters. This will be very good rate performance as compared with NCM 111. So this low temperature annealing is also effective to improve the battery performance. For example, the 5 volt plus solid state batteries. So this is the examples. We prepared the lithium nickel manganese oxide and LiCzC composite electrode and combined it with ripon and lithium. The battery looks to work well. However, when the charge and discharge reactions are repeated, the battery capacity is degraded. So after these measurements, we tried to measure cross-sectional SEM image. However, the battery was too brittle to observe the SEM image. So therefore, this is probably because this LNM shows a large volume change for the charging and discharging reaction as compared with the lithium cobalt oxide and NCM 111. So therefore, selecting some good cathode material with smaller volume change is very important to stabilize the reaction. Of course, in these experiments, we prepared this kind of small size samples. The substrate size is just 1 square centimeters, and the thickness is just less than 20 micron. However, when we repeat the deposition, it is possible to fabricate 50 micrometers. And also, by using a large size AD system, it is possible this kind of large size electrode coating, as is the aluminum transparent layers, as I introduced initially. And finally, it will be better to explain why I have explained some charge discharge reaction at 100 degrees Celsius. So this is actually the problem for the lithium metal sites. So as you know, the LLG is basically stable with the lithium metal. However, when the breaking stripping reaction repeated for the 25 degrees Celsius, some short circuit usually happens. However, when these breaking stripping reactions are carried out at 100 degrees Celsius, a stable reaction is realized. This is basically because in case of some 25 degrees Celsius, the repetition of the breaking stripping reaction provides a void around the interface. This upper side is a lithium, the bottom side is LLG. As you can see, some voids are presented. Once the void is formed, the next lithium breaking reaction occurs at this adhered region. Such local lithium breaking reaction will be the trigger for the short circuit. But on the other hand, in case of the 100 degree breaking stripping reactions, such voids are not formed, and probably uniform breaking stripping reaction is realized. Then this is good to investigate the battery performance at especially when we use lithium and LLG. And also, even our lab scale aerosol deposition, it is possible to fabricate this kind of small size of devices, and it's a flexible solid state battery. And actually, in this case, we can fabricate a crystalline cathode layer on LiPo film. So this is basically difficult in conventional method because the LiPo, the thermal stability is less than 200 degrees Celsius, but the crystalline cathode layer requires over 700 degrees Celsius for the crystallization. But AD can realize the crystalline cathode layer formation at room temperature. Then this kind of cell configuration is possible. And here the lithium is actually plated between the LiPo and the substrate, and the anode-free battery is realized. Okay, so let me summarize my talk. So as I mentioned, actually it's a big challenge to develop a large size oxide-based solid-state battery, and we have still working on it. And I introduced that the aerosol deposition is a kind of the possible process to develop large size oxide solid-state battery, because it's not required. It does not require any heating. Even it's better to heat after the preparation. The temperature is about 400 or something like that, which is much lower than the sintering process. So, of course, I understand in the current stage, we have many problems to realize oxide-based large-size battery for EV application. But I hope and I wish this kind of international conference and some fruitful meeting can make a good breakthrough to realize it. So thank you very much.
Okay, so thank you, Sensei, for a wonderful talk on all solid-state batteries and the basics. Now the talk is open for discussion. So if you have any questions, please you can ask him. So can you check, is there any questions on the chat box, Mayalavan?
Any questions, audience? Please type in the chat box if you have any doubts and questions.
So, before getting some questions, this is Professor Murugan. This is for the
Yes, sir.
So, Professor Iriyama, can you hear me?
Yeah.
Okay. This is Murugan.
Oh yeah, nice to meet you.
So I think, what about the interfacial layer? So before putting the cathode by means of the aerosol depositions, if you have a thin layer, some glassy or amorphous layer, can you solve this problem?
You mean this control the metastable interface?
Yeah.
Mm,
Artificial.
Yeah, artificial. Yeah. This artificial state we can control. Yeah, as you mentioned, if we put another material on the, for example, the LATP, we can change this artificial state. It's a resistance. Therefore, there are several possibilities. In the current stage, this metastable interface looks to be a low crystalline state. Yeah.
Maybe for the large scale production, this could be an immediate solution. I think so. That's what people are successful with the anode-free engineering. Even they're putting some ionic liquids or some amorphous layer, they could try to resolve these problems.
Yeah. Yeah, for the practical application, of course, I hope it's one of the solutions.
Yeah.
But yeah, I understand. Yeah, several difficult problems. But in this case, I have used LATP. But probably the better solution is to use a more soft or ductile materials. So that case, some how to say, the source powder is more effectively coated on the substrate, and the coating layer also very fast. A few micrometer is just a few minutes or sometimes few seconds. Therefore, very fast coating is okay. But it's in the case of the lithium cobalt dioxide and LATP, probably the few percent is just used for the thin film coating. That is currently the serious problem. But it's largely improved by using a ductile solid electrolytes. Have checked it. But the problem is we are not good solid electrolyte for such a ductile but high lithium conductive one for the oxide-based ones, right?
Okay, thank you. Thank you very much. Someone asked, can you explain the role or advantage of aluminum and titanium in LATP? I don't know who is asking. Is this from somebody from chat box?
So the titanium is basically the very important element to form the Nash-Cohn structure one. The basic structure is lithium titanium 2 PO43. But the aluminum incorporation is basically increase the lithium amount. For example, if aluminum is exchanged with the titanium, the extra lithium is presented in the LATP, which can largely improve the ionic conductivity. And also, it's also effective to reduce the grain boundary resistance in LATPs.
I think Dr. Mayal again, you can.
Yeah. Professor Ashutosh Rema, thank you very much for a wonderful presentation. And thank you, Professor Sasidharan. And there will be a short tea break. I request everyone to rejoin the session after 10 minutes. So the tea break will be after 11:05. We can rejoin at 11:05. Just 10 minutes tea break.
Okay,
So,
okay.
So, Viyama, thank you very much for your.
Okay, thank you,
Viyama,
sir.
thank you. Photo salon.
Okay.
ஏழாம் சரி சரி நீங்களே இன்ட்ரடியூஸ் பண்ணீங்க. எனக்கு லேட் ஆகுது, ஏன்னா இது விசி ஆஃபீஸில், இல்லைன்னா நான் டிலே பண்ணலாம். நீங்கள் இன்ட்ரடியூஸ் பண்ணி நீங்கள் பார்த்து பண்ணிக்கோங்க. ஓகே, ஏன்னா இது வேற எந்த ஆஃபீஸ்னா பரவாயில்ல. விசி ரிஜிஸ்டார் 2 பேருமே, விசி ரிஜிஸ்டார் 2 பேருமே இருக்கிறாங்க. நான் போய் ஓகே ஓகே பாய். ஆஃப் பண்ணிட்டோம். சரி சரி.
Hello, you can hear me?
Is it audible, sir?
Hello, you can hear me?
Audible.
I cannot hear you.
Check your audio, sir. Sagar Mitra slide போட சொல்லுங்க. அந்த ஒவ்வொருத்தர் வராங்க ஸ்பீக்கரோட ஸ்லைடு போட சொல்லுங்க. Please check your mic, sir. Can you speak?
Yeah, I can hear you now. I can hear you now.
Please unmute your mic, sir.
I can hear you now.
Okay. Okay, the session starts now. We welcome Professor Sagar Mitra from IIT Bombay. He is working as a professor in Department of Energy Science and Engineering, IIT Bombay, and in the energy storage field. Sagar Mitra research interests include developing new electrochemical storage technology, electrode design, characterization, and modeling of electrode materials for lithium-ion, sodium-ion, and magnesium-ion battery. Currently, his research group is actively participating in commercial-grade lithium-ion battery development for electric scooter and solar lantern applications for rural India. He has published more than 120 publications with over 6,000 citations, and he filed 22 patents in battery materials, which H-index more than 31. So Professor Sagar Mitra has established a world-class lithium-ion battery fabrication unit to produce more than 50 commercial-grade power cells per day. And many of them knows Sagar Mitra is well known in the battery personality in India. So I welcome Sagar Mitra to present his lecture.
Okay, good morning, everyone. Thank you, the organizer, to invite me and giving me opportunity to give a talk. So I can start?
You can share your slide.
Okay. Yeah, you can see now?
Yeah.
Okay. So, good morning, everyone. I have a time of, let's say, 40 minutes, around 40 minutes. So I'll be giving you some glimpse of what we do and what could be done in electric vehicle era. And I'll be giving you perspective of, we know everything that electric vehicles without lithium-ion battery may not be possible. I also believe that. So after lithium or with the lithium, what could be done for next maybe 10 to 15 years timeline? I'm going to give you some perspective or some new directions of the research which we are working on, even maybe we are also working on. Okay, so I'll be talking about not intercalations, but I'll show you some of the things what we do right now. Then we'll go to the other mechanism. So I'm not sure intercalation mechanism can cope up with whatever future demand will be. So then we need to shift that intercalation mechanism to other mechanism. That's the things I'm going to introduce today, and I am working constantly on that. And I believe several talk already we are listening from whole day, or will be listening for next 2 days based on materials. But here I'll give you the top-down approach. What is the requirement of India? I'm talking about only India. I'm not talking about whole world. What is requirement for India from the top level, and then go down to battery, material level, and to the like in a level where we are starting from the materials. But I look at from the in the top, so that what are the things are required for India right now, and then go down and see in the future what will be the requirement. So I am from Department of Engineering, Science and Engineering, which is a not new department, but is this kind of department is not there in any other IIT. So that's the reason. And we do produce BTech in energy science and engineering, energy engineering. That's unique in India. Okay, let's start. This is the slide I always say everywhere I showed. This is my first slide everywhere you can see where we are and what is the demand of India in electric vehicles. So if you look at the electric vehicle demand will be, this is a projection line. So this line, what I am showing here, it is a this line up to this we are here, but due to the pandemic the curve is a little bit different right now. But this is the prediction, this will increase, the demand of vehicles will be increased. And as per the Niti Aayog propositions, will be changing 28 to 30% of vehicles by maybe 2030 need to be replaced by electric vehicles. That's a proposition we have right now. So if you look at the numbers of that 20 or 25, even 25% to 30% vehicles to be converted into electric, the number of batteries are very huge. So if you do a very simple calculations, like you may need around 120 gigawatt hour battery, watt hour of batteries will be required by 2030. So that's a huge number. So how to see what is the number of 120 gigawatt hour? So if you look at the biggest factory in the world in lithium-ion battery factories, 35 gigawatt hour, even not even fully operated. 35 is not operation right now. But if you look at that size, that's the biggest size available in the world right now. And convert into 120, we need 4 types of these type of factories. But if you look at what India right now, we are not even having any small factory, even megawatt level also not there. But the demand is this much. So that means we need to, if you want to keep this trend of this, whatever trend we are observing here, if you want to keep that trend, that means that much battery need to be imported or need to be homegrown, or homegrown factory need to be there so that can produce that one, so that meet the demands. So both possibilities are there, but importing that many batteries, I'm not sure that's a good idea to do it. So that we need to have a huge number of factories with a gigawatt level factories required. At least a few hundred, let's say few 10 times of factories of gigawatt or level factories are required in India by 2030. So I'm not looking at the cost perspective. We know cost is a one factor, but I'm also looking at the human resource. I think when you talk about this human resource from the university perspective, we need to have a trained engineer, because this field is very, very different. It is not only materials. You need to see how the material is packed in a package, and how that materials actually giving the electrons or charge, and how utilize the charge with a better way, like with a better thermal management and better electrical management. All these things together is a battery, is a lithium-ion batteries all together. It's not only the material science or chemistry or electrochemistry, it is everything together. So that's the reason it is very complicated. Looks like it is very simple, but it's very complicated when you go for a system level. So I am sure that we are also taking that as a university perspective. We are also looking at this many number of resource we are producing by 2030. That should be our challenge. Okay, so I'm giving you perspective. What are the things are right now we are having and not we are having. So lithium cell production in India is not there. So I'm not sure when it is going to happen. And the cost of lithium battery is still high, but we are looking for the battery cost should be the pack cost should be 120 by 150 watt per kg. Now cell cost itself 140, not even pack cost. charging infrastructure is not there. So you need to have a charging infrastructure. If you want to cope up with that line I showed you, the slope, if you want to cope up with that, you need to have infrastructure, charging infrastructure. Fast charging is not there. I will be talking about fast charging. Fast charging may not be there right now, but people will look for the fast charging, because nobody interested to wait, let's say hour, 2 hours in the charging station. So that should be another criteria, should be looked at it. And homegrown technology. So that's another things what we are right now. We are here. We have listening talks on all materials, several materials. Even Professor, I think Manthiram also was there. So he was talking about so many materials. But how our own homegrown technology or technology support, when if you have a battery technology or battery production unit in India, who is going to support, which team is going to support the large scale production units if there is any problem. So that is another key factor what people are looking at it right now. So we are again ready to do that. Gigawatt factory, by this time we should have, but pandemic actually shifted this timeline. I'm sure by this 2021 we should have at least few gigawatt of factory in India. So it's still not done. I'm talking about cell. I'm not talking about cell putting into this packing. I'm not talking about packing. I'm talking about the cell manufacturing. Okay, so few players are interested. The problem is, that is a huge, large investment is required, and that's the reason maybe people are not looking at is a prospective or is investment. That's another things. And if you look at that vehicle manufacturer, usually they don't make batteries. So that should be the battery manufacturer, and that they will work with the OEM. So if you think that Tata or Mahindra will be making batteries, I am not sure they will be making batteries. The worldwide, that is not the case. Volkswagen is started, but I don't know how they will do that. Okay, so cost competitiveness and the established manufacturing is the main issue right now in our even whole worldwide. Okay, so I was talking about fast charging capability. When you look at in the perspective of science, fast charging is a difficult thing, because once you charge anything, like you are storing charge or removing charge in a fast scale, the problem is heat generation. So how to manage your heat? The heat management need to be properly done. Once you do this type of activity, forget about battery electrochemistry or battery chemistry, how you are degrading, that is one issue. But how you can make that battery sustainable, like a temperature, independence of temperature, pressure. So that's another thing. So, but in a material science perspective, because I am sure several people are in the material science or chemistry background, or electrochemistry background. So people are working on some of the material perspective, how to do this charge discharge. But again, it is against going towards the solid state diffusion. We know that lithium actually diffuses in the solid state materials. So the diffusion is a main problem. So 15 minutes, if you convert into diffusion, it doesn't match with the solid state diffusion in the electrodes. So it can be done by, if you make a very thin film of battery, like if you're going battery to the capacitor side. So it is possible. It is run the battery at a very fast scale, charging and discharging. But battery is not a capacitor. Capacitor is something for the applications of fast charging, charging or discharging capability. But battery is a bulk. Reaction is a bulk, not an interface. So you need to look at it. So that means your electrode thickness is completely different than the capacitor. So whatever right now people are trying with just thinning the electrode. So your energy density is coming down. Even the another thing is electrolyte. Electrolyte can support that conductivity. It is not. So people are using several type of additive to develop this different type of electrolyte, which are having a higher conductivity, because inside there is two types of like solid diffusion inside electrode, and the liquid diffusion, like a lithium is diffusing in the electrolyte. And that electrolyte need to be very fast movement, like mobility should be high. So there is several strategy people use to do the development. So development of electrolyte is another things when you develop the fast charging capability. Separators need to be different, completely different than what we are using right now. People are working on it. It's not that people are not working on it. Even we are also thinking of that direction. So separator need to be developed for fast charging capability. And cost of cooling is another things. So right now, what we are not looking at in India, so that is here listed here, long range transport. We are not interested. Electric vehicle can be run in a highways, but that is the case for the US. But we are not looking at right now 500, 600 kilometer range in one cycle. But after some time, it may be another requirement for India. and low cost transport. We are not looking at the right now low cost because this is a new technology need to be come in. So we need some time to cope up with that. And high utilization. So transport can be several ways. So how to utilize this everything together so that you can have a high utilization. So this is several aspects need to be looked at it. So if you look at what are the systems we have right now, we have in our hand, several batteries are there that can be used for electric vehicles. As per my opinion, each and every battery can be used for electric vehicles based on our current requirement. Our current requirement is per charge maybe 100 to 120 kilometer in a city, and city will be only used for electric vehicles mainly right now. So in that case, if you see this is the plot where you can see most of the electrochemical system which is capable to do that. But if you want to see the best one is obviously lithium ion. If you see, there's a few criteria are need to look at it. We always look at energy density, power density, but apart from that, several other things are also required for electric vehicle charge storage. Let's say power grid compatibility, how good compatible with the systems, how operating temperature can be sustained, that battery can be sustained, because our temperature is climate, our climate is like a tropical climate, which is totally different than other part of the world. So this need to be look at it, which system is good. So in that sense, some of the systems are very good, some of the system may not good, but still you cannot remove them. So as per my opinion, most of the battery is actually suitable for our conditions and use it with a proper thermal management. The best one, if you look at it, obviously lithium, and that's the reason I say that lithium cannot be ignored anytime for the electric vehicle problem. This is another thing. So if you look at the range wise, range anxiety, if you are not there, if you look at you're restricted 200, most of the battery systems are fine, even lead acid also fine. And if you look for beyond that, then some of the battery system actually comes up, and then lithium ion battery can actually over exceeding for anyone. This is another plot I was trying to for small vehicle and the large vehicle. I'll come to it what type of vehicles we are interested. So I'll do it a little bit first. There is one example. Everybody say that lithium may not be a problem. I feel lithium is not the problem. The problem is somewhere else. So if you look at the two type of vehicles, which is small vehicles and the large vehicles, the small is let's say small is Nissan Leaf, which is a very small vehicle compared to the Tesla models, where the battery size is like very small, and then a need of lithium is like a 4 kg per these vehicles. Whereas the Tesla motors, you have the large scale batteries required, 14 kgs of lithium is required. So if you look at the current reserve of lithium, if you can see how many numbers of vehicles can be produced, which is much more than what the predicted, how many vehicles will be electrified, much more than whatever prediction is there. The problem is other thing, it's not the lithium is the problem. Problem is challenges is for the large vehicles, where you see the Tesla car, the weight of the car and the battery weight is the major weight from any car. So when you go for increasing the range or increasing the size of the vehicles, immediately battery is a problem. And even still lithium ion battery is a problem, is a weight wise. That means you need to have more energy dense battery, like a 200 is right now, 220 is the right now battery is 250, 300. If you get this weight is coming down, so maybe 24% is right now, it can come down to 17 to 15%, which is good. So your car is very efficient without battery, but when you put the battery is less efficient because of the weight problems. Other thing is main problem which India is going to face, which is cost. Right now, if you look at the very small cost wise 150 per cost wise, if you look at it, 150, which is not even used for electric vehicles batteries. But even lower cost, if you take this in the pack wise, in this much watt hour per kg of battery, you need to have very high number of amount of investment is required. So that's the reason maybe India need to go for a smaller car where the investment is less for the battery and it is more efficient compared to the large car. And that's the tradition is going on right now. So if you look at whoever researcher, lithium may not be a problem. Problem is the cobalt or nickel, not lithium. And another problem is energy density and power density. Energy density for the car is gravimetric energy density. I think more in volumetric energy density. Both are important. So I'm going to shift right now because this is the starting from the innovation of lithium-ion battery, then gone to the right now. We are here where you are using carbon graphite as anode, and then cathode is 4 cathodes are there. But you can see the literature. I think you can find several numbers of different type of cathode people have done, but industry doesn't believe on that. So they are using only 3 types or 4 types of major candidate as a cathode. and they combine this every cathode and then get, but anode is same. So this is the generation. It is starting from 1990 and then still it's going on. This is the currently we are using, starting from mobile to the car. This is the combinations of our batteries. Okay, and the battery is safe, not completely safe. So I have marked something is here, which is my going to talk about it. But I'm talking here, this is the things which where the mechanism is, till the mechanism is intercalations. So beyond this, maybe up to this, our applications are okay, still there. But think about beyond the 10 years timeline, 20 years timeline. Can you cope up with this type of energy density and have our future applications? It may not be. So that's why you need to have a shift. That should be a paradigm shift, how the mechanism is going to shift from the intercalation to other process. I'll remove this, what I have marked here, in the next few slides. I'll talk about my group, what I am doing. I'll give you some examples what I'm doing, but this is the things I am working right now in my group: capacity, safety, fast charging. I am not started doing, but I'll be doing the electrolyte part and the sustainability. If you look at the choice of the elements, I'm taking it. This is the three main aspects right now. I am working on lithium-ion battery. I am the worker. I believe fully on lithium-ion battery, and that's my career started with lithium. Still, I am the lithium, and to whole life I'll be doing lithium-ion battery. Apart from lithium, if I look at any other elements, that should be sodium and silicon. So these two are my combination right now. One is cathode, one is anode, and the other cathode we are working on sulfur. I'll be talking about sulfur battery. That's a change of the mechanism. And then manganese, manganese based, like a cobalt free, or cobalt may not be free, but manganese rich elements of cathode. I think Professor Mantiram was talking about some of it. I'm not listened today, but he could have been talked about manganese rich composition as a cathode. So this is another things I am looking at it. This is the full combination. We are doing it for the current in the research perspective. And also we are working on electrolyte, which is ionic liquid based electrolyte. Let's start. And this is the lab things what we have right now. Few targets, few projects right now we are working on. We are working on long cycle life battery. So currently cycle life is around 2000 to 2500, even lab scale to the R&D scale, and even factory scale. So we are looking for, let's say, 10,000 cycle life can be possible. So Toshiba is having some batteries which is having 15,000 to 25,000 cycle life. So we are targeting some of the composition of lithium battery can go to that cycle life. Also, our target is 300 watt per kg in the commercial chemistry that we are targeting for a large scale. Also, we are working on the sodium-ion battery and lithium sulfur. Right now, fully concentrated on lithium sulfur and sodium sulfur, room temperature sodium sulfur. And we do some of the prototype. Most of the things, it comes in a smaller scale successful. We translate to the prototype and see how good they are. So we have a capability to produce some cells, lithium and sodium, at least in this scale. And we are establishing for lithium sulfur in a pouch level. Okay, this is the open now. Last one I opened. If you look at it, people are converting this carbon to silicon. Silicon carbon composite is one of the things is going on. But again, 5% silicon is used, which is not much improvement compared to the graphite. So this is another area people are working on in even commercial scale. But as per my third generation, maybe the solid state, people are talking about solid state. I'll give you after end of the end of slides, I'll show you our batteries, how safe they are in the even compared to the solid state battery in a when during slicing. I'll show you, which is liquid based electrolyte. So I believe before these, maybe the whole world is working on solid electrolyte, solid state batteries. I am also working on, but I believe before this lithium sulfur, sodium sulfur will come to the picture in the commercial level. So I'll be talking about these technologies. Let's start with the understanding of sulfur battery, how the sulfur battery started, and then now it is taking to the whole world, is reviving the whole world. So if you look at the first generation of sulfur battery, which is high temperature, and the battery concept was completely different there. Here electrodes are melting form, electrolyte is solid. So that's a difference. But if you look at right now, we have converted these two, electrode is solid and electrolyte is liquid. That's the difference we have done. So Okay, so anode was the liquid molten sodium, and cathode was molten sulfur, and electrolyte is solid state electrolyte, which is beta alumina. Why it was happened this way? This configuration was taken. This is very successful because if you look at the phase diagram, and they have very judiciously selected the composition where they can extract around 400 or 500 capacity out of the sulfur batteries, but the both phase, the reactive and the reactant and the product phase are in the liquid phase in that temperature. So they have to work on not above of 300. If you go to that, so go to that is around 300 or 350 degrees centigrade. Both the reactant phase are in a liquid phase. But if you go extract more sodium out of it or capacity out of it, you are shifting from the other zone where like a solid state comes. So that is the transition from liquid state to solid state. So they have restricted the reactant and product in liquid state, and extracting only the let's say 67% theoretically, but it is around 63% they are extracting, and that all phases are liquid. So liquid transition is much more feasible compared to the solid liquid transitions, solid to liquid transitions. And this is the brainstorm where this battery works and why it works. And right now, this battery is a high temperature battery. We are not interested in high temperature battery. What we are interested in, we are interested in this technology or this understanding should work in room temperature. How they do that? Instead of liquid metal, you just put into the, if you want to work on the room temperature below this, everything this will be solidified. The sulfur will be solid, sodium will be solid, and then electrolyte need to be in the liquid state. That's a strategy is going on. So we just invert this and come to a solid state battery. So let's start understanding of solid state batteries, solid state metal sulfur batteries. We have a sulfur particle which is not much electronically active, conductive. So what we have to do, we have to have a conducting network to support that, and then we need to have binder to bind all the particles, and then make it as electrodes. So this is the sulfur electrodes. Because we are dealing with sulfur particles in a micron size, then we need to have a very good coating of conducting carbon, so that the electron percolation network is good. Then that all particles need to be come together in a bind form. So that's the reason we need to have a binder. And then everything is merged in a electrolyte. Electrolyte is the diether. I'll talk about why this ether-based electrolyte is used compared to other electrolyte. And then anode can be sodium, can be lithium. This is the structure. But the main things comes in a interesting part comes in a reaction mechanism. Here the reaction is not the reaction of what we have seen in the lithium battery, is a intercalation reaction. So lithium goes in and sit in the open structure and comes out. Here the lithium or sodium is reacting with the cathode as a chemical reaction and then forming a product. Okay, so this is a completely different reaction mechanism. So here I'm giving you one example of how sulfur reacts as when you do a reactions in a series. You see, starts from here when you combine a sulfur and the cell and start doing cycling. You start from here. The first peak will get in the reduction scale, which is actually sulfur is converting to different polysulfide. It's called polysulfide, is combining with different sodium or lithium. Here I'm giving you an example of sodium, but it can be a lithium also. It's a similar mechanism. We believe, okay. And then it's going to the lower polysulfides, lower polysulfide to higher polysulfides, and then it forms Na2S. And when you reverse the reactions, you see again it is coming back. The sulfur is going to be free. So that's a complete reaction. So if you look at it in a more complicated way, what is happening in this, sulfur is almost neutral substance. How then is polysulfide forms? When this sulfur is actually come in contact with the solutions or electrolyte, the sulfur solid state goes to the first liquid state. So that means sulfur solid need to be dissolved in the liquid electrolyte. And if you look at the solubility of sulfur, soluble, I have written down here, sulfur is insoluble completely in water. So, and sulfur is sparingly soluble in alcohols and not even soluble in the ECPC, what is electrolyte used for lithium-ion battery or sodium-ion battery, that type of ether-based solvents. And it is very good soluble in the carbon disulfide and soluble in benzene and toluene. If you are in a battery scientist, I am sure you know that carbon disulfide and the benzene and toluene cannot be electrolyte compositions. cannot be a solvent. Okay, so that means we need to look for some solvent which is sparingly soluble this sulfur, and then sulfur is this, because you start, if you want to start this reaction, sulfur need to be in the liquid state, otherwise there is no reactions happening. So the solubility is the main problem, and that's the reason we are using ether-based solvent. If you look at the ether-based solvent, sulfur is sparingly soluble, and the strategy people use it, they use very high amount of electrolyte to solubilize whatever sulfur is there. And another strategy, utilizing very high electrolyte, amount of electrolyte. Other strategy, reduce the sulfur content. So if you have a less sulfur content, because of very less solubility, less sulfur is good for a whole huge number of electrolyte. Okay, that's the strategy people use for a small scale. But when you go for a large scale, for a production or prototyping, that may not be the strategy. You have to have more than 60% of sulfur, and then electrolyte can be reduced, because energy density depends on overall weight of your battery. So that's the main problem when you go for a large scale battery productions. Once that is in liquid state, then disproportional state reactions happens, and because this reaction is electrochemical reaction. Other side, lithium or sodium is oxidizing and coming and combining with all these species which is formed in all short-lived species. All are polysulfides like S8, S6, S4, S2, S, and then combining each other and then storing the charge. That's the way it works. And if you look at the plot, you can see several plateaus we'll see, and that depends which one is trapped by the metal cation, which is coming from the other side, anode side. And end product is Li2S or sodium Na2S, and that's the end product. And there is a transition here. You can see up to this is liquid. After that is a solid state transition happens, and the reaction is sluggish, because there is several things happening, several steps are happening. Electron transfer, several electron transfer. If you look at it, several electron transfer happens, and that's why this reaction is very sluggish. So two rate determining factor here. One is this liquid solids to liquid. This is the one rate determining step, and other rate determining step is this, how the polysulfide is quickly transferred to the lower to higher polysulfides. That's a main strategy. So here I'll give you understanding of the sulfur, how people utilize the sulfur in a good scale. So look at this. When you start sulfur, it is a zero state, so we need to discharge it. So add more and more lithium or sodium. So first the sulfur, I said that sulfur need to be dissolved in liquid, and then open up the cage and then start reacting with metal atom in two terminals in the linear scale, and it start adding. So up to what scale you start adding, you can go ahead up to add all the things and then come to the final product. But if you look at it here, up to this Li2S4, these compositions are soluble in the electrolyte, because sulfur, if you want to react, sulfur need to be solubilized in electrolyte, then reaction starts. And the reaction product, if you look at the strategy of liquid the high temperature sulfur batteries, their reactant and product both are soluble in the same state. So if you want to make the battery kinetically feasible and high charge and high discharge rate possible, then all your product and reactant should be in the same state, like liquid state. So if you operate up to 400 capacity, these all combinations are in the same state, liquid state. So this is soluble in electrolyte. Okay. So some of the strategy people use it. So they trap the sulfur to such that it never go to the S2 other combinations. So that you can restrict this. So there is some strategy, but I don't believe. So you can have a trap in a very small scale so that more sulfur cannot be added or more lithium cannot be added. Size trapping is there. So if you can trap so that easily, very highly reversible way, because there is no phase change happening, like a solid liquid solid transition is not happening. So now you can have which battery which is very kinetically favorable. So, but if you are interested to extract more and more energy out of it, you need to go so that there will be a phase transition. So liquid is going to transfer to the solid state, and then there is a problem. So once it is transferred, then the reaction is very sluggish. So we need to work on this. So I talked about two things. One is sulfur to solid to liquid, that is a rate determining step. Other rate determining step is here. So if you want to utilize that 1600, even 1000 capacity, you need to have this transition happens, and you need to tackle these two transitions. So people are doing it. several way. So look at in a little different perspective, that what are the difficulties we'll feel when you make these things in a scale. Sulfur, this is a particle in an electrode, this will look like this. When you will have a discharge, so lithium or sodium is added, so physically you will have a volume expansion. If volume expansion happen, what happened? The conductive additive what we used, which is closely packed and electron percolation was good, so once it is stretched, this is very prominent for alloy based reaction like silicon. Why silicon needs a huge number of conductive additive? Because of these reasons. If you expand the, let's say the silicon or sulfur is expanding, and then these carbon particles are get separated each other, so there will be again the problem because of separations, the electron percolation is restricted somewhere. Okay, so we'll have a less utilization. That's the reason we use like alloy reactions. Sulfur also need very high amount of conductive additive because of these reasons. Other thing people had not maybe looked at it. If you see the binder used, due to expansions, the elasticity of binder is very important because it's need to be expanded in the similar way as it's expanded. And then when it's quenched, when it is a discharge reaction, again the lithium or sodium is coming out, this particle again quenched. And that polymer has to have a synchronized with the same time scale, it comes down. So that elasticity and their response time of the polymer should be same as what way you charge or discharge your particle. So which time scale you are operating. If that is a mismatch, there will be a problem. So you need to be keeping in the mind. Okay, so this usually this is as 1.3 to 1.5 times of dimension changes based on sodium and lithium. That's the reason I put X. Another problem is polysulfide. This is the problem I already talked about it. Polysulfide, once you start making the reactions, the polysulfide is soluble in the electrolyte. And some people think that, okay, polysulfide is soluble, so I will change the electrolyte so that I will make it insoluble and it will not work. So one thing is like a solid electrolyte. I am not sure how solid electrolyte will work because that fundamental crack I have, that I am not sure how the solid electrolyte will work. If this is not soluble in the solid electrolyte, how this will reaction process. So this a problem is this polysulfide is soluble in electrolyte, and that solubility, because every time we are losing the polysulfide. So one way to this, whatever polysulfide is happening, that need to be trapped in the electrode structure itself. Don't allow him to go to the electrolyte. And electrolyte is anyway accessible in the electrode itself because of electrode liquid dispersion. Again, the polymer problem also comes here. Okay, this is another problem. So there is a several strategy. People use different type of carbon or different type of absorber that absorb this polysulfide and keep it in the electrode structure, not allowing to go other places. Polysulfide shuttling is another problem. Polysulfide goes from cathode side to anode side and then stay there and forms an insulating layer, and the reaction propagates. So we always try to make the electrode everything in a electrode structure, cathode itself, so that our polysulfide doesn't go other places. Okay, so that's a polysulfide I talked about, subtle mechanism. Because of concentration difference, the polysulfide goes and stick on the anode, and then reaction ceased after some time. So the strategies are several types of, if you look at the literature, several types of strategies are there, and the strategies are there, and mostly there is a different type of carbon, cage carbon, different type of additives people use, and this is a listed of all the things. So we also use some of the additives, but we found some of the additives are very, very different than other additives, and that's the reason we are working on. But the problem is additive, carbon structure, everything is good because these are not active in the electrochemical reaction. So that when you talk about energy density, anything extra which is inactive in the electrochemical reactions, it is actually contributing the weight. So we need to decrease that weight. So when you talk about small scale, right, publishing some papers, it is fine. But when you talk about in a real scale device, I think these all are problem for the device level applications. So any exotic structure, any exotic carbons, it is okay for a small scale, but large scale is may not be the solution. Okay, so we work on the different carbon composite. We also work on carbon composite, but we want to go for any very different type of structure and different type of morphology, and just simple things. We make a composites and then see how much sulfur content I can make it, and then I can use it. Very simple. And sulfur, you are not using nano sulfur, you are using micron level sulfur. Sulfur is another things we started. I think there is a lot of news out there. You can see sulfur organic. So sulfur can be free. Sulfur can be embedded on the organic polymer backbone. and that whole polymer backbone can be used as a sulfur cathode. That's another strategy we started along with SNU, Shivnadar University, along with their expertise in organic chemistry. We are using that, and the results are very interesting. And hybrid electrostructure. So hybrid electrostructure also, we look at the binder, how the binder can synergistic effect with the polysulfide absorption along with the additives. So several additives, metal oxide additives, as we are also using. And another things, we already seen that when the sulfur is in liquid state, the kinetic enhancement is there. So one of the group, I think we are the one believer that sulfur can be put in the liquid based, and that liquid based sulfur, like some polysulfides, can be used as a starting materials to start, and the kinetics can be improved further if I have a control amount of catholyte used in the sulfur cathodes. And that's another strategy we are studying right now in both lithium sulfur and sodium sulfur. This is one example I'm giving you. We all interested on sulfur because of the capacity, but we never look at it. Sulfur is a highly inflammable because it catches fire immediately. Sulfur is well known for catching fire. So if you think about it, sulfur you are using for energy enhancement, energy density enhancement, but the sulfur is again problem. If the battery catches fire, sulfur is the first one to catch fire. So here we are taking a strategy. If I put a sulfur with a copolymer, where copolymer actually is a fire resistance. Okay, so this is the strategy we had. So we chosen the copolymer which is not fire catcher, it is actually returned into the fire. So that way you can do the, in this work we have actually started doing this work and then understood when I replace at least 90% of copolymer, which is here is given one of the first person based copolymer, which is highly resistant to the fire. It cannot catch fire anyway, it will not burn. But the problem is sulfur content is very less, like a 10% sulfur, which is may not be the good way to start with the batteries. So we have gone through the several alterations and find out a good sulfur to the copolymer ratio where both the properties are intact. We need to utilize higher amount of like a 40% of the sulfur, 45 we have done, 45%, and we need to also keep our fire retardant polymer properties in the polymer. So that we selected that. Please look at this this journal, it is published last year. And then we see that we cannot compromise also in the what capacity we are going to get. So we have done that work, and then we have shown that this polymer, if I go with these compositions, it is not catching fire. So the more details are there in this journals. It is published last year. You can look at it. And we have seen even utilizing with that copolymer, it is not changing. The main things what actually making me more concerned that how this reaction mechanism is there, because sulfur copolymer, sulfur, once the sulfur start reacting, sulfur is going to come out from the structure, again is going back or not. So this reaction mechanism need to look at it more details, which is that is our next strategy to start. We have several papers along with this group with the different aspects of copolymer utilizations, and all are successful in the battery performance, but understanding purpose we are still in the wondering, and still that is actually disturbing me how this works. That is more concern right now. Okay, so another things we already talked about that the sulfur can be trapped by several strategies. We also, you can look at all the papers what we have published till now, all having different strategies. So here another thing is that metal need to be protected, because metal, once you use the lithium or sodium as a anode, then the problem is the dendrites. So I may have another 8 minutes, no? Another 8 to 10 minutes?
You can take your time, no problem, sir.
Okay.
No problem.
Thank you. Okay, so metal dendrite formation is very well known for lithium and sodium cases. So you may have a better sulfur cathode, but sulfur cathode, several strategies can be used. But metal is metal, so you are not protecting. You need to have protection. Here, what we have done, if you look at the literature, metal protections, at least lithium metal batteries, several protection techniques people use. Some people use solid electrolyte interface. Some people use a separator interface. Some people use ionic liquid as a prohibitor. And here, lithium. When you look at the lithium nitride formation on the lithium metal is one of the good strategy. I feel that's the best strategy for metal dendrite preventions. Okay, and now metal nitride is a good. The main thing is metal nitride, whatever you put it as a protector, that need to be very good ionic conductor, lithium metal conductor, as well as you need to diffuse the lithium very fast, because the lithium has to diffuse to the and then work. And also same time it is reduces the metal depositions like a dendrite formation. And after several literature surveys, a vigorous little survey, we found that lithium nitride is a good strategy. And several way people make the lithium nitride. So we have taken a different route. I will not discuss because this is just submitted for patent as well as in the publications. So we have made this nickel nitride very simple way to make this nickel and very control way. We can have a full control over what is the thickness we are putting it. And what we have seen, this is some of the things we can see here. This we have cycled in the symmetric scale, both are lithium, and see it is there is no change because lithium, and after cycling 300 cycles we have taken a AFM. This is AFM. If I don't do any metal protections, you see there is a spikes formation. That's a dendrites. Okay, after 300 cycles. So similar when you use the lithium nitride using our process, and you can see the surface is lithium depositions happening, but in the rough scale, not this scale. Okay, so the roughness is not created, or dendrite is not created, which is a semi-smooth on the atomic level itself. And that shows in a different results. When you do this like a metal like a symmetric cell applications, you can see there is no much difference in the potential as well as in current. This is another thing. Even if we increase the current rate, we have not seen much difference. That means lithium depositions is not in a dendritic form, it is a uniform form. So similar things, so the same process we have used for two different purposes. One is with a high rate performant electrode like a LFP and LTO, that is not shown here. But we also shown with the lithium sulfur battery, where you can see because of lithium nitride interface, your polarization also came down drastically, like a 0.7 volt, 0.07 volt this difference we have observed in the polarizations. Also the cycle life also showed that it can run 1,000 cycles. Here also you opened and you have seen there is no dendrite. So this is another very interesting what we are actually taking this up for a large scale pouch formations. This is one of the strategy we are trying to utilize for pouch cell productions in the lithium protections, along with our different strategies. Okay, so I cannot talk more on that because this is under things. And these are things you can see after uniform lithium depositions, after cycle, you can see there is no dendrite. So this is another interesting things that we may have observations of polysulfides, but there is no dendrites. Okay, so few things we do, we can have a look at it, our literature. So we do a lot of additive studies, but we found one of the additives which is very interesting, which is aluminum oxyhydroxide. And we have given these interactions of polysulfide with aluminum oxyhydroxide is a Lewis base acid. This is also published in Advanced Functional Materials. And this is very interesting. Why I'm saying it? Because people have used several metal oxides. We also have several metal oxides. But this one is interesting because I can reduce this aluminum oxyhydroxide to drastically very low amount. Here we are utilized 5 to 1. Even you can go below down and still that interaction is there. And then we have proved that interaction by several ways. You can see that sulfur XPS 2P and aluminum also you can see there is interaction. Two type of environment. One is interacted with sulfur, other one is not. So and so we have gone to the DFT and see how this aluminum oxyhydroxide is actually absorbing this different polysulfide and their binding energy. And we have seen once you are this is a negative energy. So once you are like S8, we have seen that several. This is the geometry how S8, S4, S6 or S2 are working with the sodium, and their binding energies are calculated. So once you start with S8, you see binding energy is going to reduce. So that means once it is absorbed, so very difficult that to go out and that form transport to the to lower polysulfide. So that's another interesting. And we have changed this this aluminum oxyhydroxides to a very slow amount, and see still these are very good. Even sulfur battery, this is sodium sulfur I'm showing you. Sodium sulfide once is very rare, you can see that. Even this is run at minus 10 degrees centigrade, this battery is working. That paper is also under review right now. We have shown the first time in the world that low temperature sodium sulfur battery is also possible. Okay, so this is another mechanism we are introduced here. So I'll go talk about very small things. What we have done, we have changed the current collector. We have corroded the current collector so that we introduce several functionalities on this. So functionalities is introduced because we want to have increase the dangling bond, where dangling bond also having a free radical. So we want to use this free radical of carbon, this carbon fiber, which is act as a current collector, and the carbon, the free radical introduced by the sulfur from the Na2, say sulfur 6, N6, these two can be coupled together. So here what we are doing, we are utilizing the coupling between free radical to coupling of free radicals and enhancing the performance. So this is also published, and this is the new observation, so that we are giving a free radical mechanism, catalyst mechanism in the sulfur batteries. And you can look at it, this is a full things are there. Why we are gone to that mechanism? Because of this peak. So if you look at it, this peak is very rare to the sodium sulfur battery. So this peak, if you people, most of the people have this peak and this plateau and this plateau. So when you have this carbon fiber which is corroded with a very good extent, we have seen that this peak enhances, and that's the reason our utilization is higher, our discharge capacity is higher. This is the middle peak, which is, and this peak actually brings us the new knowledge and new pathways of the mechanism, and that's why we are introduced this free radical mechanism, just to introduce once you observe this peak, which is not there in any literature. Some literature you can see, but they didn't discuss about it, and we take it as our understanding, and then we saw that this is a one new way it is coming up. Okay, so here we showed that this free radical is actually combining with the free radical coming from the carbon fiber due to dangling bond, and we have given several, and see the charge discharge are everything is same, and this is the thing. So what I'm talking about, the sulfur, this sulfide free radical is coupling with the free radical from the current collector, and then that coupling actually enhancing the polysulfide absorption, and then it is reacting. So that's the reason we enhance the kinetics as well as enhance the discharge capacity, like a capacity contributions. We have utilized several experimentation to prove that that free radical is there, is forming in that time scale, and then coupling it. So that we have done several experiments to give it. And this is EPR, where also we found that the carbon cloth having the free radicals. Similarly, we can see the sulfur also having the polysulfide having free radicals. So what we have given, this free radical and this free radical is coupling, and then that's the reason this is absorbing better compared to the, if you are not, current collector is not corroded much. Okay, so several things we have done, you can look at it. Okay, so few things, I have not gone through the whole literature of what we have done. We have done several things in sulfur batteries right now. But right now our interest is to have this understanding put into the large scale, not in a coin cell. So we are right now we are going for a pouch cell of work of the sulfur batteries, and we observed that low sulfur is the, everybody is playing with the low sulfur. I already talked about it, why they use low sulfur and high electrolyte amount, and both are actually a killing factor when you go for a device. So when you go for a device, this need to be looked at it. So right now our sulfur loading is 6.8 milligram per centimeter square, which is very high amount. If you want to achieve 500 watt per kg, you need to have around 6.5. So 7.5, we are already in the 6.8. Some of the literature we have 6.8. Electrolyte, you are using 4 microliter per mg. So right now we are in a pouch level. And if you are working on this field, please look at this. Its publication is one thing, but publication should be translated to TRL level. So always look at this. You need to have a high sulfur utilizations, high sulfur content, whatever electrode you're using, and electrolyte should be as low as possible. Is 10 to 15, 20, below 20 is good, but try to reduce as much as possible. Anode protection, another strategy is open up your whole gimmick, like your research field, and optimization of composition. The electrolyte people are not looked at it. We are also started looking at it. Okay, so electric vehicles, I think whole seminar is on electric vehicles. We are interested in electric vehicles because to reduce the carbon dioxide. If you look at it, where you can reduce, carbon dioxide is reduced when it is in operation, but still there is one problem. Charging the battery needs to have electricity. So electricity, if is coming from coal-based power plant, then this purpose of carbon dioxide emission problem is still there. So we need to have more and more reliability, more and more connections with the renewables. If you look at the renewable strategy at the March 2020, we are not in a very good position of renewable power generation, and that power generation should be utilized, and that numbers is increasing. Anyway, the government having that increasing the number of renewable energy. But as per my opinion, this renewable should be used for electric vehicle battery charging, not for, we should not take any electricity from power-based or thermal power plant and use it. So that case, carbon dioxide emission problem will be there, and that will not be, that is not our strategy to do it. So this is the same thing I said, that few things need to be looked at it. If you look at the battery electrochemical power system, it started with 30-40 like lead acid battery. Right now we are 220 watt per kg. So that means if you look at it, how much change we have happened and what is the factor of change and what is the timeline you used. So it is like a 4 times of energy density increased by 200 years of timeline of research. And right now lithium battery is looking for energy density, let's say 3 to 4 times. The timeline is 5 years, 6 years. So you think about it, what are the effort of human beings, effort of money, effort of talent, everything is required, which is huge numbers. So which cannot be done in 200 years, you have to do in 10 years timeline. So that is another things we should keep in mind. Okay, so that's the last thing I talk about it. We have a startup which talks about dendrite-free batteries. We are using liquid electrolyte. I'll give you an example today. Show you that our liquid electrolyte also doesn't catch fire when you slice it compared to the solid state battery, which is made a huge vibe in the world. But I'll show you liquid electrolyte, they're not catching fire. Okay, so when you cut it in a similar way. Okay, so here we have done a startup. This startup is right now in a pre-commercial level, production of cells and production level cell of productions. So we'll be interested of, I'll talk about maybe one, yeah, this will give you the full.
Technology has been in talks in recent years, mostly for safety concerns. Despite the explosions happening of cell phones, passenger aircraft, electric vehicles, and hoverboards that are in serious discussion, lithium-ion batteries remain the go-to energy storage technology for EVs, and about 80% of newly announced energy storage projects worldwide. Virya Batteries, a startup from IIT Bombay, provides an innovative offering of lithium-ion batteries designed around safety and longevity. Work based on cell structure and innovative materials, which makes the battery's internal reaction mechanism free of dendrites during cycling, thus making the battery even more safer and longer life. This lithium-ion battery is a dream project of Virya and could be the first technologically self-reliant commercial lithium cells manufacturing company in India.
Okay, give me. This is one which is shown in the. This is taken from YouTube. Everyone, you see that this is a solid state battery, and they put in the power. I just forward it. You have seen this. So once it is in the load, they put in the load, and they are cutting the batteries. Okay, so cutting the battery, and there is no explosion. That is a huge hype that cutting the battery solid state can be possible. I'll show you the same battery, our batteries, without solid state. This is a liquid state battery, but a similar thing. There is no problem with our case. We have put a load. This is a full charge. We have done this after 500 cycles of this battery. We are cutting it. This is a liquid state battery. It's not catching fire. I think solid state battery should look at it. Thank you. Thank you very much. If any questions, anything arises, please let me know. I can.
Very interesting. It does not catch fire, huh?
So with the first time I'm showing to the audience. Okay.
Oh my God. Very impressive, actually. I could imagine. This may be a message for the most solicited people, actually. I don't know. Now, maybe.
No, my group also we do solid state, but I won't discourage. But the main problem for the fire is the dendrites. So once you have a short circuit because of dendrites, or there is several other reasons are there. But one of the dendrites we are dendrite free. That's why it's not catching fire. And this battery was discharged for 500 cycles. After that, we are taking this full charge condition. Similar like what solid state has done.
Okay. No, I was imagining that the old technology was based on solid state. After seeing your lecture. No, everyone
that's why I said that this is not solid state, this is liquid state.
No, everyone was saying what the next technology will be the solid state only.
Yeah, I won't say that.
Okay, very good, actually. There are some questions. The sulfur battery pouch cell, what will happen after this 70 cycles or 100 cycles? Someone posted.
What will happen means?
Is the stability will be better, cycling stability after 100 cycles?
Yeah, we are targeting. You see, if you look at the few startups, and I think 2-3 startups are there, the data already there. They are struggling up to 800 cycles. After 800, there is a problem.
Okay.
Because of the protection may not work. But we are on the cell design side right now. We are not gone to the capability of cycling how many, but we are targeted of above 500.
Okay, good. That's a very good cycle. And someone has asked which separator you used for lithium sulfur and sodium sulfur battery.
I cannot say.
Okay. So then one more question is lithium aluminum LiAl to the cathode. What is the role of LiAl to the cathode there as well?
Okay, LiAl2.
LiAlO2.
Yeah.
The cathode. Slide number 19.
Yeah, aluminum oxyhydroxide is a additive. People use metal oxide. We are using metal oxyhydroxide. Because of we want to use that aluminum Lewis acid property, and sulfur negative. When you use polysulfide is a Lewis base. So we want to utilize that Lewis acid base concept, and we see that it is happening. So, and as per my opinion, what we have done, we have found only manganese dioxide and this aluminum oxyhydroxide is a good additive for a sulfur batteries. And right now we are optimizing the amount, because we should not have more amount of additive and then electrostructure, because these all are inactive in terms of electrochemistry, and more
additive will decrease the performance.
Not performance, it will decrease the energy density of the battery.
Yeah.
Have always less amount. We can get the performance out. So that's a control things is going on right now.
Yeah, very good, very impressive work.
Several things are there. We are not because my whole lab is on the batteries, so several batteries are there. But I thought maybe this is the one we should give it to.
Okay, very impressive work. Thank you very much, and thank you. The audience will get benefited, and now there will be this session has ended now, and I request everyone to connect with you for the next section at 1:30 p.m. So there is a lunch break now. So please connect at 1:30 p.m. Join us. Thank you. Thanks the session chair and co-chair also. And Professor Sagar Mitra, I'm very much thankful for you, in spite of your busy schedule, for accepting the talk. Thank you.
No, thank you very much.
Thank you, sir.
Thank you.
You can end up the meeting.
No. It's thank you, Ashok Kumar. Just ask them. Prakash.
Yes, sir. Hello.
Prakash.
Yes, yes.
Hello.
Tell me, sir.
My name is Jinu Lee.
மியூட் பண்ண சொல்லலாம் ஒரு நிமிஷம் மியூட் பண்ண சொல்லலாம். ஹலோ பிரகாஷ். ஹலோ சார்.
Hello.
Hello.
Yeah, how's it going?
Yeah, good.
Yeah, thank you for kind invitation to this great seminar.
Yeah. Thank you.
Yeah.
So what is the time now there?
So now 4:40. So we have the 20 more minutes, right?
Yeah. Thanks for coming early.
Yeah, it's great. So so in the morning I also attended the Professor Martin's talk.
Yeah, I saw. Okay.
Yeah. So anyway, I'm very sorry that I cannot visit your place these days.
No, I asked for extension actually. Maybe you'll look for it. And I asked for extension, and I also asked for some doing online course, something like for some for material characterization, some online course just for 8 lectures or something we can do together or something. So that and I tried to send my student also.
Oh,
Maybe next
Professor,
month.
sorry. So I will be back in 10 minutes. So I need to go to the restroom. So I'll be back in 10 minutes.
Oh yeah. Okay. Thank you. பிரகாஷ் ஒரு 10 மினிட்ஸ்ல பண்ணிடலாம்.
What, sir?
ஒரு 10 மினிட்ஸ்ல பண்ணிடலாம். ஒரு குமரன் வர சொல்லு. எல்லாமே இருக்கா உங்ககிட்ட? எல்லாமே இருக்கா?
Yes, sir. Tomorrow only start, I think.
ஓகே ஓகே ஓகே
First part Kumran, second part me.
ஓகே ஓகே கூப்பிட்டு பேசுறேன். அவர்கிட்ட இருக்கா எல்லாமே இருக்கான் பாரு, கண்டென்ட் இருக்கான்னு பாரு.
Okay. Okay, sir.
ம்.
I will call him.
ஓகே.
Hello, Prakash. Hello, Prakash.
குமரன் சொல்லுங்க.
Okay, Prakash, just I want to check. Prakash இருக்கறா இல்லையா?
இல்ல இப்பதான் வந்துட்டு போனாரு. அந்த இங்க பேக்ரவுண்ட் சேஞ்ச் பண்ணுங்க உங்களுக்கு. பேக்ரவுண்ட் சேஞ்ச் பண்ணுங்கண்ணா.
அது வேண்டாம் விடுங்க, அது எனக்கு தெரியாது. I don't know how to do it.
ஹலோ.
இல்ல அது எனக்கு தெரியாது எப்படி பண்றது.
இல்லையா ஸ்டூடெண்ட் அனுப்புறேன் இருப்போம். எங்க இருக்க?
வேண்டாம் வந்தாங்க உங்க ஸ்டூடெண்ட். பரவாயில்ல விடுங்க, ஒன்னும் நோ இஷ்யூ.
ஓகே ஓகே.
பட் வேண்டாம்னு நினைக்கிறேன். அப்படியா? சரி ஓகே. எனக்கு தெரியல எப்படி பண்றாங்கன்னு. இதுங்களா? இது பாருங்க, இந்த இது 2 மீல் வந்தது. இது ப்ராபப்ளி இதுன்னு நினைக்கிறேன். பாருங்க. டவுன்லோட் பண்ணிட்டு
டெஸ்க்டாப்ல போட்டு இல்லை எங்கே இருக்குன்னு தெரிஞ்சுச்சுன்னா அப்படியே
ஓகே, டெஸ்க்டாப்லேயே வைங்க, நோ இஷ்யூஸ். சேவ் ஃபோல்டர். வந்துருச்சுன்னு நினைக்கிறேன். சூஸ் விர்ச்சுவல் பேக்ரவுண்ட். ஆடு கொடுக்குங்களா? ஓகே, இங்கே இருக்கு. ஓகே. அப்புறம் இது ஓகே, சரி க்ளோஸ் பண்ணி இப்போ ஆட்டோமேட்டிக்லி இருக்கும். தேங்க்யூ. ஓகே.
Hello.
Yes, Professor.
Hello?
Yes, Professor.
I want to share my present. How can I share my presentation slide?
Okay. Just a minute. I will ask him to wait a minute.
You want to first introduce myself?
Yeah.
Okay, so I will do that later. Yeah, don't worry. Yeah.
No, if you want, you can check it. Check your slides sharing. Wait a minute.
Yeah.
Now you can share. Now you can share actually.
Yeah.
Okay.
Yes.
Yeah, now it's coming.
It's good.
Can you see?
Yeah. I can see full view.
Okay.
Okay. So.
Okay.
Yeah. Just 4 minutes more. 5 minutes.
Dr. Kumaran,
Yes.
are you ready?
Yes, I'm ready. So May 11. Can we start now?
Just one more minute.
Okay, no problem.
Just yeah, you can start, I think.
Good afternoon, all. So this is afternoon session. The first presenter, Professor Jinbuli.
No, sound volume is not.
Volume is not.
Yeah, audible.
Good afternoon, one and all present here. First, I'm going to introduce Professor Jinbuli. Professor Jinbuli Habtime is a bachelor degree in the year of 1998 and the PhD degree in 2003 from Department of Chemical and Biological Engineering at Seoul National University, South Korea. And he has published more than 200 research articles with well-reputed journals with a IH index of 76 and the citation of 20,316 citations, and his research focused on synthesis and the designed nano functional material for energy storage and conversion devices. for the short introduction. With the short introduction, so once again I like to welcome Professor Jinvoli for this iWest 2026. So thank you. You can start now, Professor.
Okay, thank you for, let's see, yeah. Professor Maya Lagan, thank you for your kind invitation to this great conference, Energy Storage Technology for E-Mobility. And then thank you for kind introduction. Okay, so let's see. Yeah, so I would like to talk about the next generation sulfur cathode. So in this case, we are actually employing the electrocatalyst to accelerate the sulfur conversion reaction. Okay, so as everybody knows, you know, the sulfur battery, one of the reasons why the people are excited with the lithium sulfur battery is because of the high capacity in cathode. Therefore, we expect that we can achieve about the 400 to 600 watt-hour per kilogram. So in the case of the commercial lithium-ion battery, you know that the capacity is around the 200 watt-hour per kilogram. Anyway, so there are many issues in the sulfur cathode. So actually the cell component has the various problems which lead to poor performance. So in the case of the lithium metals, as you know, during the charging and discharging, dendrite are normally generated. So we need to suppress this kind of the growth of the dendrite. And the second thing is the sulfur cathode. Actually, we are focusing on actually the development of the sulfur cathode. So in the case of the sulfur cathode, when you look at the charging process and discharging process, especially in the case of the discharging process, lithium polysulfide are generated. So lithium polysulfide are liquid product. So liquid product can be dissolved in the electrolyte. So we need to prevent the dissolution of the lithium polysulfide. And then due to actually the sluggish the redox kinetics. So when you know that this kind of the polysulfide is converted to Li2S2 or Li2S, redox kinetics are slow. So we need to overcome this kind of the situation. Okay, so when you think about the issues in sulfur cathode, so this is the EG is the gravimetric energy density. To enhance the gravimetric capacity, we need to improve voltage, and then we need to also improve capacity, and then we need to also enhance the sulfur loading. Okay, so how you can achieve this one. So we should achieve the low over potential, and then we should obtain high capacity, and then high area sulfur loading should be achieved, and the ES ratio should be low. The problem with the sulfur electrode, when the sulfur S8 is converted to Li2S, is quite slow. Because of this kind of the sluggish kinetics, part of the lithium polysulfide can be dissolved, and then viscosity of the electrolyte can be enhanced, so ionic conductivity became low. So due to this kind of the interesting problems, we need to overcome that the problem in the lithium sulfur cathode by employing the electrocatalyst. Okay, so when you think about that the discharging, so S8 is converted to Li2S8 and Li2S6 and Li2S8 in first plateau, and then in second plateau. That this kind of soluble lithium polysulfide species should be converted to insoluble Li2S. So by preventing the dissolution of the soluble LiPS, we can decrease the E over ES ratio, and then we can also realize the high sulfur loading. And then by improving this kind of the kinetics, we can decrease the overpotential, and then we can also increase the rate capability in lithium sulfur batteries. Okay, so typically, actually, I have been working in the Mesoporous Material Society. So I'm one of the pioneers, who developed the ordered mesoporous carbon. Anyway, so Professor Linda Nager just employed the CNK3 mesoporous carbon, and then sulfur was infiltrated inside the pores. And then they have shown that due to the high electrical conductivity of carbon, and then because the nanostructured sulfurs are infiltrated inside the carbon materials, they claim that that the capacity retention was improved compared with just the conventional carbon. However, still the lithium polysulfide interaction between lithium polysulfide and carbon was so weak. Therefore, that we need to further, modify the surface of the mesoporous carbon to overcome the this kind of the limitation. Okay, in our group is actually very interested in the development of the electrocatalyst for the conversion of the lithium polysulfide. So as you know, so many people are working on electrocatalyst field. Our group is also working on the electrocatalyst field for the fuel cell or for the water electrolysis. However, we realized that that it is highly required to employ electrocatalyst in the even batteries, in lithium sulfur battery. Okay, so lithium sulfur battery in lithium polysulfide adsorbed, and then lithium polysulfide should be converted to insoluble LiPS with the high rate. If this kind of the conversion is slow, lithium polysulfide can be easily dissolved into the electrolyte. Therefore, we need to decrease the energy barrier when the soluble lithium polysulfide is converted to Li2S. Then you can obtain the high capacity and rate capability and high low over potential. Okay, so let me briefly introduce what our group is doing. So although my focus should be under the lithium sulfur battery, so I just wanna introduce to the one paper regarding that synthesis of the porous materials. So our group can make the various the porous various structured porous materials using the multi-scale phase separation method. So we can make the various composition, and then we can also the control of the structure, the spherical material or 2D material or something, and etc. Okay, so I want to also introduce the research history in the mesostructured materials. In 1992, surfactant was used as a template to make mesoporous material, and then black polymer was also used as a template, and then hard template was used to make the mesoporous carbon, like the CMK3, and then multiple template was used. But our group is actually working on the multi-scale assembly method to synthesize the porous materials with hierarchical structures. Okay, so you might know the spinodal decomposition. So in our cases, by combination of the spinodal decomposition and black polymer self-assembly method, we make the hierarchical structures. The macro structures are synthesized very simple, the spinodal decomposition method, and then mesophase formation was achieved, which is microphase separation was achieved the black polymer self-assembly method. So therefore, mesopores are generated the black polymer self-assembly, and then macro structures are generated, macrophase separation. Okay, so before our report, to make the hierarchical structures, people normally has done in this way. So what they have done is they first made the colloidal crystals, and then colloidal crystals are factored into the face-centered cubic structures, and then precursor solution was infiltrated into the colloidal crystals, and then infiltrated structure was obtained, and then gelled at some temperature, and then after heat treatment, that the mesopores are generated by black polymer self-assembly, and then macropores are generated by the polystyrene. So in this way, so it's step-by-step approach. We need to first step and second step and third step is tedious. And then one more thing I want to tell you is we can just make the small amount, and then synthesis time is quite long. Therefore, it is highly required to synthesize the hierarchically porous materials with simple method. So that's the reason why we synthesize the hierarchically porous materials through very simple method. So we employed the PSBP of black polymers, and then metal oxide precursors, and then leisure, add everything here. And then during the solvent evaporation, we added the small amount of the HCl. Actually, the small amount of HCl induced polymerization of the leisure, and then leisures are macrophase separated like this one, and then black polymer and metal oxide precursors are self-assembled into the ordered mesostructures. Okay, it's how simple it is. And then calcination generated the hierarchically porous meso and macroporous materials. So this kind of the process is quite simple. So you just mix everything in THF solution, and then after evaporation of the solvent followed by calcination, you can obtain this kind of the hierarchically porous structured materials. Okay, so this is the structure of the hierarchically porous SiO2. Major pores are well developed with the hexagonal structures, and then macropores are very well connected. Okay, those kind of the well-connected macropores are characterized using the NanoCT. So NanoCT has shown that the macropores lead struts are very well connected, although we synthesized this kind of the hierarchically porous material through very simple method. Okay, generally, you know, the spinodal decomposition gives us this kind of the three-dimensionally interconnected structures. Okay, so I want to introduce one more, you know, that papers. So mesoporous spheres. So when you think about, you know, the energy density in, you know, the energy related, you know, the devices like the fuel cell and like the lithium sulfur battery. So when materials are this kind of spherical like this one, in such case, energy density can be increased. Typically, so to be used as an electrode for lithium sulfur battery, mesoporous carbon spheres are synthesized in this way, multi-steps. Polymer colloids are first synthesized, and then between the polymer colloids, silica precursors are infiltrated, and then they made the inverse of silica replica template, and then black copolymer and Lejol were self-assembled into the ordered mesostructures, and then after the carbonization, silicate were removed. Then mesoporous carbon spheres are generated. So this is quite laborious. It's a multi-step method. So this is not suitable for mass production. Okay, and then I want to introduce the one more thing, which is the spinodal decomposition that is the typically employed for the black copolymer scientist. So when the AB block, this is the AB block copolymer, and then when they add B homopolymer, when the homopolymer molecular weight are small, in such case it's well mixed. However, when we increase the molecular weight of the B block, like this one, B phase are macrophase separated, and then just the B phase just act as a matrix. So this is the example. When they assemble the PSBPI in the presence of the large molecular weight of the PS, like this one, and then PSR matrix, and then black copolymer just, you know, self-assembled into this kind of the spherical structures. So what I want to tell you is the inorganic material society is just working in the inorganic material field, and then polymer material society, they're just working in the polymer material society. However, I wanna just, you know, get insight from the, you know, the polymer physics. So I want to transfer the physics of the polymer blends to inorganic porous materials. So this is the, you know, the example. So when we add the high molecular weight of the polystyrene, and then when we make the mesostructure, the aluminum silicate using the black copolymer self-assembly and aluminum silicate nanoparticle. So when this kind of the homopolymer polystyrene has the high molecular weight, and then self-assembled, macrophase separated, and then black copolymer and inorganic particles are self-assembled into this kind of the spherical materials. So this is quite simple compared with the previous method. And then by adding one more polymer, even we can synthesize the hollow spheres, and then we can also change the internal structure of the, you know, the spherical mesoporous materials. And then even by changing, you know, the matrix of the polymer from the polystyrene to polymethyl methacrylate, because of the neutral interaction between polystyrene and polyethylene oxide and aluminum silicate, all surfaces are exposed. Therefore, we can make this kind of the anisotropic structures range like mesoporous carbon or mesoporous metal oxide. The advantage with this kind of materials are channels are so short. Therefore, in terms of, you know, the diffusion, this is much favorable compared with, you know, the large size, you know, the mesoporous carbon particles. Okay. so I introduced why the catalysts are important in lithium sulfur battery, and then I also introduced the how we can make the mesoporous carbon sphere or mesoporous spheres using the black copolymer self-assembly. Okay, so let's focus on the the electrocatalyst. So for actually to achieve the next generation sulfur cathode, we need to engineer the electrocatalyst. We need to search for new catalytic materials, and then we need to understand the fundamental understanding. So we need to unveil the parameters to control the electrocatalysis. So as you know, in the case of the, for example, oxygen reduction reaction cases, people try to understand the parameters to control the electrocatalysis. However, in lithium sulfur batteries, what people doing is generally just the changing the catalyst from the A material to B material, and then they say, oh, when we employ just the B material as a catalyst, we can obtain the high capacity and high rate capability. So we need to first understand the parameters to control the electrocatalysis, and then the conductive substrate. So as I mentioned, we are synthesizing the porous spheres. Those kind of the porous material should be controlled for that the electrolyte wettability, and then to accommodate large amount of the sulfurs. By combining and by considering these three factors, we are developing the high performance electrocatalytic sulfur cathode. Okay, first let me start the molecular type electrocatalyst with the ultra high power volume the mesoporous carbon. Okay, so as to be used as the electrocatalyst host, the power volume should be very high to accommodate the large amount of the sulfur, and then content of catalyst should be low. So if the content of catalyst is high, in such case the active material, the space active material space for the active material sulfur could be sacrificed. And then sometimes people are using just platinum, so we need to replace the expensive the platinum catalyst with the inexpensive the molecular type catalyst. Okay, so first I want to show that mesocellular carbon form. Mesocellular carbon form is the spherical mesoporous carbon, and then pore size is around 30 nanometer. And then what I want to tell you is this is spherical, and then pore volume is huge, about 3.5 cc per gram. Therefore, you can accommodate about 88 weight point of the sulfur. So this is good to enhance the energy density of the lithium sulfur batteries. Okay, and then I decided to introduce the FENC catalyst, this kind of the molecular single atom catalyst. So as you know, this type of the electrocatalyst is typically used in the oxygen reduction reaction in the fuel cell, right? To replace the expensive platinum. I just that the combine the knowledge obtained from the fuel cell field with the lithium sulfur battery field. And then FENC was that incorporated inside the pores of the mesoporous carbon sphere. And then that the GNC shows that Fe 2+ ions are generated, and then we cannot find the FeFe, and then we can only find the FeN, FeC peak. That means the atomically coordinated Fe species are homogeneously distributed inside the pores of the mesoporous carbon materials. Okay, and then after infiltration of the sulfur was accommodated into the inner part of the porous carbon particles. And then when we employ just the irregular morphology mesoporous carbon, in such case that the thickness is 15.2 micrometer. However, when we employ spherical morphology carbon with the same loading of the carbon, that the thickness was just 10 micrometers. So therefore, volumetric energy density can be increased by the controlling the particle morphology into the spherical morphology. Okay, so this kind of the FENC site was incorporated into the mesoporous carbon spheres, and then as we expected, so during the charging and discharging, the voltage difference was decreased from the 0.35 volt to 0.3 volt because of, you know, the reaction kinetics are improved. And then, so, you know, that to see, you know, that reaction kinetics, typically using the Landers-Sevig equation, when by changing, you know, that scan rate, current response can be recorded. And then in that way, you can obtain this B value. By employing this kind of the molecular catalyst, B value was increased in the charging process and discharging process. So, okay, by just employing very small amount of the molecular catalyst FNC, we can obtain, you know, the high rate capability in lithium sulfur battery. Okay, compared with the pristine mesoporous carbon, you know, the higher capacity and higher rate capability can be obtained. And then, so nowadays we obtained the better data. Anyway, so when we employ the 5.2 milligram per square centimeter sulfur loading, and then the cyclability was quite good. Only we lost a very small amount of the capacity after the 500 cycles. Okay, the next topic is as you know, we are always, you know, inspired from nature when we do research, right? So, you know, that's the reason why the biomimetic field are quite, you know, active and popular in the science and engineering field. So the reason why people employed this kind of FeNX complex is from, you know, they got idea from the hemoglobin. Actually, the hemoglobin, you know, transported oxygen. So they, you know, that this kind of the Fe site is the oxygen binding site. So this is the reason why people employed this kind of the Fe site for the oxygen reduction reaction catalyst. And then one more lesson is when we, you know, look at the structure of the heme, actually the Fe site is modified with various functional groups. So what I think is our nature is trying to, you know, find, you know, the appropriate adsorption site by just controlling, by, you know, making some, you know, this kind of the functional groups. That means we need to also, you know, control the active site of the MM4, FEM4, by, you know, introducing some of the functional groups. For example, this is regarding the oxygen reduction reaction, which is published by our group. In the case of the FEM4, oxygen adsorption is relatively strong. From the Sabatier volcano plot, we need to lower, you know, the adsorption energy of the oxygen. So this kind of you know, adsorption energy should move this one to lower energy, right? And then if, you know, increase the oxygen adsorption energy, activity would be decreased. So what he have done is by employing the Thiopan, this is the electron donating group. This moves like this one. And then by in the case of the electron withdrawing group, oxygen adsorption moves this part. However, this is in the case of the oxygen reduction reaction cases. Anyway, in the case of lithium sulfur battery, maybe by changing, you know, the functional group, it would affect the adsorption property of the lithium polysulfide. So anyway, we functionalized the thiopin and oxidized thiopin-like sulfur and oxidized sulfur in FEM sites. Okay, yeah, as you know, nowadays in the catalyst field, we should always consider this kind of the DFT calculation to explain why we obtained, you know, the nice result. So in the case of the oxidized sulfur, lithium polysulfide adsorption energy is increased. In the case of the thiopin sulfur, lithium polysulfide, the adsorption energy was just slightly increased. However, when you think about, you know, the rate determining step, when, you know, the thiopin sulfur was, you know, attached around the FNC, you know, that the RDS was, you know, the energy difference is minimized. That means highest activity can be obtained when the thiopin sulfur was functionalized around the FNC. So in the case of the oxidized sulfur, it shows the lowest catalytic activity due to strong binding of the polysulfide. So as you know, from the Sabatier principle, that when adsorption is too strong, right, activity is not good. And then adsorption is too weak. In such case, activity is not good. adsorption should be between too weak and too strong. Therefore, in the case of the cytopine-like cases, adsorption energy was, is intermediate. Therefore, you can obtain the high activity. Okay, so result is as expected. So when we functionalize with the cytopine sulfur, when the Li2S is, further you know that Li2S nucleation potential dip is lower compared with that just the F and C. And then during the Li2S decomposition, you know that the energy barrier was lowered when cytopine was incorporated, and then lower Tarpey slope indicates that that cytopine functionalization is quite critical to obtain that the high kinetic activity during the charging and discharging of the lithium sulfur battery. Okay, so as I mentioned, so when we employ oxidized sulfur, cell performance was not best because the adsorption was too strong. So what I want to tell you is in lithium sulfur battery, the catalytic activity should be also controlled. Many people are just saying in lithium sulfur battery, polysulfide adsorption should be strong, but that's not true. If that is too strong, catalytic activity is not good, like the electrocatalyst. Okay, to show this kind of model system, we have done a systematic study. So as a model system, we employed the PT3M nanoparticles. Okay, so as I mentioned, in lithium sulfur battery field, the problem is the lithium polysulfide dissolution from this carbon-based cathode to the electrolyte. To overcome this kind of the limitation, what people is doing is just employing just some the dopant or some the materials, right? Metal oxide or metal sulfide and metallite, right? Blah blah blah. And then they are saying lithium polysulfide adsorption was enhanced. Therefore, it is just believed that strong adsorption ability of catalyst is just the right answer for high cell performance. But I did not agree because this is catalyst. From the, as you know, the electrocatalyst, Professor Mayer-Lagan is has published that very nice papers, right, in electrocatalyst field, in oxygen electron evolution field, like that field. So in many fields, we always think about the Sabatier principle, right? Not too strong, right? So not too strong and not too weak. Always should be there is an optimal point. So we also think that in lithium sulfur battery, there we can make this kind of the volcano plot by just controlling the adsorption energy of the model electrocatalytic system. Therefore, we obtained the PT and PT3CO and PT3FE. So in the case of PT3FE, the band center is low. So this is a weak binding of the lithium polysulfide. And then in the case of the platinum in itself, right, the band center is relatively high. And then adsorption of the sulfur intermediate is relatively strong. So we thought that in this intermediate, PT3CO would show the higher conversion rate because when you think about the volcano plot. Okay, to make the model system, we controlled the particle size into about 2 or 3 nanometer, and then physical properties are same because the particle size is the same, and then mesoporous carbon is the same. So with the same condition, we just changed from the platinum to PT3CO and platinum to PT3FE. Okay, this kind of the alloying was the evidenced by the X-ray diffraction pattern. Okay, as I mentioned, in the case of the platinum and mesoporous carbon and alloyed structures has the similar pore volumes and then similar content of the catalyst. Therefore, the difference in the performance was derived from that the catalyst surfaces, not related to porous structure and the amount of the catalyst. Okay, so when we make the alloy, that by characterization of the XPS and Janes, we characterize that the balance state is changed from the PT3FE and PT3CO to PT. That means, you know, the D-band center is changed from the PT3FE to PT. So D-band center is highest in the case of the PT, just platinum nanoparticles. Okay, so as we expected, so D-band center is very high in the case of the PT, and then D-band center is low in the case of PT3FE, and then D-band center is intermediate in the case of the PT3CO. So we obtained the best data always in the PT3CO. So in potential deep, and then in Doppler plot, in cycloblarity. That means people are just saying adsorption energy of the lithium polysulfide should be just strong, but that's not true. Like the electrocatalyst, oxygen evolution and hydrogen evolution and oxygen reduction, already, you know, the polysulfide adsorption should be not too weak and not too strong. Okay, and then the D-band center, as I mentioned, so we also, you know, obtained the DFT calculation, and then D-band center, in the case of the PT3CO, D-band center is intermediate, and then so when we obtain the oxygen reduction reaction, you know, the data, so although, you know, the intermediate has adsorption energy, has the linear relationship with the oxygen. So similarly, in this case, lithium polysulfide intermediate adsorption energy has the linear relationship with the sulfur atoms. And then when the D-band center is increased, D-band center is upshifted, and then, you know, the sulfur adsorption energy is increased. So there is actually also linear correlation of the D-band center and the sulfur binding energy. Okay, so as you expected, D-band center can be actually used as a descriptor to explain, you know, the high catalytic activity. And then D-band by when you draw, you know, when you make a graph, x-axis is the D-band center and y-axis is the activity, and then you can obtain the volcano relationship. And then sulfur adsorption energy can be also used as a descriptor. And then x-axis is sulfur and y-axis is the activity. And then, you know, that this kind of the volcano relationship can be obtained. So what I want to tell you is the metal D-band center and then sulfur adsorption energy can be used as a descriptor to expect the catalytic activity of the electrocatalyst. So it is highly important, you know, the design of the optimal catalyst, right? So by considering this kind of the adsorption energy, people just are working, you know, that the just a trial and error, right? But we need to just consider this kind of, you know, the D-band center and the sulfur adsorption energy, not too weak and not too strong. Okay, so finally, I want to introduce, you know, that the another just synthesis, newly synthesized materials, hierarchically porous titanium nitride synthesized by the multi-scale phase separation for application of the lithium sulfur battery. Okay. In lithium sulfur battery, what people is doing is typically we employ mesoporous carbon. And then inside the mesoporous carbon, we add the catalyst. However, we just want to make the you know, the material that has, you know, the dual function, electrocatalytic activity and high conductivity. So before, you know, our group's report, many professors nicely tackled this issue. So they made the mesoporous titanium nitride and mesoporous Ti407 to, you know, achieve dual function. However, so in this case, pore volume is too small because, you know, the density of the titanium oxide is higher than carbon. Therefore, when I look at the data, part of sulfur was just, you know, the outside, you know, the mesoporous TIN or Ti407 because the pore volume is too small. Anyway, so that's the reason why we wanna, you know, combine mesopores and macropores to accommodate most of the sulfurs inside, you know, developed, you know, the porous materials. Okay, so we made by just spinodal decomposition, by simple method, we made actually the mesoporous and macroporous hierarchically porous titanium dioxide, and then that was converted to titanium nitride. And then we made the hierarchically porous titanium nitride. So mesopores are around here, and then there are macropores around the mesopores. And then mesopore surfaces is titanium nitride. As you know, titanium nitride is also catalyst for the conversion of the lithium polysulfide. Okay, structure is something like this one. Macropores are very well connected, and then mesopores are very well developed in the framework. So when we try to infiltrate the sulfur first infiltrate the mesopores, and then the remaining sulfur is infiltrated in the macroporous region. Okay, so this is the hierarchical porous catalytic host. You know that this is the case for 80% of the sulfur cases. When you just employ the mesoporous titanium nitride, because the pore volume is small, part of the sulfurs are just outside the porous materials. This would be just dead sulfur during the charging and discharging. However, when you employ this kind of the hierarchically ordered sulfur electrode, after infiltration of the sulfur in the mesopores, and then the remaining sulfurs are located inside the macropores. This kind of the porous material can accommodate all the sulfurs inside the porous host. Therefore, you can minimize dead sulfur during the charging and discharging. Okay, because of the that the adsorption of the sulfur in titanium nitride is good in Bayer cell, even after 10 hours, very small amount of the lithium polysulfide is dissolved. However, in the case of the ordered mesoporous carbon, because that interaction between OMC and lithium polysulfide is too weak, many sulfurs are just dissolved in the solution. And then titanium nitride has the strong adsorption property compared with the graphene. Okay, so as expected, compared with the titanium ordered mesoporous carbon, high kinetic activity was obtained with the hierarchically titanium nitride. And then compared with the ordered mesoporous carbon, electrode lost its the capacity even after 200 cycles. However, in the case of our materials, even after 450 cycles, the large amount of the capacity is preserved. And then one more thing I want to tell you is that in the case of mesoporous titanium nitride, because of the dead sulfur, capacity is quite low. Okay, so we can also that employ electrocatalyst even in separator. So sometimes that electrocatalyst can be just loaded on the separator, and then we can also obtain a nice result. Okay, so I just want to show the future research direction in our group. We need to understand that the electrocatalyst, we need to control the lithium polysulfide adsorption ability to obtain the high cell performance. And then many people claim that adsorption and catalyst effect. So many people made this kind of the heterostructures, titanium oxide and titanium nitride and vanadium oxide and vanadium nitride. And then they claim that metal oxide adsorb and then conversion occurs in this, the catalyst. But I don't know. Anyway, they obtained a good result. However, I would think that maybe this kind of the reaction would occur, this kind of the TiO2 and TiN interface and vanadium oxide and vanadium nitride interfaces by the dual, the adsorption function. Yeah, let's see. And then, as I mentioned, the catalytic activity should be optimized by making the functional group around this kind of the molecular catalysis. And then one more thing is as you know, in fuel cell, you study the catalyst separately, right? So you study, the hydrogen evolution catalyst, hydrogen oxidation catalyst, hydrogen evolution or oxygen evolution catalyst in separate way. So when you think about, that this kind of the process during the charging and discharging, during discharging and charging, maybe different catalysts should work, right? But we just think about just one catalyst. So in the future research, we need to think about what is best catalyst during the discharging process, and then what is the best catalyst during the charging process, and then we'll combine those kind of the catalyst. And then one more thing is although we add about 5 weight point or 3 weight point of the catalyst, if the catalyst is the host for the lithium that can accommodate the lithium ions like the vanadium sulfide, we can extend just the conversion. We can extend capacity to higher capacity by employing this kind of VS4, because the VS4 can exhibit can show the reversible capacity in the lithium sulfur operating condition. In this case, the VS4 has the dual role. It has capacity and then it has the catalytic activity. Okay, so this is the summary. We need the fundamental understanding for the lithium sulfur battery catalyst, and then we need to employ nice host materials, and then finally we need to develop the next generation the lithium sulfur battery cathode. Okay, thank you for your attention. And this research was supported by the National Research Foundation in Korea, and then the LG Chemistry. So the name of the company of the LG Chemistry was changed to nowadays the LG Energy Solution. So LG Energy Solution, they only focus on the battery. Okay. Thank you for kind attention. Thank you very much.
So thank you, Professor Lee. So you have a nice presentation. And now the session is open for discussion. If you have any questions. So any questions?
Professor, generally you have used this iron nitrogen catalyst.
Yeah.
Is it what percentage is it iron nitrogen?
Yeah, that's very good question. So in oxygen reduction reaction, so people just employ about 2 or 3 weight point, right? In maximum.
Yeah,
so
yeah.
In this, we just employ the 0.3 weight point ion. 0.3. So very small amount.
So this is a good idea, but did you try cobalt based or?
Yeah. So we also changed from the FENC to cobalt NC and the other NC. So actually the cobalt NC shows the best performance compared to the FENC. And then we need to study why cobalt NC has best performance compared to the FENC and nickel NC.
Okay.
Yeah.
So have you thought about any single atom catalyst in this part?
Yeah, it's good. Yeah. So are you also, Professor Mayalagan, are you also working on lithium sulfur battery?
Not really.
No, yeah. Please send me, so because you are working in the lithium oxygen battery, so you might have the very nice catalyst. So actually for the collaboration, please send some the catalyst to me.
Okay.
And then I will integrate your catalyst in the lithium sulfur battery or sodium sulfur battery, and then we can write a nice paper together, right?
Yeah.
Let's do it. Yeah.
So thank you, Professor Lee.
Question in chat box, Dr. Kumaran.
Yeah.
How to reduce polysulfide shuttle in lithium sulfur battery? Someone has question.
How to reduce
polysulfide shuttle? That's the main research topic.
Yeah. You know that in the case of the that the first thing is the adsorption of the polysulfide should be adsorption energy is increased by employing the catalyst. And the second thing is as I mentioned, the reaction kinetics was improved, right? When the reaction kinetics is improved, the retention time of the lithium polysulfide around inside the host is reduced, right? That's the reason why the lithium polysulfide dissolution can be minimized by employing the electrocatalyst.
Okay, very good.
So, Professor Lee. Hello.
Hello.
Professor Lee, I have one question. But you said So in future aspects, we will go for the co-catalyst, which means having charge, there is a different catalyst. One we having the charge for the another catalyst, right? So which kind of, the material, it's a suitable for, co-catalyst.
So you are you mentioning this part?
Yeah, you are.
Yeah, so yeah, that's challenging. So we are, yeah, that's a good question. So I'm now pushing my students to, they try to, find which is best for the discharging, I mean the reduction, and then which is best for the sulfur oxidation.
Yeah,
so
this,
still no. So that's
this is a problem in lithium sulfur battery till now.
Yeah. Yeah, good question. Yeah.
Okay.
This is my proposal to LG Energy Solution. Yeah.
So there is one more questions. Mail again. You can.
Yeah. Does changing to solid electrolyte from liquid electrolyte will reduce the polysulfide settle? If they change the liquid electrolyte to solid electrolyte?
Yeah, sure. So that's a good question. So we are actually working on the solid state lithium sulfur battery.
Okay.
And then recently we obtained very high capacity and good cyclability. So in such case, that catalyst also, helps, that electrocatalytic activity. So rate couplability was greatly enhanced. And then there's actually the dissolution was almost no dissolution because, that is the solid state electrolyte. Yeah.
Okay.
Yeah.
So, but there is some conductivity issue, right?
Yeah, conductivity issue, right? Yeah.
So how to overcome? Solid state.
Yeah, so as I mentioned, so in the case of solid state, lithium-ion conductivity is relatively low compared with that's just a liquid-based electrolyte. But that's not my research, the field. So I don't know the details. But my collaborator always try to that improve the ionic conductivity. So what I'm doing is because there is no the electrolyte. Reaction kinetics is very slow, but by employing this kind of the catalyst, reaction kinetics can be much enhanced, improved. Yeah, that's my strategy. Yeah.
Okay, thank you, Professor Lee.
Yeah, thank you very much.
Thank you very much, Professor.
Any other questions?
Yeah, thank you.
Thanks a lot.
Thank you for yeah.
Our slide person.
So the second presenter, can I start mail again?
Yeah.
So the second presenter, Professor Ramasamy Murugan. The short introduction about Professor Ramasamy Murugan. So Professor Ramasamy Murugan is right now working professor in the Department of Physics from September 2000 onwards in Pondicherry University. So he has published more than 120 research article with the reputed journals with IH Index of 36 and the more than 5,000 citations. And he also worked as a visiting scientist at the University of Texas at Austin. And he was in the Shikoku University and the Nagoya University from Japan, worked as a scientist. And then he was also guest researcher at the University of Kiel from Germany. So for the short introduction, so I like to welcome Professor Ramasamy Murugan for the iWest 2020.
Well, thank you, Dr. Kumaran, for the introduction. Thank you very much for the organizers also. So initially, I didn't know that I'm going to, because being an organizer, I never used to give a talk in any conference. At the last minute adjustments, he asked me to deliver a lecture. So after seeing this number of participants, I think most of them are graduate students. So I take this opportunity to discuss something on how we develop these lithium carbonates, what is the issues with developing the whole solid state battery, where we stand now, and what is our contribution, what is the future of this solid state battery based on lithium carbonates. So I wish to start from the very basics. Evolution of energy storage device starting from 1859 with lead acid battery. Still we are using lead acid battery if you ask me, our technology is 10 years behind the Western technology in India, even lead acid battery is concerned. And we have crossed many barriers. Really, we have done a wonderful job. As the evolution of this energy storage device, particularly electrochemical energy storage devices, concerned. A lot of progress has been made. But if you ask me, all this progress is able to run your taxi or run your car, I don't think it's possible now 100%. Even for grid energy storage, stationary storage, we have to think about the new technology. So we have to think about the new concept, new chemistry for the future energy storage devices. So what are the requirements for the energy capacity? People are working for getting 300 miles range for electric vehicles, enhancement gravimetric and volumetric energy density, and other aspects also. And again, fast charging, ability to recharge batteries up to 80% capacity in just 15 minutes for life more than 12 years, and greater than 150 miles for EV. And above all, safety is very much essential. So people are working on developing non-combustible, sometimes solid separator, they ensure high safety. That's the thing. Above all, for industry and for the consumer markets, are reducing manufacturing costs. So that is the very, very important aspects. Think about before developing a new electrochemical energy storage device is concerned. So future, is it the immediate? Is lithium metal batteries? Because we are talking about the high energy density. So if you look into this specific capacity of various anode metals, starting from our conventional lithium titanate to the metallic lithium, you can see the dramatic increase in the specific capacity. If you look into the present graphite, 372 milliampere hour per gram. If we have a chance to utilize the metallic lithiums, we can end up with 3,861, almost more than 10 times the increase in the specific capacity. Looking through these various anode materials, starting from lead, zinc, aluminum, magnesium, sodium, lithium, and proton. So atomic weight, not much interest people will have, but you have to think about the maximum voltage. Lithium is in the top. Cost-wise also it's a top, but please be careful. What is the amount of the lithium we are using, amount of the money we are going to spend on lithium for developing lithium metal battery is not even great. So one has to keep it in mind about the cost of the lithium metal battery is concerned. And if you look into this roadmap for lithium batteries, already activities for the last 60 to 70 years is concerned, both anode and cathodes and even in electrolyte. We started with the organic liquid electrolytes, graphite and lithium iron phosphate, this which were initially lithium cobalt oxides, then moved on to the lithium iron phosphates. Then recently we started to work on the NMC and NCA. Then in the electrolyte, we just started to work on the non-flammable organic electrolytes and non-flammable liquid electrolytes or ionic liquids. Moving away from the graphite to the graphite and silicon composites or silicon carbon composites. Then people started to work on the lithium-rich NMC as the latest step. And people started to think about, is it possible to use this combination of lithium-rich NMC or polymer electrolytes on some of the composites? Then in the earlier talk also, lithium sulfur is a very interesting, very active research is going on lithium sulfur. But overall, we have to think about the solid electrolyte. If you have a solid electrolyte, we can solve many problems. So you can think about the lithium sulfur, lithium iron, and if you are successful, then we can think about anode-free engineering also. So people are very much interested to utilize the lithium metal as an anode for the application. So which means that these are the three structure, I think, architecture. One is the using the insertion electrodes. That's what we call lithium metal battery with the electrolyte batteries. Then lithium ion battery, then lithium sulfur battery. But each one has its own problems when you start to use the lithium metal. The most common problem is the electrolytes. They couldn't identify the right electrolyte for having this lithium metal battery, whether it's a sulfur or the iron, or it might be an intercalation. Basic things what we require is the solid. So when you imagine the high energy density lithium metal batteries, so people, as far as the electrolyte is concerned, people want to use the liquid or inorganic ionic liquids. So that's the people really working very hard, putting some additives and so many concepts. They try to avoid the major issues with the lithium metals. So forming the in situ solid electrolyte interface or ex situ artificial solid electrolyte and stable host for lithium deposition. Several, I think, strategy they are using it while using the liquid or ionic liquid. I don't think it is the maybe immediate options. I don't think it's a permanent solution to handle the metallic lithium is concerned. A permanent solution might be what you call having a solid electrolyte. Even I don't have confidence on the polymer solid electrolyte. Only option left over is the solid electrolytes, maybe inorganic solid. So once you have the cathode and anode is metal, solid, then solid electrolytes, that's what we dream, all solid state lithium metal. So it's simple. I don't think you have to replace so many things. So what we are using the present technology is the graphite, and you are using the organic liquid electrolytes and any insertion electrolytes. So what we want is we want to replace the graphite by this. These are why lithium metal, we want to use the high energy density we can expect. And not only insertion electrodes, whatever it might be, starts from LCO, NMC, NCA, HAD, sulfur. If someone finds a new electrode material, happy to work with it. That's a concept. What we want is we have to find a right solid electrode. This concept is not new to the world. People have demonstrated LiPo a long time back. But unfortunately, it has its own drawback. That's why people struggled hard to imagine the developing of all solid state battery, particularly based on inorganic solid electrolyte. Once you have the solid electrolyte, you can easily imagine lithium graphite, conventional lithium iron phosphate to the lithium metal and lithium iron phosphate combination. You can have the lithium sulfur combinations and even lithium air or oxygens, whatever it might be. Let us look back the evolution of the solid electrolyte. Just imagine 1954, the concept has been introduced lithium nitride. Then beta alumina, nazigon, lizigon, glassine, LPS, and LiPo. That's really a great breakthrough in batteries. Then ferroscales, then thiolisicons, then garnet, aggregates, and recently good enough antiferrous. Among all the families, there is always a competition among the sulfides and oxides. So whether it's a sulfide or oxides, what we want is ideal solid electrolyte. Have the high lithium ion conductivity, wide electrochemical stability, good mechanical properties, and simple processing. So if you have all the four combinations put together, then we can call this could be an ideal solid electrolyte for the fabrication of all solid state batteries. Advantage of the solid electrolyte based batteries: simple structure, manufacturing process. So electrolytes acts as separator between cathode and anode to prevent contact. That's the only thing. Higher capacity, because if you have the solid electrolytes, decomposition voltage is expected to be high. And if you have the good cathode, then you can think about the high voltage. Above all, higher safety, higher operating temperature, flame retardants, no liquid leakage, and simple. So these are the great advantages of the solid electrolyte based batteries. That's why a lot of active research. But we'll come back to our inventions, lithium garnets. Since it's a workshop, I'm always interested to tell some storytelling concepts just for the graduate students. Our journey into the invention of a fast lithium ion conduction. It started in University of Kiel in Popular Lab. So just I entered in 2007 in University of Kiel to work under Professor Ratna, just with the support of my friend Dr. Tangagare, who is a professor in University of Calgary, Canada. Unfortunately, I couldn't meet him when I landed the University of Kiel in 2005. already he left the University of Kiel and joined as a faculty in the University of Kiel. Okay, that's it. So these garnet, our expertise, our experience in the garnets, I wish to put it in the I think, period. One is with working with the process of how we developed, how we made this innovation on zirconium containing lithium. How we made really a battery, fabricated a battery with the process of Iriyama from Suzuka as well as Nagoya University. And what is my interaction with the professor good enough? Why he is so much interested on the garnet and initially. And later on, when I joined in Pondicherry University in India, so what are the works we carried out in Pondicherry University? We developed these various synthesis techniques and interface engineering, both cathode and as well as the anode. We want to use these garnet for lithium sulfur batteries. At present, we are engaged in anode field engineering. But unfortunately, I'm unable to provide all the results because of various reasons, because of industry projects, both projects. Okay. So what made us to enter into this world of the lithium garnets? So let us take the 4 examples. 4 candidates widely considered a suitable electrolyte developing the solid state lithium battery. One is the LiSiPo, then LiPoN, then lithium, titanium, aluminum, germanium, phosphate, then perovskites, lithium, lanthanum. These are the 4 candidates widely considered 10 years or 15 years back. So if you look into the Arrhenius diagram, it things very clear. LiSiPo has the lowest conductivity among the 4. The LiPoN came into the pictures, and Vaghara sheet made by this lithium, titanium, aluminum, germanium phosphates is the second. Above all, lithium, lanthanum, titanate. But I'm having a disagreement with these perovskites also, because always they used to put the bulk conductivity, ion conductivity, not the total conductivity. But if at all, if you want to use this electrolyte against the metallic lithiums, you have to think about the stability. If you look into this one, the LiPoN has the very poor conductivity, LiSiPo, LiPoN. But chemical stability is quite good, which means that it's stable against up to 5 volts. But the good conductivity, this Vaghara is also some 2.5 or 2.4 volts. But lithium, lanthanum, titanates is the best conductor available at the time. There's something around 3.1 or 3.2. A much more problem is this reduction of titanium 4+. It's very easily reduced by lithium metals and just reduced. And what it may be the leakage of electrons, short circuit, and good fire. So which means the development of truly solid state high power lithium battery is dependent upon the successful identification of a suitable solid state with good conductivity and chemicals. So unless otherwise you have these 2 qualities, you have to develop, you have to think about developing a solid electrolyte which has the good lithium ion conductivity, something very close to 10 power -3, and good electrochemical stability against metallic leakage. But if you look at these 2 diagrams, left and right, you can see very clearly. Lithium, lanthanum, titanate has the good ionic conductivity over electrochemical stability. This LiSiPo has the good stability, but poor lithium ion conductivity. So God played a trick over here. Doesn't allow the people just to make an invention which has both the characteristics is very high. So that's the reason why Professor Bhatna group is very much interested to develop a solid electrolyte. But they look at the various structure, vesicles, and as well as the perovskites and halurites. Even at that time also they tried with antiperovskites. The fast lithium ion conduction is limited only to those well-known structure. Why don't you think about a structure which is free from those things? So while looking through the literatures, they found that the composition like this, lithium, lanthanum, niobium, credit should go to the Mazza and some Italian and as well as the Japanese scientists, the structural chemists. They very easily they made by means of powder, and they measured the powder diffraction, just published what would be the possible structure of this garnet-like structure, these compositions. But why we are interested in these compositions? If you look into the perovskites, lithium, lanthanum, titanium oxides, titanium is the trouble. Remaining things are what's good. But this composition is very similar, lithium lanthanum. Instead of titanium, we are having niobium and antimony. So what you got? So why don't you try? Unfortunately, this NASA and other groups didn't measure the conductivity. We can start to make this material and try to find whether there is any lithium-ion conduction in these. Interestingly, we found this able to make this material very simply. This credit should go to the Koch graduate student, Koch, who made this material first. Niobium, very simple way, just 800 degrees Celsius, they make single phase material by means of this. And they able to observe that's very interesting results. But 40 degrees Celsius, they able to get the conductivity something around 10 power minus gold. So this is a starting point for the looking through the past lithium-ion conduction in lithium quartz. But what we expect is something around 10 power minus 3 Siemens per centimeter. But this is what 10 power minus 6 Siemens per centimeter. The order of magnitude lower than the. So that's the right time I entered into this. I was Wepner Labs. But unfortunately, I am trained by physics. I was a Raman spectroscopist. I got some postdoctoral experience in Raman spectroscopy. I don't have any great knowledge of solid state. But I was forced to learn a lot of solid state chemistry during my stay at the University of Yale. Then I started to learn some things. So my idea is I wish to systematically go through this process. As I mentioned earlier, already the garnet has been reported with the tantalum, niobium, and antimonite. I want to complete that series. I want to put the bismuth. I expected bismuth will sit at the 5 but all chemists laughed at me because I'm a physics guy. So I don't think it will stabilize with the chemistry. No, some positive results. I could stabilize with bismuth even at chemistry. But I got the 4 compositions. I wish to take these 4 compositions to get some understanding on these lithium garnets. So what I did is just I put the conductivity Arrhenius diagram, which tells very clearly. The black one is tantalum, red, niobium, then antimonite, then last one is the bismuth. So the bismuth containing lithium garnets X at the room temperature or any temperature exhibits a maximized lithium ion conductivity. The tantalum is the among this series, tantalum is the least. If you look into this cubic lattice constant, because I know very well that among these dopants, tantalum, niobium, antimonite, and bismuth has the largest ionic radius. So naturally, I expected the increase in the lattice constant. So when I put this moving from the tantalum to bismuth has the largest cubic lattice constant. And what happened is conductivity also maximum. So what I observed is if somehow if I able to enhance the cubic lattice constants, I could improve the conductivity as the first information from this. But we want to test it where we stand among these 4 already existing 4 systems. What interesting is a 2-step ahead, but still a lot of 1 step ahead compared to this one. But we are having other 3 competitors. This is the LiPon, the lithium nitrates, and lithium lanthanum. Then we thought, is it possible any way to improve the conductivity by means of the Li-valent substitutions? Just starting from Li5, what we did, we started to dope this trivalent by means of all the divalent. Magnesium, calcium, strontium, barium, and as well as barium. Again, I demonstrated moving from this magnesium to barium, increasing ionic radii, I could improve this cubic lattice. Get the maximized conductivity. So now, 2 steps further, now we're just left with only 2 competitors, which gives me a lot of confidence that by doing this systematic way, by means of doing these Li-valent substitutions, I could reach this expected. But in the meantime, we want to learn what is the reason for getting this fast lithium ion conduction in these lithium garnets families. So that time we don't have any great crystal structure data because we don't have the different diffraction. It depends mostly on the order X-ray diffraction. Now, if you know very well that it's very difficult to assign the position of this lithium in the heavy lanthanum and the other barium and so many. But with the available data, we're just able to predict that a 3-dimensional lithium pathway. This is what we expect. It's not like the 1-dimensional pathway for lithium ion motion. It's a 3-dimensional pathway. But the credit should go to the person who has made a really big contribution. With the powder neutron diffractions, he helped to protect the what we thought initially is lithium is housed exclusively in what he called distorted 2 octahedral core. But Cousin has made a beautiful interpretation. Lithium is not housed exclusively in 2 octahedral position. It's a combination of the octahedral and tetrahedral position. Much more, it gives a prediction that there is a partial occupancy in the tetrahedral octahedral, which makes me lithium ion jumps very easily from this. This is really a big boost for me. Then I started to work on this various compositions. So let us look into this first one. This conventional lithium garnets. You know, yttrium aluminum YAG. That's a base for the conventional lithium garnets. So when you move from this YAG, yttrium aluminum oxide Y3Al5O, we replace the aluminum by means of the telluriums. Then we used to get these still a conventional Y3Li3T2O2. Then replace the yttrium by lanthanum because we want to improve these cubic lattice. So lanthanum is the ideal option. Then if we replace the tellurium by tantalum, then we got the composition Li5. Then I already explained the Li6 by means of replacing the trivalent lanthanum by means of the divalent. Finally, we want to replace this by means of what we call this 4-valent. So we wish to get a composition like this Li7, La3, Z2, but I have a strong confidence by the time. This could be the ideal compositions. A stable valence. The lanthanum is a very heavy, it's very difficult to move the lanthanum. Then our experience with this yttria stabilized zirconia also with a lot of activities in the Professor labs. I used to think about this right materials. This is also deficient functions. Very, it's very slow. I thought that this could be a bit composition. But I struggled hard because all my materials, the same garnets, I used to prepare at 800 degrees Celsius. But this composition took me to 1230 degrees Celsius. I don't think chemists might have been interested to go up to 1230 degrees Celsius for 36 hours. In between several steps of the grinding and sieving and so many steps. But we got it. So what we want is we should be the top. This is how we made in 2007. So zirconium containing lithium garnets as the best lithium ion conductivity at that time. So we are able to improve the conductivity. What about the electrochemical stability? We don't have any great facilities that time in University of Kiel, and moreover was retired at the time, so we thought that how to carry out this. We took a molybdenum crucibles and put the metallic lithiums, then melted and put it inside these glow box. Then I put my pellet. So I used to keep this pellet as my table weight in those days, even during Christmas period. So what happened? This is as far as our knowledge is concerned, that time this is the first material made outside and just stable against molten lithium for months. It gives a great confidence. So electrochemically stable. But later on with the process of Griyama lab, we tested what could be the electrochemical stability window for this one. It shows tremendous. It's maybe something around 7-fold. So if you look into these various other competitors, sulfides, antiferrosides, borohydrates, and argonites, among the conductivity, electrochemical stability, slightly it is much better when compared to the remaining system. So we come to conclusion that lithium garnets are the most attractive system for solid state. Reason is very simple: stable against metallic lithium, very good lithium ion conductivity, and wide electrochemical window. So I made this invention in 2007. I came back to India. I joined a administrative meeting. I don't have any idea on the research activities about a company. But credit should go to my friend Hawaka in Japan. Just he published a paper on what you call this, a tetrahedral structure. So I was so surprised because I'm not a chemist. After seeing this powder oxide diffraction, and I found that this is this data I used to get when I separated 950 or 1000 degrees Celsius. I thought it's a mixed phase. I should get the cubic phase because cubic phase is a less number of peaks. I always expect peaks. Signature is these 3 peaks. So later I found that in the garnets like such a lithium garnets also we're having one more structure, is what we call tetrahedral. Unfortunately, most of the labs by the time they landed with the tetrahedral structure. bad thing is conductivity is 2 order of magnitude lower than the conductivity of the cubic field. So a lot of controversy regarding these materials. Some people, most of the people are unable to, none of them are able to produce these materials. Then the credit should go to my professor Kanavara from Tokyo Metropolitan University. He's a good friend of mine. Just I gave a recipe how to make these materials. Then at last he found that God has favored me. That's why sintering the samples of 1230 degrees Celsius, 36 hours, I always used aluminum crystals. So from the aluminum crystal diffuse into my pellet and replace some of the lithiums. So that's the reason aluminum diffusion in the pellet is the reason for stabilizing the cubic phase, which helps to get the conductivity 2 order of magnitude higher than the conductivity of the tetrahedral. That the story began the invention in the zirconium containing lithium carbons. So starting from these conventional lithium carbons, Li3, then Li5, Li6, and Li7, you can see the tremendous increase in the conductivity. So 1 in 10 power minus 5 at the 600 degree might be we are unable to measure the conductivity of the conventional lithium garnets at the room temperature. But when you're able to dope these by alveolar substitution, when you're able to increase the lithium concentration from 3 to 5, the conductivity is 10 power minus 6 Siemens per centimeter. When it's lithium 6, it's 10 power minus 5. Then it's a 10 power minus 3, very close to 10 power. So this is the way we have to improve the conductivity of these lithium garnets. We thought that we're having only the tetrahedral phase and the cubic phase of In3T, but later on, a lot of structural chemists came into the pictures and they identified not only tetrahedral and cubic In3T. We're having one rotum cubic phase also, the protonated cubic living. In addition to that, what we're having is I4 3D and as well as orthorhombic IBs. These are the last two of the recent results made in the single crystals as well as made in interval. So now it's very interesting, a lot of structures and a lot of activities on the lithium. Then what is the reason for getting this enhancement in the lithium ion conductivity moving from this ideal lithium garnet to the stuffed lithium garnets? We made a systematic studies also and things, a lot of contributions from the other group also. What we understood is when you have the conventional lithium garnets, the Li3, Y3, Tier 2, what we left with is only the lithium coordination, tetrahedral coordination. Not only that, it's completely filled. When you have the lithium 5, just to start to open up these what we call the octahedral coordinations and keeping some packets. But when you have the Li7, it's optimal concentrations, keeping the perfect optimal vacancy in both, then people start to way we are able to improve this conductivity in Li7, Li3. So we reached 7. If you go to the 8, can I go up to the 10 power minus 2 or 10 power minus 1? Can I beat this any electrolyte? So what is the optimal concentration for the lithium? This short visit, it was a good enough invitations. We did one, and we able to found that lithium is something around 6.4 to 6.6 is the optimal lithium concentration. It maximized lithium ion conductivity. So if you look into this evolution of Barnard structure solid electrolytes, a lot of. Just imagine in 2003 he made this Li5. In 2005 he made this with the Li6 and so many things. But it took longer time to realize the world that it has a lot of potential. Recently, for the last 5 to 6 years, huge importance on materials. Everybody started to work on this solid electrolyte. I want to put these are the major breakthrough in the development of lithium garnets with electrolyte. So these Eberg measurements by Professor Tangadure on this LIFA system, able to measure this. It's a perfectly ionic conductor. Its electronic conductivity is very small. This is the first measure. Then we got this Li7, Li3 is not. Then what you call the tetrahedral phase. And similarly here, these cousins groups interpretation on the coordination of the lithiums. Then my understanding on this cubic lattice constant expansion is really important to get the maximized conductivity. Then Professor Diamo's contribution about how to reduce the grain boundary resistance by means of having this lithium aluminum silicon oxide, and nanocrystallites. And this is another very interesting result. What is the reason for getting the maximized conductivity when you're moving from ideal garnet to the stuff lithium garnet? And the gallium dope is one recent findings for other groups. These are some of these important breakthroughs in lithium garnets evolution. Now, if you want to compare with this summary with the sulfides and antiferroskates and halides, just I feel that the figure of merit for this lithium garnet is still the best among them. And I'm not competing with anyone's, but my understanding is because the reason why I believe this material is far superior, yes, that's advantage of this technology is people knows how to make the tapes. So tape casting really helps to overcome many problems. It's like a separated what we are using the present day lithium-ion battery technologies. People started to make the films thickness of 50 micron size. Really, people are really interested to reduce the thickness and get the perfect good quality. So this is the one advantage I feel this could be ideal material for fabrication of the all solid state batteries. So in bonding, but once people start to get interest, how to produce a bulk volume, that's very interesting. What we did is the laboratory scale, the solid state reaction, which takes at least 10 days to see the lithium zirconium contained lithium garnets with a lot of grinding and ball milling, intermediate steps and firing, calcination, sintering. Oh, too much. So is there any other technique by means of which industry is interested to make this material in a very short time? So this could be ideal techniques, what you call modified soldier techniques. We demonstrated in the physics lab, the Pondicherry University in 2011 itself. This could be ideal. Simple way, very fast you can think about the developing and much more. You have a control over the particle size of this. It has been demonstrated and followed by many. But this is the technique which really I'm interested in. Industries are not much favorable techniques because the combustion techniques, combustion during reaction, explosive reactions. But interestingly, within 10 minutes, you can get the garnet on the pyroplus phase. If you calcine at this 700, 800 degrees, 900 degrees Celsius, cubic feet. Want the much dense, then you have to sinter it at this high temperature. So this is a simple, fast, low cost, and low temperature process. I feel most of the industries may not like because of this combustion nature. And people tried the nebulized spray pyrolysis. We also tried with this flame spray pyrolysis, but we are working on the plasma pyrolysis, but I'm unable to present the results. But we used to work on, from an industrial point of view, what would be the ideal techniques for producing a large volume of the lithium garnet powder. And this conventional way, people used to make these polymer nanocomposites by means of the electrospin techniques. Maybe again, this is on the what you call laboratory scales. It's a very simple way by means of which you can make the fibrous membranes incorporating the lithium powder. So it's conventional PVDF4, HFE, stirring, and adding the garnet powder solutions, then homogeneous light viscous. Then you can spun the things. You can get it. But you have to calcine and sinter for other applications. So this could be a simple technique by means of which you can think about. But we have done a lot of work on polymer nanocomposites also, but I don't want to. But our other major contributions is the grind boundary engineering. If you look into these other oxides, particularly what you call this lithium lanthanum titanate, that people claim this is the best lithium ion conductivity. The bulk conductivity is 10 power minus 3 Siemens per centimeter. But total conductivity bulk plus grind boundary is 2 order of magnitude, something around 10 power minus 5 Siemens. Not only the ferroskates, any oxides, electrolytes, the grind boundary resistance will be very large. Interestingly, this garnet really, when compared to the other oxides, it's less. But still, we believe that it can be reduced if at all, if you're able to find this material for real applications. That's why our initial focus is on the grind boundary engineering to reduce the grind boundary resistance. So this is a classic paper published in this EMA, where we are able to create this what you call lithium aluminum silicate nanocrystalline and this amorphous phase and the grind boundary, whose conductivity is also quite good. So because of this, we could remove completely the grind boundary resistance and be able to get the pocket conductivity is very high. This is by means of this simple technique. Now in Pondicherry University in India, we also used several sintering heights starting from lithium borates to the lithium phosphate, lithium silicates. But we found that the lithium silicate is a good sintering additives by means of which we can use the grinds in a much better fashion. We can improve the density. Not only the density, we can get the maximized conductivity of lithium silicate. Again, it depends upon the what would be the composition of the lithium garnet concept. That decides what would be the ideal option for this. If you are really interested in the conventional sintering of lithium garnets with sintering, then we enter into the spark plasma sintering. But it's not a viable technique for industrial point of view. Just for academic interest, we did a lot of work on spark plasma sintering, also with the help of UPL Delhi. But good results, but it's not that much widely accepted techniques for industrial application. We used a hot isotopic press also, just to understand how to improve the density of these pellets. So without the sintering additives, with the sintering additives, what is the role of the sintering additives? How it is really help to improve the density, how it is useful to improve the conductivity, how it is useful to improve the critical current density and the reduction of the interfacial resistance. We have done a very interesting and dedicated work on this hot isotopic. So this is regarding our interest and our work on the what you call this grand boundary engineering. So then people started to ask, maybe earlier itself, 2011 itself. So ultimately, you want to develop the inorganic element, which has the good lithium-ion conductivity and good electrochemical stability. Already you developed the zirconium-containing lithium garnets. What's the problem in fabricating them? That question came. Again, I went back to Procedia. This lab is especially made for this, what you call the solid-state battery concept. So this is the, if you ask the last slides, what you have is the first all solid-state lithium metal battery based on lithium garnets. I think like this. So we used a PLD for putting this, developing this what I call LCO cathode, sputtering for the current collectors, and this is thermal operated inside the globe box in 2010s. Because even in those days I don't have in Germany, but we coated the very thin foil of metallic lithium on garnet one side, the other side is the LCO, then put the current collector. We thought that we are successful in fabricating the all solid state. But we able to do some microamperes. We unable to glow the LED. Those really very pathetic. People are struggling hard to find a material which has all the qualities. This material has all the qualities. We thought like LiPoN, immediately we can think about fabricating battery, but the results are very poor. Then we understood solid-solid interface is not like a solid liquid. Which means that it takes longer time to understand all the problems. At the time in 2010 or 2011, it's a very young stage, not many players in this solid-state battery working. And once people started to understand this problem and several groups joined together, and I will show you from 2010 to 2010 years is really a big and a very important period for this research activities on the lithium garnet. If you ask me what are the major challenges in the solid state batteries, if you ask me the common issue is the interfacial resistance. Interfacial resistance with the anode and interfacial resistance with the cathode. That's very common we can expect in the solid-solid when compared to the solid liquid instance. Which means that if at all, if you want to think about of the solid-state battery work like a liquid battery means you have to mimic, you have to solve the problems, you have to get the interfacial resistance very similar to the liquid-solid interface. That's a very biggest issue and very common issue. If you look into this cathode interface, the anode interface, it has its own issues with the anode. Lithium dendrite. So initially I thought, once I developed a dense garnet with 98 or 99% of the density, theoretical density, then I thought that we can completely avoid the dendrite. But things became very bad. I started to get the dendrite. So still it's a big issue. Then stability with these anodes. That's also a lot of trouble. So these are the attraction for the initial times. Initially, most of the scientists, they thought that how to solve the problem with the lithium metal and garnet. So many paper literature is available as far as this. I can say almost they are able to solve the problem with the anode, but completely it neglected for the first 8 years on the cathode side. The lattice mismatch, the space charge layer, and these are the biggest problems. So that's the reason why nowadays a lot of activities on the cathode garnet interface. Let us focus on the anode lithium carbonate interface. What you call interfacial engineering is concerned. So we're having strategies to overcome lithium garnet, electrolyte, and lithium metal. We're having several issues, and people started to work on these things. I think we can think about these things. So as far as the strategies to overcome dendrites, buffer layers, anode free structure, ion boundary engineering, overcome these interfacial issues, then we are starting from this surface treatment, tailoring grind size, operating at high temperature by applying a pressure, buffer layers, 3D structure, alloy anodes, and finally, what we are doing is anode free structure. So this is the first work. This is a gold interlayer between the cathode and the anode, metallic lithium and this garnet. Just by forming the lithium gold alloy, one can have a very fine nano size layer which could reduce the interfacial resistance. Just think about 8656 initially, able to reduce it to 54. People started to get 1 ohms per centimeter square is the interfacial resistance, which is on for right, or slightly better than the liquids. So metallic interlayer helps to overcome this problem of the interfacial resistance. We demonstrated that not only this metallic layer, even the lithium niobate, the symmetric cells, which are able to reduce these interfacial problems. Then not only lithium niobate, we are able to graphite, so metal, ionic materials, and graphite. And we have demonstrated with the what you call alloys. So several strategy people came with the pictures with the metals, non-metals, and the graphite, and as well as the alloys, the means of which they able to overcome, not only able to overcome the interfacial resistance problems, they started to realize that they could overcome the problem with the dendrites. So we also demonstrate the sulfur batteries, just how we can able to reduce these problems and demonstrate very well. This is a very hot topic early days. So factors affecting the critical current density of garnet-based batteries, grind and temperature interfacial resistance. You can see in the right-hand side, major interface engineering strategies of the garnet electrolytes and lithium anodes. Several things coming to the everyday, and people start to think about that. It's almost to solve our problems where you can avoid the dendrite and as well as the what you call resistance. And this is the way you can think about what about these latest status on the anode and the garnet electrolyte interface. But the biggest challenge at present is the cathode garnet interface. We're having a problem with the reaction product layer, space charge layer, elemental coefficients, volume expansion, lattice mismatch, and power contact. Really, we never thought that we will have issues like this. So each one is having some overcome these problems. If stability, cathode coatings. If it's a space charge, artificial interface, volume change, three-dimensional cathode host, co-deficiency, buffer glassy layers, lattice mismatch, compactness of structure, over contact, wetting interfacial layers. The problems are large and technologies available, the solutions available large, but it leads to a complex architecture. So this is the first work on our lithium cobalt oxide area and garnet. We observed that reaction product line forms in a few cycles movement. Then this reaction product line is major issues. Then people started to understand how to overcome these lithium garnets and the cathode interfacial reactor layer formation. Then we introduced a gel polymer electrolytes. This is a technology people are really interested to work on to reduce interfacial resistance and wetting ability, improve the wetting ability and fast lithium diffusions, able to get some proper results with this engineering. We used a lithium silicon buffer layer over garnet and coated with the NMC. It gives some slightly better results. This is one strategy people started to use. Slightly better at high temperature, but still at the room temperature is a big question. So we also made this one lithium sulfur battery, just solid electrolytes. Is it possible to solve the problems? It able to avoid this what you call polysulfate settlings. It got this movement, but still we are having some issues with the other sides. Still, it's a good starting point to understand these problems. And we used decoration within conventional polypropylene separators. We are able to demonstrate this garnet is quite useful in lithium sulfur battery also. But you can see tremendous strategies. People are really come up with a new idea every day to overcome the issues with the cathode and lithium garnet interfaces. Really, from 2013 to 27 years, really, there are a lot of work. I expect much more work on cathode to realize the all solid state battery based on. But at present, we are engaging on this anode free engineering. That's a final targets. Really interesting results. People started to get it and interesting results. So you need not have the anode. The problem people face with the commercialization is the handling the metallic lithiums. If you don't have the metallic lithium, then handling will not be a tough task. So just you have to charge it. While charging, you can diffuse the lithium from the one end to other end, by means of which you can form the in situ form lithiums, what you call anode free engineering. But still, we're having the problem with the cathodes. But if you ask me what are the major advantage of the anode free engineering is, if you use the metallic lithium, you can reduce the 35% of the volumes, the naturally energy density you can don't have the metallic lithium just by means of this stripping, and you can just able to make this artificial, what you call in situ formed lithiums, and 50% reduction in these reduced volumes, which helps you a lot to lithium free to in situ plating, which means that you really help a lot to think about the making these all solid state battery, what you call these not free. Advantage is increased safety. Enable lithium metal as anodes. Even you can think about the anode free engineering. Enables high voltage cathodes. Who knows, someone can make the 10 volt cathode also. They can use this material or 7 volt, 6 volts. Smallest size with increase, which helps to improve high energy density and large operating temperature. Longer lifetime, increased safety. That's the reason why a lot of research activities on this all solid state battery, particularly on anode free solid state battery using this garments. Unfortunately, I'm unable to present all the results. On these things, time is up. I think I have to wind up my lectures. Thank you very much once again for all your attention.
So thank you, sir. Thank you so much for your nice presentation. So now the session is open for discussion. So if you have any questions.
There is a question they posted it. Why do you think inorganic electrolytes is the future and not polymer electrolytes? Though polymer electrolytes can easily overcome the major interfacial challenges as a standalone electrolyte. Moreover, lithium metal polymer batteries have been already commercialized with the blue solutions, whereas a complete solid state inorganic battery is still under development.
I am talking about the developments. You cannot imagine the polymer with the anode free engineering. You will have a lot of issues because above 60, you will have the operating temperature issues. Because everybody claims that every day they developed a battery, it's working, commercialized. Story is different. The solid state battery, because I don't want to enter into these arguments. But the final solution is should be an all solid state battery. Okay, I think I can move on to the next questions. I'm not competing with the polymer. So I work with polymer. People are working for the polymer quite long time. So a lot of people. Quite good.
Sir, I have one question, sir. Hello, sir.
Yeah.
I have one question. We have actually many type of solid state electrolytes. For example, oxides and polysulfides and oxyfluorides, fluorophosphates, and many type of the solid state electrolytes. So, do you think what kind of composition is suitable for EV application for the future?
So the problem with each one will have advantage at the same time disadvantage. We are always looking into the commercial point of view. Industry should invest and they have to bring it to the market. Sulfide, you have the lot of disadvantage because you have to work only with the groundnuts. Phosphate is the biggest issue. And for commercial things, if you're able to make a electrolytes, the roll to roll takes. Just it's a question of placing it's a conventional electrolytes, like what you're doing, lithium ion water, like separate, polypropylene separate. And it's very easy to attach what you call the cathode and the anode. And if you're having solid electrolytes, where you can prepare it to open atmospheric conditions, where you can make the process, the tape casting is a well-established technology where people can make the rolls of few meters, meters of 50 microns. So stacking is quite good. But remaining electrolytes, that's what I understood is, oxides are the most suitable for the commercial purpose because industry likes is and technology maturity level is very high compared to the sulfides and fluorides aspect. So each one industry will have its different idea, but oxides will have several advantages: mechanical strength, handling, and the processing technology. Everything will be slightly better when compared to the remaining technologies.
Okay, sir. Thank you, sir. Thank you so much. So really very nice presentation and very useful, sir. Especially for future aspects, you know.
It's not a feature. Maybe in a year time you can see the
Yeah.
commercial.
Thank you,
That's
sir.
what I
Thank
can
you so
say.
much
Thank you.
for
Thank you.
your
Thank
time.
you.
So the next 15 minutes, so after 15
No, 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 it's not next 15 minutes. It's just only 5 minutes is left.
oh, we have we don't need you know the coffee break, coffee or tea break.
I think just 5 minutes you can leave.
Okay, maybe after 5 minutes you can come to join. Thank you.
Very nice presentation, sir. Thank you, Professor. Next on the slide. You can share the screen. You can.
Now, just a minute. Hi, Ivan.
Hi, how are you?
Fine, how are you? After a long time, almost 2 years.
Very nice talk, by the way.
So Miguel, can we start now?
Yeah, they might not have taken a coffee also by that.
Oh, okay.
Yes.
So he said after 5 minutes. So it's almost 5 minutes over now.
I think you can continue.
Okay, thank you. Good afternoon, Professor Anand John.
No, no, voice is low, little bit.
Okay, because of hello.
Yeah. Carry on.
Hello, good afternoon, Professor Anand John. Just I'm going to give the short introduction about Professor Anand John. So Professor Anand John is associate right now. He's an associate professor. Wait 1 minute. In the School of Material Science and Engineering at the Shanghai Jiaotong University, and he got his PhD in Material Science and Worcester Polytechnic Institute in US in the year of 2009, and he did his postdoc in Vandor Group at the Cornell University before joining the SJTU at the beginning of 2013. And Dr. Dion's studies mainly focused on solid electrolytes for lithium ion batteries, and also inorganic thin film ion conductors, which includes application of electrochemical energy storage and conversion technologies. He published more than 10 reputed international journals, which includes JAGS and the Journal of Power Source and the Journal of Applied Physics Letters and nanotechnology. So for the short introductions, once again, I welcome Professor Anand John for the HiVis 2029. So you can start now, Professor John.
Yes.
Yeah, you can start now.
Okay. Thank you for your kind introduction. It's the information is a little bit old though. Okay. Good afternoon, everyone. And it's a great honor to be here, and I thank Professor Murugan for his work like more than 10 years ago, and for this invitation. This is just a wonderful field to work on, and I started I joined the SGTU in 2013 and started to work on this system since then. And the more I studied, the more I find it's a very interesting, and there are always so many things for me to find out. And today I'm gonna specifically talk about our understanding of this lithium and LLZO interfaces. So interface, as simple as this: we have a piece of lithium, and then we have the garnet. So at the interface, there's a reaction like this, right? So it's the lithium ion will combine with this electron and the lithium vacancy to form lithium. But for this to happen, so there's a fine balance between the electrochemistry of this lithium equals to the electrochemical potential of this lithium ion plus the electric potential of this electron. And this combined is equal to this chemical potential of lithium ion and the chemical potential of the electron. So all this need to be equal for this at equilibrium for this to happen. So there will be a variety of factors affecting this lithium and the garnet property. So one thing is that the intrinsic property of the electrolyte, such as the electrochemical stability of this garnet, and the chemical stability, and the contact between these two, and this electroconductivity of garnet, because this is where this electron is, because this is closely related to this electronic conductivity of this garnet. And for the garnet itself, it's closely related to how dense the planets are, and what's the property of this green boundary. So we have so-called green boundary engineering. And the surface of garnet is not that clean, so we need a surface treatment. And people are working to make the surface porous to increase this interface area. So there a lot of work going on this garnet side. And if we look at this lithium side, we can surface treat this lithium, because as you will see later in my talk, the lithium has an intrinsic layer on its surface too. And this is another hot field. A lot of people are doing alloy. So just put alloy elements such as carbon into this lithium, this molten lithium, to make the alloy lithium. Okay, that's this lithium side. And of course, the external conditions are important too. We can apply heat, or we can apply pressure. So all this come together can affect this lithium garnet interface. So I, end of last year, my group submitted different factors in this short review paper published in ACS Applied Materials and Interfaces. But today, due to the limited time, I will focus more on this highlighted areas, including the electronic conductivity of garnet, surface treatment of lithium, and something about the garnet itself. So first, let's take a look at this, this electronic conductivity of garnet. This is important because this determines whether the electrons are available for this kind of reaction to happen. And this is a very famous work. It aroused a lot of interest in this field. I mean, in this people after this, people just pay much more attention to this electronic conductivity of garnet. And this work is was done by Professor Wang Chunsheng, a group at University of Maryland, and in this work, they used this operando neutron depth profiling, this method to study this process, basically this lithium plating and the lithium stripping process. So they use the setup like this. So neutron goes this way, and when this neutron hit the lithium-6, so they will have some nuclear reaction like this. Basically, this 3H, this will form, and it will release and detected by the detector here. So, and they have a potential stack here, so they can probe the released 3H during charging and the discharging of a symmetric cell. Okay, and by controlling by detecting different energy, they can detect different depths of into this cell. And what they get is like this. In that work, they compared several electrolytes, including LiO, and I'm particularly interested in LiO, so I will take this part out. So what they found is that at 25 degrees C, so this is the depth, I mean, let's say from top to bottom throughout the electrolyte. And there's a different time. So when the symmetric cell is maybe charging for different period of time, they monitored the lithium concentration throughout the electrolyte, and they find that at relatively low temperature of 25 degrees C, so this is very uniform, right? And the concentration doesn't increase when we increase when they prolong the time, but at 100 degrees C, so the lithium concentration increases. And what's the reason? And they think that this is due to the deposition or plating of lithium within the electrolyte. So for lithium to precipitate out, plating out, they need a lithium ion plus electron. So they think that at 100 degrees C, the electronic conductivity is significant, so that the plenty of electron be provided. Okay. But in this experiment, they use this copper garnet copper cell. And in the same paper, they use this gold garnet lithium cell to do the similar measurement, and they find that the electronic conductivity is about 2 orders of magnitude lower. And they think that this is due to the interface layer formed between the lithium and LiO. But you know, LiO is known as a very stable material with lithium. So, but those are the argument and their results. And interestingly, there's some computational work relating to the electronic conductivity of lithium. So one typical work is like this. So in this work, they use a DFT calculation to calculate the DOS, density states of different electrolyte. So L0 is right here. So they have several different like vertical line here. So, you know, here is this conduction band minimum, and this vacuum, this line here is related to this electron affinity. So if this conduction band minimum CBM is lower than this one, it says that the electrons tend to stay here. So we need more energy for electrons to be promoted to vacuum. And that means the system is stable. And for the CMB is higher than this vertical line here. For example, this one, there's a Bach. So this is higher. In this case, it's not stable. Okay, that's the position that when we compare the position of this CMB with the vacuum here. And another thing is to compare the CMB with this lithium, with this lithium ion and the lithium elements, the potential this one. So this one will determine whether reaction will happen or whether electron can transfer. So when this CBM is lower than this one, then electrons will go from lithium towards this electrolyte, meaning that this electrolyte is not stable. So, and when this is higher than this one here, for example, this cubic L0, then electron will not transfer. Okay. So after comparison, first thing the result is that when they compare the surface and the Bach, they find that the Bach, this band gap is much larger compared to the band gap of this of the surface here. Actually, the band gap of this Bach L0 is 4.3 eV, so that's a typical insulator. But when we go to the surface, it's 2.2 eV. It's a typical semiconductor. Another thing, okay, as you see here, because this is below than that one, then this kind of material is not stable. So the information here that the surface, the band gap is much smaller. And further, they compared the LDOS, local DOS of this cubic of this Bach L0 and the surface L0, and they find that this electrons, basically this one, the relative density of lithium of LA is much higher here. And by this figure, just put another way, the excess electrons were trapped at the surface of just cubic L0. Okay, then because the electron will be trapped here, will be accumulated here, and then they claim that the L0 itself is a good conductor, and on the other hand, the surface the electrons will trapped here. So there is a chance that the electron will meet lithium ion to plate lithium to form element lithium. And that's why they think that, this lithium will form inside the lithium, the garnet. But there are a couple of questions. Now, one is that even though this is trapped here, it does not mean it can transfer from one place to another place easily, because about the electron transport mechanism, Professor Wepler thinks it's a polar mechanism, meaning that it's very difficult for electron to transfer from one place to another place in LSAO. Another thing is that with our own preliminary results, the previous one, this one is not it's a undoped case. So this is our preliminary results shows that, so when we doped the system with tantalum, so this tantalum will play a very important role, determine the band gap and also this electronic property. Okay, so, and another thing is so this is the work by Professor Yuri Yama group. This group basically showed that this lithium not necessarily plated at a green boundary. Okay, they were placed just right here. That's why this makes us to study more on this electronic conductivity of garnet. So right now, what we're doing is that we're using thick pellets like this and use this 4-point gold measurement to measure this conductivity, electronic conductivity of garnets. And some of the results like this. Of course, the bias voltage higher, the conductivity higher. And there is a difference between the 2-point measurement, meaning the top and the bottom, the 2-point, and the 4-point measurement. And what we're also doing is use this, this is more like this HW method. So there's 3 gold, this is lithium, and we are doing this measurement now. And I hope we can share more these results in the future. Okay, that's about the electronic conductivity of garnets. Another one is let's take a look at the garnet site surface treatment. So this is in this work we show that after storing garnets in ambient atmosphere for a certain period of time, the ionic conductivity will decrease. And that's due to this lithium carbonate formation. And we also find that depending on the grain size, so if there will be more, this grain size is smaller and there will be more grain boundary, then this formation of this lithium carbonate will be more significant compared to the one with larger grain size. And in another work, we further find out that the formation of lithium carbonate is closely related to this moisture. Because if we just store the pellets in dry air after 6 weeks, so we use a Raman mapping to detect the lithium carbonate. So after 6 weeks, still the lithium carbonate, the signal is quite low. But if we store in humid air, it's pretty high. So we propose that the interaction with moisture, water, specifically the formation of this hydrated lithium hydroxide is a very important intermediate agent for this lithium carbonate to happen. And with that, we further increase the air stability by optimizing the composition. So in this work, we added this hydrophobic lithium fluoride. And indeed, after storing in air for a certain period of time, by the TG, the mass loss of this decrease of this optimized composition, the mass loss is much less significant, and also confirmed by the Raman mapping. Eventually, people know that for garnet, if it's not stored carefully, properly, the lithium carbonate will form, and this on the surface, and this will affect this lithium and the lithium garnet interface property. So people are propose the different strategies to improve this property. So one, so it can be divided into two categories. So category number one is to do subtraction. So just try to remove this lithium carbonate layer by either mechanic polishing and by like this acid soaking, and in this work, indeed by this is by heating, by heated up, by heating, they can remove this lithium carbonate and increase this this interface property. And another strategy is to the addition. So to add a so-called interlayer. So this is a very famous work too. So it's an aluminum oxide layer by ALD. And later on, there's just so many different materials have been tried. This zinc oxide, this silicon oxide, and many element material, magnesium, aluminum, silicon, germanium. So there are so many just interlayer added to increase this this interface property. And the reason people propose that for this improvement is number one, this interlayer can increase the so-called wettability between the lithium and the garnet. And another one, so after this, so as a result of this increased wettability, then this lithium ion can transport across the interface more easily. And another thing for the garnet is this green boundary engineering. So because with the use of lithium garnet, when we assemble symmetric cells and do the cycling, this lithium garnet can still form and lead to a shorted circuit. And this has been found by several groups, including Professor Sakamoto and Yuyama, and Professor Nan Cewen group. And we find this too. And this is the shorted cell. Indeed, we can find this lesion along the green boundary. Okay, this is what some researchers find too. So the lithium, this lithium dendrite may form along the green boundary, and this is a typical impedance of this shorted symmetric cell. So it's related to, so it will form along the green boundary. So, so one question is that can we control this lithium dendrite formation by changing the green boundary property? Okay, that's the idea. And my student at that time, Xu Biyi, just used several different lithium salt, lithium borate, lithium silicate, and lithium phosphate. So one thing in common for this salt is that they can have a relatively low melting temperature. So after form this lithium garnet, and we added this one, this different salt as a second phase additive, and the SEM image shows that this additive doesn't change the morphology very much, and by control the content, even up to 10%, it doesn't change this structure, phase structure of garnet much. But when talking about the suppression of the lithium dendrite formation, this lithium phosphate works best. This is before cycling. You can see that this pennant is very dense, and this lithium phosphate just form near the green boundary area. And this concentrated at the green boundary. And the addition of lithium phosphate will decrease the ionic conductivity a little bit. But so when we do the cycling of this symmetric seal, the effect is very obvious. So without lithium phosphate, so this is very noisy. And eventually after around 30 hours, you shorted the seal was shorted completely. But with the help of the lithium phosphate, we can cycle it stably for 66 hours so the current at that time was quite low. So it's 100 microampere per centimeter square. So why? What's the reason underneath? So this is the impedance of this cycled symmetric seal. So it's similar than before. It's not shorted. And this SEM image shows that still this lithium phosphate mainly exists at the green boundary area. And this shows the mechanism. So there's a P3 minus here, so by XPS. So there's a possible formation of lithium 3P during cycling. So there might be a reaction like this. Okay, by such a possible reaction, so we propose the working mechanism like this. If there's no lithium phosphate, then the lithium dendrites will form along the green boundary. So if there's a lithium phosphate near the green boundary, then the lithium phosphate may react with the freshly formed lithium to form a lithium Li3P. But this is a ionic conductor too. Okay, by such a in situ reaction, the lithium dendrite is can be suppressed. Okay, my last the last part of my talk is about the surface treatment of lithium. So I'm not sure whether you can see this video. So this is what my student did. So instead of so when we assemble a symmetric seal, so the conventional way is just stack a piece of lithium metal, another piece of lithium metal, and this garnet in between, and then press it. And maybe we can increase that like around 80 or 100 degrees C to like increase the contact. But in this work, my student, particularly Hongpeng Zheng, he found that by rubbing this garnet in the molten lithium, like this, the contact between the lithium and the garnet can be significantly improved. And you can see this one is the stacked one. This one is a rubbing one. And as you will see in a minute, this already like wetted. This molten salt, molten lithium already wet this garnet surface. But for that one, as you will see in a minute later, this one will come off immediately if we turn this upside down. Okay, if we turn that one, stacked one upside down, it will come off immediately. And so this is a SEM image of this two. So with rubbing, this interface is very intimate. And if we just stack, there's a gap between this lithium and the garnet. So this is the optimized one. This is the conventional one. And this is a typical voltage profile of a stacked one. Even after we heated it to around 100 degrees C and cool it down, this symmetry. So if we do cycling, the voltage profile is very noisy, and it will be shorted after a certain period of time. But if we do by rubbing, then this is what we get. So as we will see, this is the symmetric seal at 65 degrees C. So the half cycle time is 10 minutes. You know, we're measuring this CCD at that time, so we increase the current step by step from 0.01 to up to 3.3 milliampere per centimeter square. So as we will see that, so as we increase the current step by step, the voltage will have such a profile. You know, during one cycle, the voltage goes up. That's the result of the loss of contact at the stripping side. And so that's why we have an increase. So we stopped here because, you know, this is way too much, this voltage. And we'll keep this time constant and increase the current. That means that this capacity is increasing during each cycle. Put another word, the involved thickness of this lithium is increasing during each cycle. So we decided to do this another way. So we kept the capacity the same and increase the current. So in this case, when we increase the current, we have to decrease the time because we keep the capacity constant. So if we do it this way, we fix the capacity to be 0.36 milliampere hour per centimeter square, then we'll find that this current can go up to more than 10 milliampere per centimeter square. So this is a very big one. And at this high current density, we can keep the symmetrical seal running for 500 cycles. And this is, as you can see, it's not shorted at all. So this is a very nice increase of the voltage, meaning that they are losing contact at this stripping side. And we can also increase the capacity to 0.88 milliampere hour per centimeter square. And both experiments were done at room temperature. And we can do this so we can decrease the current density a little bit and increase the capacity, because now we doubled the capacity here. And this symmetric cell successfully cycled for 100 cycles. And we tried this long-term cycling. Now, one example is like this. So at that time, we think this is fine. So at a relatively low temperature, studied for 9 or around 1,000 hours. But later on, we suspect that that might be a soft shot here. Yeah, because, you know, as you can see here, it doesn't increase like previous one. So it's very flat. And at the beginning, it's quite noisy here. And something like this, it's kind of like a soft shot. But this one, no soft shot. This one, there might be a soft shot. And now, right now, what we are doing is trying to control the temperature and control the pressure to increase the current density as well as the capacity. That's what we are doing now. Anyway, at that time, we got the highest current density. That's more than 10 milliampere per centimeter square. And we did a lot of characterization to understand why. So this is the top SIMS results of this lithium metal. So as you can see here, we do this oxygen depth analysis. This is from top to bottom. You will see that this top surface has a certain content of oxygen. So there might be something on the top. And also it shows here. So we have some oxygen at the surface of lithium. So this shows this is spotted for 100 seconds. This is spotted for 4,500. So this is a very top surface. This is like a underneath. So you will see the surface will have a certain amount of oxygen here. So there might be some lithium oxide on the surface. And this, so we characterize this lithium garnet, this interface. And this time, we intentionally exposed this garnet in ambient atmosphere to form lithium carbonate on the garnet surface. And by rubbing for garnet, even with the lithium carbonate, it can be stably cycled. Okay, so this with lithium carbonate, the red one, it can be stably cycled if we treat this lithium properly. And we also use a theoretical computation. We studied this interface formation energy between lithium with different materials. So this is and we find out that the wettability, we use this formation energy to characterize this wettability. So we find out is that the wettability of this tantalum doped LaZO, that's this one, is much higher. Is the best compared. That's better than this LaZO undoped one, and it's better than lithium carbonate, better than this lithium oxide. So the lower the value, the better the wettability. Then we propose such a mechanism. So there is a lithium oxide formed on the surface of lithium metal. So by simple stacking, there's no way we can remove this lithium oxide. Only by rubbing, so this is a molten state, even with lithium carbonate formed on the garnet surface, still we can get relatively good interface property. So if we also remove the lithium carbonate, that's case B, then we can get a current density as high as more than 10 milliampere per centimeter square. So this is a post-test examination. So after cycling, still so no sign of shorting. This is the SCM. So there's a plating side. Stripping side, there are some voids, and plating side, so the morphology of the plated lithium is a little bit different compared to this lithium here. But looking ahead, there are still unsolved problem for this lithium garnet interface. One is the origin of this electronic conductivity is still unknown, and that's what we are working right now. We really need to combine the experimental and this computational work to understand the origin of this electronic conductivity. Another one is the working mechanism and the long-term effectiveness of this interlayer, because people study so many different interlayers, oxides and the elements. But what is the working mechanism? So how exactly this lithium ion transfer across this interface? And how about the long-term effectiveness? Still unknown. Another one, that's also what my group is doing now. So we really need a high current density as well as a high specific capacity, because previously the highest specific capacity is only 0.88 milliamp per hour per centimeter square. That's a relative, that's a quite low value compared to the commercial lithium-ion battery. That's like 3 to 5 milliamp per hour per centimeter square. So another thing is, so many of this interface optimization work was done in coin cells. How about punch? How can we scale it up? And also, how can we manufacture low cost and thin garnets? And also, how can we, if we do this lithium, so the idea is to enable this lithium anode technology. So how can we manufacture and integrate the thin lithium metal? So that's our unsolved problems, and we are working on that. So finally, I will thank my collaborators and my group and this support, financial support.
So thank you, Professor Hannan. So it is a nice presentation. Just you covered with theoretical as well as the experimental for the solid state electrolytes. So now the session for the questions. So if you have any questions, just you can write down.
slide.
So any other questions? Hello.
Oh, sorry, Yuan.
Yes.
Nice presentations. I appreciate your extensive work, excellent work on the interface engineering. So my best wishes. So that's what I can convey to you.
Pardon?
It's a nice presentation, and you have done a wonderful work. Continue it.
Thank you very much. Yeah, there's still so many problems for this interface, and I think we can.
I think you can start to work on cathode side also. Still much problems.
So which one?
The cathode garnet interface.
Oh yeah, that's another big problem.
Yeah. Not a simple problem. 7, 8 problems are there.
Yeah. And I noticed that Professor Murugan already introduced something about that. That's tough too. Yeah, we're working on that. We're using this sputtering method to deposit this lithium cobalt oxide on the surface of garnet.
Oh, it's good.
Yeah, we're working on that. Yeah.
So you're talking with the same person only, Murugan only, Professor with the Murugan.
I think Reddy will talk to you now. Dr. Reddy will talk to you now. Hey, Reddy.
Hello, sir.
Fine. Okay, thank you very much. I think you can.
Thank you, Professor Anand. So the
Okay,
next
I
session
will stop
will
my
take
share.
Dr. Pragas. So Pragas, we can continue. With.
Good afternoon. Next session, the next speaker, Dr. Mailgan, sir.
Yeah. Just a minute.
So hello, sir. Hello, Reddy, sir. This is Kumaran here. How are you?
Share person.
Sir, Kumaran, welcome, sir. Welcome to all the people.
All the Kumarana.
I think Reddy will give lecture in Tamil.
Yeah. I supposed to give, that is very important. Since the international conference, you to respect. Otherwise, I'll talk in. Okay. Thank you.
Share person. Yeah, you can introduce now. Prash.
Good afternoon to everyone. Next speaker is Professor M.V. Reddy. He's a senior researcher at the Institute of Research Hydro-Quebec, Montreal, Canada. And he received his PhD degree from CNRS laboratory from University of Bordeaux, France in the year 2003. And then from 2003 to 2019, he was worked as a senior research fellow in the chemical laboratory, National University of Singapore, NUS Singapore. And for the first 20 years, he has been working on the nano and submicron sized material for lithium-ion battery materials such as cathodes, anodes, supercapacitors, and solid electrolytes, including novel methods of synthesis, characterization, and evaluation of electrochemical properties. He has published more than 200 papers in a highly reputed journal, and his citation H index 61, and his overall citation around 14,000 citations. And he authored a landmark publication on electrode material for lithium-ion batteries and the reaction mechanism that appeared in chemical reviews. And that paper has been cited over around 2,500 times from 2013. And also he trained several PhD and international exchange students. And now I invite Professor Reddy to deliver his talk on the topic of novel electrode material for lithium, sodium, potassium ion batteries. So welcome, Professor Reddy.
Sir, thank you very much, sir. Thank you, Chair and Prakash sir and all the organizing committee, including Professor Mayaligan and his team, Kumaran. And then again, thank you very much, our president. In fact, you know that so Murugan, I think you would remember the different Garnet Murugan they will call. I think the previous speaker has forgotten. Okay. Anyway, so today I just I would like to share my slides, sir. Yeah.
Yeah, please share.
Now it is audible, sir, visible, audible?
Yeah, you make it a full screen. Okay.
Okay, so again, good evening, everybody. So just I'll put my timer on so that make sure that we'll follow the, sir, 40 minutes, if I remember, yes?
Oh, you can go 1.5 hours also, no problem.
Oh, thank you. Anyway, I'll make it so that, okay, again, thank you very much for all the people. So just for attending. In fact, it clearly shows that nearly around 200 people. So it clearly indicate that many people are interested. And also some few people are already, some already people are experts in this battery, and some few new people are coming from the colleges with a different part of the India as well as a different part of the world. Again, thank you for the excellent conference organized by Mayaligan. In fact, today morning I attended the talks by Professor Manthiram. In fact, he told the overview, what is the real status of the energy storage material, etc. So now I'm going to touch up some of the some few new materials and some brief introduction of the something topics are not covered by previous speaker. Hello, sir. Some voice is a little bit. Now it is okay. Yeah. Shall I continue because I saw some voice? Okay, now it is clear. Now it's clear. Okay, so actually I'm from almost previously I was in US next to the Singapore next to the India, so now it's almost very far next to the American border. So Quebec is a both French and English speaking state. So here especially you may see that importance of hybrid vehicle, especially here. I think Professor Manthiram and all the people suggested that any electric vehicle must adopt the climate condition here. Sometime depending on the region, we may see the extreme climate. It may go to -40, -30, some particular regions, and then especially and also temperature you also have to adapt. For example, especially places like India, 65 degree with extreme summer, etc. So this is outline of my talk. Just I'm going to introduce the topic followed by some few examples and the materials. So before I would like to introduce, so I mentioned the importance of the education. In fact, when I was in Singapore, almost 15 to 16 years in the Department of Physics, we've been trying a lot of the school students from the high school and junior college. So I told that there is a way opportunities to survive. In fact, with this funding, I don't need to write a big proposal. So at least I'm able to run the lab more than 10 to 15 years. So again, the importance of this school kids, at least we have trained them. In addition to the training, also we've been published few papers based on the international Scopus journals, starting from high school and junior college, and also we have something specialized students from the NUS high school. So those people have been trained. Interestingly, these students are able to participate in the national and international conferences. For example, Singapore Science and Engineering Fair, as well as some few students are able to go to present in the prestigious Intel International Science and Engineering Fair, and some people they went to Europe and Japan, etc. So overall idea is that at least our responsibility as a mentor, at least we help them to train them, and at the end I think they're able to present like me. Instead of the 40 minutes, they're able to present or work in 10 to 15 minutes or 20 minutes depending on the conference. So again, I think we are like, thank you some of the few people. In fact, you can see the bottoms of many people from India. I think 5 to 6 to 7 people, especially many people from the South. And then I think they've trained, they visited our lab, and many people have utilized the facility. And it's the idea here is that at least whatever they share the facility, I think at the end, they're also getting the exposure. I think it's good, useful for them to use the facility. So again, I think these are a recent group. So again, I would like to thank my previous bosses, Professor Chaudhary and late G. Subbarao. I think you might have known that Stephen Adams is one of the solid state ionics expert. In fact, some of the talks are going to cover by Dr. Prasad Rao, another invited speaker by tomorrow. So all the real solid state electrolyte and interesting things is being covered by Dr. Rao. And also I'd like to thank Professor Vittal from Chemistry Department, and also my previous people from France, and then again Karim from Hydro-Quebec, etc. So these are my small collaboration with within the Singapore as well as the India, different parts of the places, different places all over the world. So again, I'm mentioning that since I work with more than my interest also was in a lithium-ion battery. I tell what is the purpose of doing lithium batteries? Why don't you concentrate magnesium or potassium? The main issue is that if you go for higher, the other elements means mobility issue. Sometimes we may get lower energy density and capacity, as well as another main issue is that the stability of this material. Again, for example, if you prepare any sodium containing compound, you expose outside. Again, these are hygroscopic. That is the way we learned with long back, more than 20 years. We try to prepare the sodium compound by layered compound. You can exchange sodium by lithium. So this is my personal opinion. Still, and now I think as Professor Manthiram suggested, still we have a lot of problems in the lithium batteries also. We have to solve this one. Once we are able to solve real problem, all things finalized, and people slowly focus into the sodium or any other type of the technology. Again, I think some other things we've been worked. So today I'm going to cover mainly on this type of the topics, and some of the other studies have been worked in the area of especially some nanomaterials. It is sometimes more collaborative work, etc. So these are introduced, you know that presently energy, water and healthcare, there are three main global problems, including not only India, all over the world. I think we are working on especially how to, especially in terms of renewable energy. In fact, depending on expertise, people are working on the different type of the renewable energies. Since our today conference is on mainly on battery materials, again, we know the importance of batteries. If you want to use this battery for especially run the electric vehicles or run the, for example, to store the solar energy, etc., or etc. So again, I can tell since some students are there, it is the energy storage and technology interdisciplinary area of material science, both chemistry, physics, and engineering. Again, suppose you want to prepare large scale preparation, we need chemical engineers, or sometimes you want to design or work with mechanical engineering or automobile engineering, especially electrical engineers also will play an important role while doing the real device. Again, maybe at the end, we need civil engineering in the sense that suppose future, if you want to work with driverless or autonomous vehicles, I think they are the main civil engineer play an important role, making the good roads, a good infrastructure. I think they're also playing an important. At the end, I think we need some management because if we want to do all this one, I think management also play an important role. Again, today the topic is that I think as a researcher, we have to understand the basics and the various characterization techniques. That is very important. Although, so since I don't have time to discuss with the large scale, this one, at least I can tell that importance of this battery material. In summary, I think use of these electric vehicles, I think, or any energy storage system, for example, batteries, we can store solar energy or wind, or run electric vehicles, or what they call as smart cities or smart house development. I think battery energy storage will play an important role. So again, so in summary, use of these electric vehicles, I think we can reduce the pollution, and then so overall summary is that depending on the, like as a academic researcher, I think mostly we focus on the coin cell, or sometimes people have facilities, people can go to pouch cell. I think these also already we can do. Again, in summary, if you have good new material, we are able to demonstrate here. Again, I think we can do on the pouch cell or cylindrical cell. Again, remember sometimes although we are academic researcher, we climb very high capacity, high rate, in reality, suppose for example, here also people are doing especially loading the mass, the material will be very important, and then what they call a weight of the material for energy density, we need a proper loading. So that's why sometimes although we climb some 200C, 500C, in reality, practically if we are able to do with a good mass, I think it is enough to, I think 50C or that way it is enough. So overall summary is that although academic researcher is nice, we can develop the new materials, and especially industries are interested, I think they can focus the same material, they can develop in a large scale batteries, or for example, electric vehicles, etc. So again, these are the battery components. I think already people have been discussed the importance of battery component. So again, the cathodes, for example, cathode, anode, and electrolyte. So suppose, for example, if it is in lithium containing compound, it should be any material should be lithium, or if it is working with sodium, it can replace by sodium by lithium, or potassium ion batteries, etc. Again, other things we can use silicon or metal oxide composite, etc. Charge we call as oxidation. Sometimes these are simple basic concepts. So anionic oxidations, if it is electrochemist they call, and positive current, or sometimes you are the electrical engineer, they call as state of charge. Discharge we call as reduction, and cathodic scan and negative current. Again, liquid electrolyte. So usually people use the liquid electrolyte or ionic liquid and some polymer. Again, the new era presently, I think due to flammability issues, there is a lot of interest. In fact, solid electrolyte is one of the hot area throughout the world. In fact, you can tell that in fact this solid electrolyte is very, I think one of the interesting contribution from India, especially Professor R. Murugan. In fact, especially his garnet electrolyte has been worldwide popular. In fact, there is a lot of extent, although a lot of challenges are there, as previous speaker suggested, and also Professor Murugan suggested. Even if I know that a lot of challenges are still, as academic researcher, there is a huge interest, especially solid electrolytes in this area. Again, we make a large scale batteries, I think a little bit challenging, and there is a huge interest is going on throughout the worldwide, including Europe, etc., etc. Again, some people may ask you, I think previous sometimes, what is the purpose of using current collector, the copper? Because copper, it is more stable, it will not react with lithium. Again, copper, if you use the other side, the cathode side, copper may oxidize above 3.5. That's why if you use aluminum to this side, it will react with the lithium aluminum alloy. So that's why sometimes, so as a English researcher, you have to remember that don't interchange the current collector depending on the cathode or anode material. In fact, again, I think this is all the 2019 Nobel Prize. In fact, you know that Professor Mailigan also worked with well-known Professor John Goodenough. So again, I want to tell you that in addition to this one, I think we have written recently some early history of lithium battery. In fact, I dig out all the literature, everything I spend. So you can see the original paper by earlier intercalation concept has been before TAS2. The first paper has been done by Michel Armand, one of the French chemist. They are the iron cyanide bronzes. I think this is very important. So that's why these I can tell before TAS2 this paper was the first, and also you can see again, for example, some of the TAS2 also simultaneously G.V. Subbarao when he was in Bell Lab and Whittingham. All the people, all the TA intercalation concept has been after I remember around 2075 or 80 during the time. A lot of the materials have been done. So again, the importance of the intercalation concept, I think I can tell 1973 or 70 like the example. Okay, for example, if you're talking about sodium batteries, again remember sodium cobalt oxide has been early in almost like 1973 with my previous Professor Heigenmuller from France in our previous laboratory. Again, at the time, people are always concentrating as a solid state chemist to look for the physical and magnetic properties, and then they try to understand the structures, etc. They're not. So again, I think Professor John Goodenough, they visited the lab, and then I think the idea is that through what international collaboration, I think people can get the exchange ideas. So since Professor Goodenough is very smart, I think just he replaced the sodium cobalt oxide, sodium by lithium. I think this lithium cobalt oxide is almost like more popular compound, and he's taken this concept by his own work and published in Material Research Bulletin and some patents. I think Sony used this concept, and then now and there is a lot of extensive research. I don't have time to discuss too much on history of the lithium batteries. Again, the principle of lithium-ion battery, I think already people have been covered. Just I want to tell you more simpler way. So it is like shuttling of the lithium between cathode to anode, where the electron will pass to the external circuit. Very simple. Since your chemists are there, what will happen is that when the lithium removed from the structure, oxidation, it in the sense that, for example, lithium cobalt oxide, when the lithium is removed at a particular voltage 4 volts, means like oxidation, means cobalt 3 plus to 4 plus, and 4 plus to 3. So since solid material electrochemist we call as oxidation and reduction. Suppose if you're talking about this crystallographer, or they call it the structural transformation, etc. Again, the same thing, the galvanostatic potential, for example, voltage as a function of capacity. For example, lithium cobalt oxide, you will get nearly 4 volts or 3.9 volts. Remember, the voltage of cell is difference between the charge minus discharge. As a layman's, you always should get a extended plateau. If you do any discovery in new material, I think you would extend this plateau maybe 400 or 500. I think you will get another Nobel Prize, I can tell. So that's why we need the importance of new material. Any material, whatever way you discover, you would get a plateau, or whatever the voltage, near 4 volts or above 4.2 or 4.5 volts. You have to get extended plateau with almost like 400, 500. That is a real challenging. Still, it is not so easy. So again, so since any new researchers are there are a lot of possibilities to look for the new materials and reasonably good potential plateaus. I think that is very important for designing any new material. So again, the reaction mechanisms are concerned. We broadly classified into based on the intercalation concept. It is very popular, including commercial batteries, or all the sodium, all this one we call as intercalation. Intercalation means simple, like one lithium, almost lithium is inserting and going back. We don't see any much structural variation during the charge or discharge, and what they call minimum volume variation occurs during this type of the intercalation concept. Again, including a graphite or layered compound or iron phosphate, all the things will come under this category. Another one is the tin containing compound. If tin and silicon are there, that's why we call it alloying, de-alloying reactions. Again, remember, if you cycle this limit to 1 volts, we call it the alloying limit. So you can see, for example, tin is there. So first reaction is tin will react SNO to tin metal, and alloy as a consequence 4.4 lithium, we can get the expansion. Same thing with respect to silicon, same story will occur. Again, suppose for example, tin oxide, if you cycle this material 1 volt, we call as the alloying limit. Same material people are working with now. There is extensive research going on. If you cycle same material to the higher voltage, we can get alloying and conversion. Remember, Sometimes there is huge literature. I saw some few publications. I think sometimes people may cycle up to 3 volts, they climb this mechanism. That's why you have to be careful. So always theoretical capacity will be different based on which voltage you're cycling, etc. And again, there is a lot of conversion reaction type oxides are there. In fact, huge bunch of materials. I think people want to use the supercapacitor or some other applications you can do. So that will be very useful, especially sometimes, as you know, that academic researchers sometimes they don't have much facilities. If you use aqueous electrolyte with a simple potential start, or you can do especially research like supercapacitor, etc. So again, if you want design any material, I think it is very important. Always you to, I think already high energy density and high capacity. Again, long cycle life and working voltage is very important, and good Coulomb efficiency almost like 99%, or 100 you will get, mostly it's very difficult. Again, at the end, we have to get low resistance in the sense that during charge discharge, resistance of the cell should be minimal. If it is huge variation, is something going on wrong. That's why, and also at the end, we have to adopt the climate condition. For example, although I mentioned 50 degree, sometimes it may, especially India, sometimes it may go to 65 also in the extreme summer. Especially temperature, I mentioned here 30, some cases in Quebec, in like Canada, some other places, extreme, sometimes it may go to the minus 43 or 45 also. It depends on the region. Again, at the end, we have to look for the more safer material, cost and toxicity. I think these are the major problems. Toxicity, cost make them. In fact, the same thing is occurring, especially in terms of fuel cell, all the, including solar cell, I think the cost is a major one. So anyway, still no options. Still people want to work with renewable energy. We have to sacrifice in some way. Anyway, at the end, we want to look for the fast charging material. I think this is a question mark. Still, there is a lot of extensive research is going on how to improve the rate capability of the material. In summary, if you compare your other technology, I think lithium is very mainly because of the good voltage, like that. As a consequence, we are able to use in the different type of the applications. Again, I think one small slide, I'll tell what are the importance of the, suppose you want to do any researcher want to do look for new material, always you to look for the low atomic weight, in the sense that theoretically, for example, number of lithium into Faraday's constant, and then finally these are simplified formula divided by molecular weight. And the overall summary is that always you to look for the low atomic weight. That is the best principle if you want to design a new material. Again, if you are assuming is anode material, always you to look for the plateaus should be like what they call discharge potential lower as possible is good. And the cathodes, we have to get a higher potential. For example, so there are 3 types of cathodes are there. For example, lithium iron phosphate, lithium cobalt oxide, and iron. So you can see 3.5, 3.9, 4.2. Again, the voltage of the cell is nothing but average potential of the cathode, whatever it may be, minus or any anode. So for example, if you take another example is nickel 0.5, manganese 1.5 is 4.8 volts, you will get, minus by graphite. Or suppose if you use Li4 Ta5O12, you will get around nearly 1.5 potential somewhere here. So as a consequence, we remember, you know, that if you get higher discharge potential, automatically your working voltage will lower. Again, the energy density, it will affect on the your energy density. Although it's not very simple, at the end we need a lot of permutation and combination to do the research. And again, another criteria is that same thing with electrolyte materials must not be soluble with chemically stable. I think this is very important. And we need a mixed ion conductance, a good conductivity. That's why sometimes people, they use some graphene or carbon coating and the current collector to improve different technology depending on the different people have been adopting in the literature. Again, the electrolytes we broadly classified into liquid electrolyte mainly LiPF6 based electrolyte, these are ECDMC. Again, we know that these are reasonably good conductivity when compared to your other type of electrolyte. Again, there is a problem with the flammabilities and leakage issues. And so because of this one, I think another approach is a polymer based electrolyte. Again, polymer and gel polymer electrolyte. And again, the conductivity is slightly lower. Again, we need slightly higher temperature to, especially to, you may not to make a good conductivity. Again, I think one of people may ask you what is the use of separator. I think especially if you're using a liquid electrolyte, so separators will play an important role. Again, so remember, so there is an example of the, so especially we, so again, we try to classify the cell guard or glass fiber separator. Usually for sodium batteries, I think glass fiber is a little bit better because weightability is really good. Again, I think these are the criteria people are looking. We look for thickness, and usually we will buy the commercial separator. You know, you're not bothering too much. In fact, some students are there. I think these are the thickness, also porosity, and good permeability and tensile strength, etc. Again, I think here, I think with all of the Professor Morgan's work, I think these are the literature one. Again, the importance of the solid electrolyte. Again, we know that always it is very important to look for the high ionic conductivity. These are 10 to the minus 4, and the low electronic and wide chemical potential, and a good chemical stability over the temperature range. Again, transparency number also we take into, and also is very important. Thermal expansion coefficient has matched with the cathode and electrolyte, in the sense that, suppose, for example, lithium cobalt oxide, this garnet. I think based on my literature, I checked this is a work with from Germany. I call maybe next slide. I'll show you that again. So they used the LLZO, means tantalum doped garnet with a 0.5 doped sample is a composite electrolyte, and lithium cobalt oxide. Reasonably, I think this is only one paper. In fact, I don't have to discuss too much detail. In fact, you can check the literature. So this is only one paper with real vigors with solid state batteries have been really demonstrated. Again, other one, especially Professor Murugan, and then also previous speaker also been already demonstrated, especially use of the different technique to make a all solid state battery. Again, although a lot of challenges are there, again, the good chemical stability so is very important, and sintering temperatures to match with that of the electrode, in the sense that usually if you go to 700 or 800 degree, make sure that the interfaces, for example, although we claim that lithium cobalt oxide, or it will not react with your electrolyte. So there are the things, big problems. Again, I think people are not bothering about presently based on cost is not bothering, and so mainly they are worrying about how to improve the rate capability. For example, previous speaker, they mentioned that high current. I think there is a lot of challenges are there. Still, there is a lot of scope for this, especially people are working solid state ionics and then physics, etc. In fact, you can see the solid sulfide based electrolyte are there is series of sulfide. Among them, few are the promising electrolyte because of good conductivity. And anyway, these are all the, among them, I think LPA, Li6PS5Cl is a little bit more promising, and also beta LPS, also some electrolytes that people are using. Another one is a garnet based electrolyte. In fact, this early work with the Professor R. Murugan from I think Pondicherry University, in fact, and also with Wepner. So, and also another also Tangadarai also we can contributed with some other type of the garnet, etc. Again, I think due to their original discovery, I think now throughout the world, people are concentrating. I think that early work, what I'm telling, that importance of the academic researcher, although idea is that I think to the small contribution it now throughout the world they have been working, and also in the name of I think garnet, I think Professor Murugan already organized it in the conference, I think 2017 in Pondicherry, the world first garnet conference. In fact, is very famous conference, and then is more specialized conference in the especially in the garnet contribution. So anyway, now today coming to the, again, it is very important. So it's very, so it's always as a researcher. So what type of material processing is very important. Always you look for chemical methods are really good. Why? Because if you work with the 2 to 3 elements, I think if you use the sputtering thin film, sometimes you're getting a lithium evaporation and a good thin film. Usually doing the sputtering, always you get amorphous films, and sometimes you need a sintering of the, and also we get very small quantity. So idea here is that use of the chemical method, for example, co-precipitation method is one of the best method to prepare the layer type NMC type cathode. In fact, this technology has been already demonstrated by pilot scale by Umicore in Belgium. I think people are preparing tons of the, not only Umicore and few part of it, especially Chinese company, many other, especially people have been already demonstrated use of these co-precipitation techniques to prepare in large scale NMC cathode, etc. Again, I also sometimes as academic research, sometimes we call the electrospinning. I don't claim that it's spinning because we need a lot of method maybe. Although as academic researcher, we can do some interesting things. And then sometimes carbothermal reduction method. In fact, if you want to prepare lithium iron phosphate, either you can do what they call as hydrothermal approach, or you can use a carbothermal reduction method also you can prepare. Again, each method have an advantage, it is a disadvantage. I can tell you later if time permits some few material preparation. Again, some new students are there, how type of things we can do. We to look for the ionic radius and everything is to match. Again, if it is thin films, we usually they use RF sputtering or pulse laser deposition, etc. Again, it is very important if you want to make all solid state battery. I think we need a good because usually you do mechanical by cold pressing is a little bit difficulties are there, especially if you work with oxide. So that's why people are using either spark plasma sintering or what they call hot press techniques to make a ceramic dense pellet. Okay, so again, I think the same technique people can use the solid oxide fuel cell and lot of the especially sensor different type of the applications. Again, as a chemist, depending on the research and which type of the materials you want, you can do different type of the nanomaterials or submicron size materials for the battery applications. Again, so you need XRD is very useful tool since any researcher want to should make sure that especially layered compound, you have to check the cation mixing. So make sure that we are able to get a desired lesser cation mixing is good so that before doing the electrochemical characterization. Again, thin films is RBS and these are well-known characterization techniques, for example, galvanostatic cycling and impedance analyzer, etc. So again, suppose if it is XRD, at least we need in situ or sometimes other like Raman and other well-known characterization techniques. Again, these are the one of the electroanalytical techniques. Either you need a battery tester or impedance analyzer, or sometimes especially for solid electrolyte, you need a. I think these are the KL cell has been also used from Professor Wepner's contribution. In fact, very compact and I think really good to do for probe setups. I think this is also very useful setup to people want to do the ionic conductivity measurement, etc. So regarding that, in fact, these are our standard slides. Cathode usually work in the limit of 3 to 5 volts. Anode we work in the 3 to 0.05 volt limit. So in fact, this is a summary of this slide. In fact, already, so importance of, although we climb some of the new material, next slide I'll tell that practically as a hybrid community, many people are working with the nickel-rich layered compound because of the high energy density and reasonably good plathos. We can get nearly 3.7 to like 3.8 volts. We can get that because of this one. It is very popular. Again, each technology, for example, nickel-rich compound, we need oxygen atmosphere. It is not like lithium cobalt oxide. Lithium cobalt oxide, you can prepare our NMC. Like one third compost you can prepare in the in air, so that is not a problem. Again, you may see that this early history again, this one third has been originally worked with, I think, based on Japan from Canada and also Ozuku from Japan, and simultaneously with Singapore. Have been already, I think, 2002 with Chaudhary and Subbarao and Shaju at the time. They've been reported this compound. Again, now there is a lot of the, depending on the capacity, there is a lot of permutation and combinations of this combination is possible. And again, these are all things are known in the literature. So again, one example, what type of materials we can prepare by using, since is a graphene thermal reduction method is one of the, or carbothermal reduction method. So especially as a researcher, we need a good tube furnace. Suppose you want to do high temperature, make sure that tube furnace is really good, and at the end you can put any type of metal oxides and calculated amount of carbon or graphene oxide. You can try to put it in. Usually, my own experience, you need a 650 to 850 degree temperature in it to react. And again, with a proper gas like argon gas is needed to. Or sometimes people want to prepare nitrites. You can use either ammonia gas or nitrogen, depending on the sample you can do. Since you are chemical engineers, some people are there, people want to prepare the catalyst or metal oxide by using simple approach. Again, depending on the research, they need a high surface area, etc. Or for example, supercapacitors also, they want high surface area carbon, especially you can put the sample into furnace, etc. You can do the reaction. So usually, carbothermal reduction method, use a carbon as a source, and we can try to prepare various metal oxide, including that lithium iron phosphate and LiVPO4F, etc. This is one example: lithium iridium fluorophosphate, nearly 4.2 volt cathode material, and reasonably good thermal stability when compared to the lithium iron phosphate. So these are samples prepared carbothermal reduction. These are simple triclinic structures, and also we've been checked with the lattice parameter. So it's very important if you make a electrode material, always you take 70, 15 and percent. The standard way we can do R 80, 10, 10 also you can do. And finally coat the sample, and finally we can get to roll the things, and we can get a, usually these are like small type kind cell. Again, if it is a post cell facility, then again you can cut it different size, again filling everything you can do depending on what type of R, for example, 18650, etc. People can do. Again, remember, if you go for higher device, again, we need little bit expertise, and then especially good proper infrastructure, because a good lab is needed, a good write room, etc. is needed. Since I think this side of Quebec, they have big lab people can do, since there are a lot of technicians, everything people can do work in a group. That is advantage working with a large group. So again, as a researcher, people, if you want to automatic things, these are all things available already in commercial. In also, I think in especially ARCI, different parts of the India also we have this type of standard facilities, fabrication facilities are there. So, for example, you want to make a coin cell, either you can do either cathode anode and put it the metal, either then separator and lithium metal. Finally, we can get a coin cell, and this cell is ready. You can do the either charge discharge. So these are lithium iridium fluorophosphate. So reasonably, as I told you, that compared to your iron phosphate, so reasonably higher voltage, and then it is almost 6 months we are able to run the cycle, reasonably good stability. So interestingly, and also we check with XC2 and impedance, as well as for example, and also in summary, if we good cathode or anode, so we look for the higher potential is good, then only it is very useful for the in terms of high energy density. So now we are going to discuss some few vanadium based anodes, and based on the expertise vanadium materials, I've been extended to the vanadium containing LiVPO4F and metal organic framework material. Advantage of this material is that I think this work with Professor Vittal and chemistry. So if you compare to your lithium iron phosphate, vanadium containing oxalatophosphate materials, we in reasonably almost like 4.51 volt we can get. Interestingly, so based on the early report, I thought is really good. They're all really cathode, not like anode. So anode, many reports are there. First few example been use of these materials. And again, we try to prepare the sample either being simple hot plate or simple stirring. You can try to prepare the sample. So again, remember, since the water is there, so for the battery property, make sure that you remove the water. So usual way, best way is to heat the sample nearly below, I think around 150 degree, make sure that water can be removed. Then that's why the in situ XRD shows that at what temperature clearly water we can remove. So again, we can, since I don't have time, I can do either by various characterization tool. As a electrochemists are concerned, you can see reasonably nearly 4 volts we can get. Again, at the end, people may ask you that, yeah, they're really good. So in summary, I think we have to look for almost the capacities. I think with the temperature of high temperature, we'll get 120. Reality is that it is nice to look for the, especially slightly, we can reduce low molecular weight. Automatically, we can extend the what they call a reversible capacity, etc. Another, people may ask you what type of the potassium ion battery. In fact, these are all the things. Potassium, see, due to mobility issue, you can see almost you get lower capacity. Again, still very recently with Professor Komaba group, I think this is the original work with Dr. Shahul. I think now with Professor Komaba in Japan, I think they've been. I think that if you want to, people want to go to the potassium ion battery, more details at the review by Komaba and Shahul. And again, he's extended the same type of materials with slightly improved performance. Idea here is that at least people can report that in idea the novel results. I think later, I think people can report in a, for example, improved performance, or we have, for example, electrolyte optimization, etc. We can do. So overall summary, if you compare the lithium one. So potassium, sometimes the plateaus is below, and the lower capacity is mainly due to low mobility, as well as some electrolyte problem, etc. And similarly, some new materials have been extended to either we can prepare with lithium containing compounds, or so another new example is a vanadium containing LiVPO4 cathode material. Again, the early work with we've been reported with 2012, followed by again. I think Professor Mantiram group 2013, I think they use this extended. So what I'm doing, although we try and climb some methods, I think later they extended by the solvothermal approach and microwave assisted synthesis. I think they've been extended, and followed by Professor John Goodenough. Again, the same thing, the lithium sodium compounds have been done. Again, as academic researcher, because different people have different ideas, I think idea is that all people work together, at least you can contribute the society, at least we have to look for the new materials. So I think since I don't have much time to discuss too much details on the synthesis, so overall summary is that we can prepare the again depending on the phases. So again, you can see reasonably nearly 4 or 4.1 volt potential you can get. And these are the reversibility of the peak. It will clearly tell that these materials are really reversible. Again, I think they call a phosphate as HPO4 and HPO3 also is possible to prepare. Again, you can prepare sodium, potassium, all combination is possible. So again, his early work with RSC Advanced will be published, and recently 2021 by again Shahul and with Professor Kamabu, Japan. Again, they've extended and they've done the improved performance. So in summary, I think as a chemist, or we have a little bit ideas, I think you can try to prepare a new material. Later, there is a possibility to do. Again, I'm mentioning that although the first report, we can get a lot of ICL in the first cycle. Again, now I think further with electrolyte or some further improvement, I think there is a lot of possibilities are there. So in terms of, I think people are talking about the sodium. I think sodium also is very, in terms of cost wise, again, the sodium batteries are really promising. So I think if you reduce the cost by sodium, again, the sodium chemistry also their own problem. So I think we have to look for the, in terms of ionic radius is higher as a consequence mobility issues already I discussed. So one slide, I think these are the literature, especially Tarascan group. I already clearly mentioned the possible combination of sodium compounds, etc., etc. Again, if you see lithium, the voltage will come down drastically. So this is one example in terms of energy density. Already one example, same compound, don't confuse. Lithium compound, you'll get 4.2. Again, the same compound I cycle with respect to sodium, I'm able to get nearly 3.5. Then overall summary is that although cost is lower, we may get lower energy density. Again, so it depends. For example, grid storage, I think there the cost is also very important than, for example, this voltage. So in summary, I think these are the, in fact, these are all Nasican. I think they're not a really new idea. I think people have been reported. In fact, these are small contribution, the literature. Then there is extents among them. NAVP also a little bit good material and reasonably good plateaus we can get. And with some optimization, we can get improved performance, etc. I think since I have another 5 minutes, I wanted to finish so that the importance of the graphene, people are asking that why don't we use the graphene alone and utilize the graphite? So it's very important. Graphite looks like this way, and graphene we can get slightly higher capacity and higher ICL. This is not really good. And also, you can make a composite, for example, either by so again the new materials people are interested. I think you can. Not a possibility. Alloy-based materials. Okay, I'm going to finish within 3 to 4 minutes. Okay. So again, there is a lot of extensive research is going on. A lot of anode material. Again, each materials have been problems are there. If you talk about irreversible capacity in the first cycle, is a little bit difficulty. I think the voltage is also very important to look for the entire tin-based material. I think I'm going to skip these details. Again, there is a lot of the anode materials have been reported in the literature, although we claim the capacity around 800 milliamps. So in reality, we have to reduce the potential to the lower voltages. So that's why always it's very important. We have to look for the any new materials. Always anode should be we have to get discharged in lower HP. So again, I think with different type of combination, graphene and graphite, like a lot of composites also we can prepare the. In summary, people want to with anode based with the sodium compound. Again, sodium seems to be slightly better because the in terms of anodes we can get a lower discharge potential when compared to the lithium. So that's why these comparative graphs I'm telling that in terms of anodes, yes, again we have to see the plateaus and how they will get a reasonably good potential or not. We check into literature. Again, in summary, always if it's alloy-based materials, you have to look into the potential, which potentials you have to stop. Although we may get higher potential, get high capacity, reality the capacity will fade. So make sure that depending on the appropriate alloy-based anodes, you have to use the appropriate cutoff limit. So I think nitrides have been extensively, people have been, we've been early example with the oxides, we've been demonstrated by the French group. And we thought, why don't you look for the nitride? Means here we can, lithium can be reacted. Anyway, we try to prepare by either using nanoflake or nano thin filament bulk materials. Overall, in summary, so as a chemist, So in terms of electrochemistry, I don't see, especially here, the potential is almost like we don't see much difference. It's a practical application. We have to reduce the potential is really good for the, if you use this anode type of material for the real applications. So I can tell another example is the intercalation type of the oxides. In fact, you can see the lot of the, for example, TiO2 or ruthenium oxide or Nb2O5 and among TiO2, etc. Among them, Li4 TiF5O12 is really promising because of the reasonably nearly 1.5 volts we can get. So that's why if you want to do any titanium based or intercalation type of the anodes, I think we have to look for the, I think if you have any good ideas, people can do nearly 1 volt or this type of plateaus, I think really good for especially hybrid electric vehicles, so that they can use this material for the combining with high voltage, for example, nickel 0.5, Mn 1.5, cathode, etc. I think these are the full cells. Again, I think there is a lot of people are not, I think a lot of literature is there in this type of the material. So I'm going to skip the details on the titanium dioxide since people are molten salt, since my time is catching up. So again, if using the molten salt approach, you can try to prepare by either using nano size approach, again as a XRD data, and again importance of you go for nano size to submicron size material, importance of chemistry. So again, you can play the thing. So with the use of the molten salt approach, I think we've been prepared a lot of the layer type content compound. Again, I'm telling that since this seems to be good only if you work with manganese. Too much manganese rich compounds, it's not really good. We cannot use, we have to do appropriate molten salt depending on the oxidation state, etc. And again, we do simple binary oxide, titanium dioxide. And then again, I think the last example already discussed in 2017 with Professor Wepner, Garnet conference. In this one, again, I am telling the summary that molten salt method is not really good for the especially garnet based electrolyte. What we noticed is that by using this approach, because of water washing, the intercalation of the proton exchange is occurring. As a consequence, we are able to get a lower conductivity and compared to your either simple solid state method. So I think although then later I think use this same concept, I think people have been used by some other people have been for slightly different way, they've been optimized and then use this approach. I think I'm going to skip the electrolyte, and then some supercapacitor work has been, I think there is extensive research going on, especially sometimes in situ reactions. People want to do the safety studies. For example, you can do in situ XRD. For example, you can do how they during the charge discharge, you can do what is going to happen with respect to the material. Overall summary is that depending on facilities, you can do still my own experience, since you don't have any in situ, still you can do XA2. Only thing you need more cells to each time different cells are needed to understand the things. So I think some work we did with lithium with and also some. And sometimes, for example, these are the possible in situ XAS is very useful for future people want to do, especially real type, for example, oxidation state, etc. I can do. I think XAS is also very useful. I think one last slide, importance of, again, it's very important always to look for the what you call circular economy. I think we know you cannot throw the battery in a dustbin. So make sure that I think these are predicted nearly 11 million metric tons of the spent battery by 2030 discard, so that at the end, I think now we have to look for the alternative. In fact, how to recycle the material. That's why there is a lot of research also going on, especially in terms of industry. Again, because since we are working too much of many batteries, I think at the end, I think people can do the direct method, hydrothermal, hydrometallurgy approach, and pyrometallurgy recycles technique. Again, in summary, usual way is that you can discharge the batteries and dismantling and pre-treatment, and finally use this pyrometallurgy or hydrometallurgy approach you can do. So overall summary is that so efforts have been made. Although I claim that so many material, at the end reality, the promising is that this material, although sometimes idea of new materials is good, at least so there is the possibilities. If you look for the other than capacity, what reported is that at least if you look for any new materials with more than the present cathode, I think they're really good for the college community. That will be really useful. Again, at the end, I think we have to look for the safer material and long cycle life, etc. I think this is very important. Again, at the end, we need a cooperation between scientists and engineers, especially to prepare the large scale battery systems are needed. And thank you very much. And okay, so, and I didn't discuss too many. People are interested, I think you can go to the lot of the YouTube, so many big large scale fabrication setup, etc. And thank you very much. I think I've already taken almost like 45 minutes. So now I have some more time to, if you have any question and answer, happy to discuss with you. Okay. Thank you very much. Thank you.
So, Professor, good evening. This is now very nice talk covering all the aspects, material synthesis and characterization. This is Professor Sashidharan from SRM University.
Okay, sir. Thank you, sir. Thank you.
Yeah, thank you very much for the wonderful talk. So I need some clarification regarding the in situ study. So you have done so much, in situ studies.
Yeah.
So
Yes.
I'm really, so I want some information, some technical information from your side.
Yes, I
So yeah, instead of now the beryllium window.
Yeah.
So can we have some substitute, because getting beryllium window from so abroad it is there are so many technical issues.
Yeah.
So something we try to do with the aluminum and other things. So what kind of technique you are using to collect the data?
So yeah, another thing is that people use some like mylar film. Did you try with mylar films or mylar?
Mylar. Oh,
yeah.
Okay. No, still we have not tried that. Okay.
No, the mylar film is a transparent. Only thing the line is something we would check that mylar film is the one option.
Okay.
Also, people recently some like graphene type, and I don't know really it's how it's not so easy to prepare.
Okay.
You make a transparent graphene coating. So that is a little bit difficulties are there. Yeah, you're right. I think so. Sodium is, for example, the beryllium window is a little bit difficult, and make sure that again I forgot to tell you the safety issue, because beryllium is very toxic. Make sure that it will corrode. Try to put it in a glove box, and also don't touch with bare hands. And that is very important. In fact, that is, although research is very important, especially for the students, make sure that don't be handle. Especially the beryllium is very toxic, and we would be careful.
Yeah, that is the surface easily gets corroded and other
things.
Yeah,
no, that's
some
why
kind of force. Yeah.
Always is best way to put it in either dry, what they call the desiccator, or in a glove box. Okay, make sure that. Okay, so that is my personal experience, because it is very important. It makes you neatly clean the thing, especially the electrolyte, the same electrolyte, the solvent. Make sure that to pipe it up and neatly clean the thing. Store in a glove box. Okay.
Okay. So thank you, Professor, once again. Thank you.
Okay. Thank you. I think some people have asked about how to improve the metal oxide by modifying synthesis of bismuth. Yes, I think, for example, molybdates are there. There is a extensive research is going on, bismuth and then cobalt molybdates. So based on my personal experience, photocatalytic properties or whatever, I'm not really expert. I can tell. In reality, this one I think we have to prepare an appropriate materials in a liquid composition. Okay. Especially nanostructuring is very important. Okay.
There is another question from audience. Does the electrode preparation can be done like greener way?
Oh, so I don't know. Greener way means what is the meaning of greener way? Which way, sir? Which way? What is the meaning of greener way? Anyway, people are telling about you can use, for example, previous speaker they're telling that you can use in the carbon mat. I think that's not really greener. I can tell that in reality it's not so easy. People use electrospinning, use a carbon mat, and that is not so. Since why people this technology people want to prepare large scale roll to roll, that's why we need a okay. So maybe I don't know what way greener way. If you explain me, then I can try to.
Sir, good evening. Good evening. Sorry for disturbance.
Yes, sir. Sir, meet your.
Sir,
sir, meet Thank you, sir.
Okay, maybe I don't know greener way. This is very important. So this one you are talking about a greener way.
This is the question asked from KN Vidya. Maybe Vidya, are you there?
No, it's okay. It's okay. I think.
Or if you have any doubts, you can send the email. So usual way is that is very important. Make sure that it should be any current collector. Otherwise, although we can demonstrate them in coin cell.
No, Prasad Rao want to ask some question, I think.
Okay, hello, Prasad Rao.
Yeah, Dr. Rao, hope you are doing good there. Just one question I want to ask is after coming to India, so we are trying to look various approaches, but India is looking for the lowest and cheapest we have to go for. In that context, we are looking for the kind of combination of graphene and graphite for battery. What is your comment about this one?
Okay, I think that is also a good question. In fact, Professor Rao suggested. In fact, I think people are using the graphene. They 100% graphene they will not use. They mix with some graphene and graphite because graphene will improve the electronic conductivity. Suppose you want to improve the rate capability, so the advantage. So
Meeting passcode
maybe 10 to 15% depending on the some people and optimize. Yes, it's really good. Not only, for example, this current collector, you may see that I think during our NUS, we didn't bother to, at the time. Nowadays, there is a graphene coated ink on the current collector, for example, aluminum substrate, so we can see that type of thing. Yeah. Yes, it's a good
So
idea.
is it leading towards a supercapacitor or is it behaving like a battery? That's what.
But it depends on how much percentage you're using, because if it is too much of graphene, again, it will react like the supercapacitor. To make sure that try to avoid maybe if less than 10% or 5% is good. If it's too much, yeah, you're right, the supercapacitor one.
Okay.
There is no more questions now. We'll go to another speaker. There is the last speaker. Hello?
Reddy, please close your slide.
Yeah. Once again, thank you very much, sir. Thank you very much, Kaligan, and then all the people, and welcome to all the people, and then thank you very much. Okay, and also nice conference. I'll try to attend some few talks. Okay. Okay. Thank you very much, sir. Thank you.
Next speaker from Biologic France, Thomas Blunt. He's a sales manager responsible for South.
5:15. Are you interested to come?
Sasidharan sir. Okay. Oh yeah, carry on.
So, sales manager responsible for the Southeast Asia, India, and the Middle East. And Damas graduated from Grenoble INP, specializing in material science in the year 2014. And he has worked for Biologic for more than 5 years. And Thomas is passionate about customer support and is always keen to visit customers to discuss the current research and help them to get the best out of their equipment. So now I am inviting Dr. Thomas.
Yes, thank you for the introduction. Can you hear me?
Yes.
Okay, perfect. Thank you very much for the introduction. So I will take the hand and start the presentation right away. All right, I think everyone can see my screen. If you cannot for any reason, please let me know.
Yes, sir, it's okay.
Okay, perfect. Thank you very much. Before I start, I would like to thank everyone from SRM for the opportunity to give this presentation today. So thank you very much. It's a great pleasure to be here. Unfortunately, I cannot be directly in India. I wish I was able to travel, but for the reasons everyone knows, unfortunately, we cannot travel anymore. But it's very good to be in contact with a few scientists right now across the world. Today's presentation would be on low frequency impedance measurements on batteries while we are charging or discharging these batteries. And the work I will be presented is not based on my work, it's also based on the work of some of my colleagues. And I would like to very quickly acknowledge them. Bogdan Petrescu, Nicolas Muir, and Jean-Paul Diard from Biologic have done a lot of the work that I would be presenting today. Okay, so we go straight away in the presentation. What do we mean by a low frequency impedance on batteries? We want basically to be able to measure, to run an impedance measurement while we are applying DC continuous perturbation in current on the battery, basically a charge or a discharge. And the purpose of that is to study specific processes that happen in the battery. If you study your battery at equilibrium when you are not charging or discharging it, you would be monitoring processes that are not really happening when you charge and discharge a battery. And we will see why, but it's a real challenge to actually measure a battery while it's charging or discharging. So that has not really been done so far, because it's very difficult to know if the measurement we are doing while we are charging or discharging makes sense. But we think we are sure we found a solution to measure properly during charge and discharge. So I will then explain you later how we can do that and what are the limits actually of these kind of measurements. Before we go further, I would like to maybe recall the general requirements for EIS measurements. One of the requirements, which is probably the most important requirement during an EIS measurement, is to be in a linear regime. So in order to make a measurement on a linear system in EIS, we use small amplitudes. Why do we use small amplitudes? Because a resistor is linear. If we double the voltage on a resistor, then we have double the current. Unfortunately for us, there are very little systems in the nature that are linear, and especially not batteries. If I double the voltage on my battery, I'm not doubling the currents. It's pretty far from that. This is why we use small amplitudes and when we are measuring systems. We also want to make the measurements in a steady state sinusoidal regime. We want to avoid any past or transient response from previous measurements. The system should be time invariant, which means that the impedance we are measuring is supposed to stay unchanged during the measurement we are running. Running an impedance measurement on a charging battery is going to be a problem for a few reasons. Is because we're going to have non-stationary states. The response of the battery will not be steady during the sinusoidal regime. So of course, it's going to depend on how fast we are charging this battery. And the battery impedance will also change during with the state of charge of the battery. And this state of charge is changing as we are charging the battery. These are two problems we're going to have to overcome in order to do a good measurement. In order to make sure that the requirements for impedance measurement have been met, we came up a few years ago with what we call EIS quality indicators. So this is not really the main, explaining the quality indicators is not the main purpose of the presentation today, but I still want to explain you how they work in order for you to understand the rest of the presentation properly. So I've just summarized here some of the requirements for an impedance measurement. The first, as we said, is that the measurement should be linear. Okay, if we have a sinusoidal perturbation, then we should get a sinusoidal signal. If we use a PIS, then we should have a sinusoidal current that we are measuring. If, on the other hand, the system is not sinusoidal, then we're going to have a strange answer, and this is something we definitely want to avoid. The system should not be time variant. What is a time variant system? Is a system where typically the voltage will change across time. So this is something which is going to happen if we charge a battery. We should also make sure we don't have any transient answer from the system. And finally, we want to avoid any noisy measurement, but this one is pretty obvious. So we came up with a few quality indicators. The THD is a quality indicator that will help us measuring the linearity of the measurement. It will actually give us, it will measure during the EIS run a parameter. So it's going to be a number, and this will give us directly an indication on the linearity of the measurement. Similarly, we have another parameter, which is called the NSD, that will help us looking at at the sample and see if it's a time variant sample or not, and if we are in a steady state regime. And we can also look at the noise level that we have on the measurements, but we're not going to use this NSR quality indicator today. To explain you a little bit more in detail how that works, when we are doing an impedance measurement on a system, we have a generator, we apply a sine wave on our sample, and what we measure is the voltage and the current, of course, and then we run this through a Fourier transform, and then from this data, we can get some analysis. So I will go to the next slide and I think you will understand a little bit better. This is, I will start with the THD because I need the THD for my next step. If we look on the left-hand side, we can see that we are taking the assumption that we are working on a linear sample. On the linear sample, if we have a sinusoidal perturbation on the sample, we should have a sinusoidal answer from the sample. Then what the instrument is recording is that the instrument will actually record part of the signal and then it will extrapolate it. And then if we do a Fourier transform on the signal, then we get a single peak on the Fourier transform because we have a single frequency. We have a single frequency with a certain amplitude. On the other hand, if we have a nonlinear sample, as you can see, you will not get a sinusoidal answer from your sample. And then at the end, you will not get a single peak after your Fourier transform. It's a little bit of signal treatment. I'm trying to make it as simple as possible. If you have any questions, I will take some time at the end to answer your questions about that. The bottom line is that we see that we have two different answers from the nonlinear system and the linear system. Based on that observation, we can define a parameter that we will call THD with a certain calculation. This is the way we calculate it. And on the THD, we're going to be looking at all the different amplitudes, that's all the different frequencies on the measurements. So we're looking at base frequency and then 2 times the base frequency and then 3 times and so on and so on. And we run this calculation, and then from this, we can get an information on the linearity of the system. Now that I have explained this THD, I want to go to the first step of how do we make a low frequency impedance measurements on the sample while we are charging or discharging. The first question we should ask ourselves is which EIS technique should we use to do these measurements? Because, okay, we want to do a challenging measurement, but as you know, you have different types of EIS measurements. No matter the instrument and the brand that you're using, you probably have different names, different ways to run these EIS measurements. And we need to wonder which one is the best for a measurement. First thing we need to keep in mind is that we want to perform an EIS measurement while we are charging. If we do an EIS measurement while we are charging, means that we have to apply a DC perturbation in current. So based from these first points, we can say that we will use a GIS, an impedance measurement where we are sending sinusoidal perturbation with a current perturbation. The second thing is that we need to maintain a good linearity over the whole measurement, because remember we mentioned before we are expecting to have problem of stationarity, problem of steady state regime. So first thing is to get a technique which will give us a good linearity over the whole range of the measurements, so we can put this problem on the side and then focus on stationarity issues that we may have during the measurements. The question is, we are going to use a GIS, but what type of GIS are we going to use? So I don't know if you were aware of that, but there are different types of GIS. I've just shown right there a picture of typical measurements that you can do on a charging battery, where you are repeating impedance measurements over and over and over during a discharge. You can see the first impedance and the 7th impedance here. And then I will go get back to this example later on. But this is just to give you an idea of what we want to do during this measurement. So, okay, we know we want to use the EIS measurement, but we don't know which one. So usually what we are doing in GIS measurement is that we are sending perturbation on the current, which could be current with a DC value. So if we charge or discharge the battery, this DC value would be positive or negative, of course. And then we are looking at the voltage. But we want the current and the voltage to be linear. We have another type of GIS available, which is called the GIS with adaptive amplitude. What is the GIS with adaptive amplitude doing? In this type of GIS, what we are doing is that we are actually, the instrument is actually controlling the current during the excitation, during the impedance measurement. But what we are, the parameter we are setting on the instrument is the voltage, the amplitude of voltage that we are expecting to have as an answer from our system, which means that we can put a GIS, but have set the amplitude in millivolts. And this will actually help us improving the linearity during battery measurement. This will help us also to apply DC current, because we need to charge and discharge the battery during this measurement, as we mentioned before. For those of you who may wonder how to activate this GIS with adaptive amplitude in the software, you can see if you open typical GIS measurement, instead of putting the amplitude in milliamperes, you just have to change the type of amplitude from current to voltage, and then you can apply the amplitude in voltage, and this you will automatically change to this type of GIS. So we are expecting to have a better linearity with a GIS with adaptive amplitude, but we need to check that. And to check it, we are going to use the quality indicator we have mentioned before, the THD. So we have run two measurements on a battery. This is an example. Okay, we have done this on many samples, but this is an example where we run two measurements on a battery. One measurement is done with a GIS with an amplitude of 50 milliamperes, and the second measurement is a GIS with adaptive amplitude. So we are setting an amplitude in voltage, and we are setting an amplitude of 3 millivolts. And you can see we have two different answers. They look the same, but these two graphs are not the same, and they are measured on the same sample. So we should have exactly the same impedance measurement, which means that there is a problem. We are doing the same impedance measurements on the same sample in the same state. We should have 2 times the same answer. In order to find out which measurement is the best, we're going to look at the quality indicators. The quality indicators are here, so it's the full dots, and we can see that the THD level is actually higher on the GIS than it is on the GIS with adaptive amplitude. The blue curve is the GIS, and the red curve is the GIS with adaptive amplitude. If you look at the amplitude in currents during the measurement, you can see that the GIS has maintained. It's the blue rounds down there. So it has maintained an amplitude of 50 milliampere during the measurement. And on the measurement with the adaptive amplitude, you can see that the amplitude in current has been changing throughout the measurement. And this is what actually helps us maintaining a very good level of linearity, as we can see on this graph. What we see here is that the GIS with adaptive amplitude gives us a much better linearity, much better results, and simply a result that is closer to reality. We are going to use the GIS with adaptive amplitude for the rest of the measurements. All right, now that we know which GIS we are going to use, we need to wonder which challenges we're gonna be facing during charge discharge. The first problem is that usually low frequency impedance measurements are always corrupted when you're charging and discharging during an impedance measurement, because they are slower if you run an impedance measurement at a few millihertz, you will see that to get a data point, it's going to take longer. It's just because one period of signal will take much longer. We are also expecting that a few factors would influence the quality of our results. Of course, the magnitude of the DC current, the stronger we charge, more likely the more difficult it's going to be to run our measurements. At the same time, we have the magnitude of the AC perturbation that that will have an impact on the measurement. The low frequency limit, as we mentioned, if you go to lower frequencies, you're gonna have a problem because these points are longer to measure. So the lower you're gonna go in terms of frequency, the more difficult it's going to be to actually run this measurement. And finally, the state of charge of the battery may have an impact because, as you know, the voltage shape of if you look at a graph when you're charging a battery of the voltage versus time, you can see that the shape of this graph is changing over time. I think there is a question from Prof. Kwanan, or no? Okay. Then I will go to the next slide. I can anyway take some questions at the end if you have some. So let's look at an example of measurement on a charging battery, and we will compare these measurements on the charging battery. So this is the red curve that you can see on the left hand side here, to a measurement, an impedance measurement done before the discharge and after the discharge. So before the discharge is the green curve, after the discharge is the blue curve, and during the discharge is the red one. The green one is a good measurement. The blue one is also a good measurement. The state of charge of the battery has changed between these two graphs. This is why they look different, but they are both very good measurements. On the other hand, if we are looking at the red graph, we can see that the shape is really strange. The shape is really strange, and if you just base your analysis on this shape, you probably go into something, you're going to get the wrong results and your analysis would be completely off. We can also look at on the right hand side at the phase and the modulus, okay, of these two measurements, and again we can see that during discharge we get a strange measurement. For all these measurements, we have used an amplitude of 10 millivolt in order to be able to compare them. And when we were running the discharge, we have used a DC current of 500 milliamperes, which is pretty high. In order to go further and understand what is going on here, I want to very briefly introduce you to another quality indicator that is on biologic instruments. Similarly, with the linearity, we can measure a non-steady state regime. Again, if we look at a steady state regime, if we are on a linear system, of course, we are expecting to have a nice sinusoid from our sample when we are running the measurement, and this should give us a spectrum with just one peak in frequency when we are running the Fourier transform. On the other hand, if we have a non-steady state regime, then the answer of our sample should look like this. The instrument is going to measure a part of this sample, of this response, sorry, and then it's going to extrapolate it over time. And this is actually going to give us a spectrum after the Fourier transform, which is very typical of a non-steady state regime. You can just visually, you can immediately spot the difference. Similarly, if we consider a time invariant and a time variant system, if we look at the difference between the two, so on the time invariant system, we should have something which should, this is an example, but it could look like this, for instance. And then the instrument is going to measure this, it's going to extrapolate it to there, and then we're going to have a very strange spectrum. So we have this is why we have introduced this second quality indicator that is called the NSD, for non-stationary distortion coefficients. And we can see that on this with this quality indicator, we're going to be looking at the frequencies that are very next to the frequency that we are using for the measurements. And in both time variant and non-steady state variants, non-steady state case, sorry, we will be able to actually spot these frequencies. And then we run a calculation. And from this calculation, we will have an SD value. So it's just a number for us. But the higher this number is, again, the less, the worse is going to be our result, and the further away we are to be in a steady state or in a perfectly steady sample. So let's have a look. I will get back to our example, okay, where we have a measurement before and after discharge and a measurement during the discharge. We can see that the two measurements before and after the discharge, they have NSD levels that are extremely low. They are below 0.1%, which is considered for NSD to be a pretty low value. On the other hand, if I look at the NSD value on the sample during the discharge, I can immediately see that below, let's say, 10 Hertz, the value of NSD starts going very high. And we can see visually also on the graph here that below 10 Hertz, the red curve starts to be off. It starts to be very different from the other curves. And the fact that I see the NSD going up like this means that my measurement is not reliable anymore. Similarly, we can do successive EAS impedances on a lithium-ion battery. This is the example I've shown you before, where we do multiple impedances. We start from the first one, and then we go down and down and down. This gives us, again, strange shapes in the measurements. And you can see that depending on the state of charge, the shape is getting really different. So if you compare the first and the seventh measurements, the shape is really different. This is normal because the state of charge is changing. But we can also wonder if this is a good measurement. If we look at the NSD levels again, we can see that the NSD level are going pretty high, below around 1 Hertz, which make this measurement not so trustable. So the question is, how can we get a comfortable NSD level in order to be able to analyze the data, the low frequency data? Again, if I just go back here, you will actually realize that above 1 Hertz, maybe above 10 Hertz, the NSD levels are good. So I could actually analyze the data above 10 Hertz. Today, I'm focusing on the low frequency because it's the most difficult part to analyze and to measure. So this is why I'm saying this measurement is not good. But if you're just focusing on whatever is going on above 10 Hertz, this measurement is good enough. All right, so this is a measurement that was done, and we have used different AC-DC ratios. So what do we mean by AC-DC? Is just we compare the speed of charge. Okay, the DC level is the charge. In this case, we are discharging here. So in this case, we are discharging at 100 milliamperes or 30 milliamperes, and the DC value is going to be the amplitude that we use for the measurement. And we're going to be looking at two things. We're going to be looking at the THD and the NSD. The THD is because if we start to play with the amplitude, we don't want to go out of the linearity of the sample. And the NSD because we want to make sure that our measurement is good and we don't have a drift of the system during the measurement. If we look at these different measurements, we can see that by lowering the DC value and that by increasing the AC value, we were able to lower the NSD levels down to a very acceptable level. We are below 2% of NSD. This is very acceptable. On the other hand, if we use 100 milliamperes to charge and 5 milliamperes of AC voltage, then we are having values of NSD that are not acceptable. And if you look at the shape here, just from the shape, you can see that there is something off with the red curve. This is an indication. So one thing you want to be careful of when you're running this kind of measurement is to have an AC and DC ratio that is favorable to the measurements. You're probably going to ask me, okay, should I use these values for my sample? The answer is no, because it's going to depend on what is your sample actually. 30 milliamperes for a coin cell is going to be big. It's going to be huge even. In this case, we're considering cylindrical cells of a certain capacity. The good answer to that is to actually look at the quality indicators, just like we are doing right now. You need to play with these parameters in order to bring the quality indicators down to values that are acceptable. So I'm sorry, I will very quickly switch to a corrosion example because it's much more visual. You can actually reproduce the same thing on a corrosion sample where you are running multiple impedance measurements across time. But once you have found the right parameters, so you have found the right AC and DC ratio for your measurements, you know that you have an NSD level that is acceptable and a THD level that is acceptable. Then you have a final answer you have a final question to ask yourself. If you have, if you're running a measurement in low frequencies, remember the last points are going to be longer to measure than the first points. So maybe between your first point and your last point, you may have 1 hour or even 10 hours passing, and the state of your sample has changed during this time. Typically, if we are looking at a corrosion system, if we do measurements and we go to very low frequencies, we would get this very strange shape on the measurements where, you know, we have a tail that goes back to the origin of the graph like this. Of course, this is not the right graph. Okay, if we look at the NSD levels on these measurements, the NSD level is fine. It's low enough, so the measurements is good. Each point individually, each point is well measured and it's true. But to understand why we have this tail and where the problem is coming from, we need to look at the impedance data a bit differently. We need to look at the impedance data in 3D. And this is how we will look at it. I know this is a bit strange if you have been always looking at impedance data in 2 dimensions, but as soon as you want to do innovative things like running a measurement at low frequency, doing a discharge, you have to look at it in 3D. What we see here is that at the origin, so this is the Nyquist plot, okay, the classical Nyquist plot, and then we have the time on this axis. You can very quickly see that on this graph that the last points were very long to measure, because you see the first points, they are very close together in time, and the last point starts to be very different. And from the end of your first measurement, you immediately start the next one. So we understand that this tail that we were seeing on the previous graph, all these tails, they're actually due to the drift over time of the sample, because we don't have a time invariant system. And each point individually taken is good, but it's just like, you know, taking a picture. If you take a picture of something which is moving fast at night with your phone, you're probably gonna see a very blurry picture. And this is my blurry picture that I'm taking with my phone. But the good thing is that we have an algorithm, so it's not we have not completely invented it. Okay, it's based on the work on a previous work. So we often refer to it as a 4D Stoyanov impedance correction. And from all these graphs, we can reconstruct a graph at a particular time. And from all these graphs, I can reconstruct the red one here to get a perfect answer. So I would get the red graph here. Okay. And this is the right answer from my system. And this is something I cannot run an analysis on all these graphs because they are not right. If you try to fit anything on these graphs, it's going to be wrong. But if you fit this red graph, then this is data you can actually use. And this is very interesting because you can measure more and more phenomena. So if we look at similarly, if I go back to my battery example from before, if we look at battery measurements in 3D, then we are looking at something like this. So it's a little bit less visual. This is why I just wanted to show you the corrosion data, but the result would be exactly the same. You look at this graph in 3 dimensions, and then you use the Stoyanov correction to get a snap in time of your battery, and then you can get very, very interesting data on phenomena that are happening in the battery. So just know that these are measurements that are possible. So my conclusion very quickly here, we were able to run low frequency measurement during charge and discharge. But these low frequency measurements, they are affected by non-stationarity errors. And to overcome these errors, we need to look at different things. We need to look at the quality indicators, very important. We have seen also that to bring these quality indicators down to values that are acceptable, we had to look at the AC and DC ratio. And finally, even when the quality indicators were good, the measurements had to be corrected with the Stoyanov 4D correction. If you have the Biologic software on one of the latest version of the Biologic software on your computer, you will see this is available directly in the analysis of the software. So this, I think, finishes my presentation. I hope you will. This will extend the range of your research and open your mind to new types of measurements. I really believe that this can lead to very interesting discoveries, because again, you're no longer studying your battery in a regime which is not the actual regime the battery is used. Because if you're studying a battery when it's not charging and discharging, this is not really how the battery is used usually. So this should open your research to new opportunities, and I hope you would make good use of it. Thank you very much. I don't know if you have any questions. I can take some time for a few questions, of course.
Thank you, Thomas. Now the session will open for the question.
Thanks for your nice presentation. One thing I would like to ask you, do you have any fitting kind of software which you are using for Biologic? Maybe I missed some of your talk.
Yes, there is a fitting software in the system. In the presentation, I've not focused on the fitting software because, as I always like to say, before starting to fit, we need to make sure the data is right. If I go back there and I try to use the fitting software on this data, this is not data that, I mean, it will fit, it will give you an answer. You can get even a very good fit on this data, but since the data is not right and you have to correct it first, then the whatever results you will get from your fit would be wrong. So the first step before going to the fit is to get the data right, and this is why we use typically, if I want to fit this data, the first step for me would be to correct it with the Stoyanov correction here, and then I would fit this red curve with the fitting tool directly from the Biologic software. There is, of course, a software which is very to use, and most of the measurements, if you do a standard measurement on a system, like if you're not charging your battery when you are running the impedance measurement, you can go straight away to the fitting. Yeah, so yeah, there is a fitting tool and it's pretty easy to use. And by the way, if you're wondering, one of the questions we have very often is which elements should I use to fit my battery? This is actually a pretty long question to answer. But actually, if you go on our website, we have two very interesting application notes. One is talking about high frequency fitting on batteries, and the other one is talking about the low frequency parts of the battery. And you can see we take you through the whole thinking of the whole process of how to choose the right elements to fit your battery. Because we should not take like just the elements that give you a good fit. Getting a good fit is one thing, but these elements need to have need to make sense, physically speaking, and taking the right ones is pretty important. But this is another. I could speak for I think 3 or 4 hours just on that topic. But if you have a little bit of time, I would invite you to look on the website at these application notes on high and low frequency fitting on batteries, and you will see this is pretty interesting. Yeah.
Thank you.
Thank you. There is another question. What is the physical meaning and the reason behind these negative values of Z axis? And why should we measure the EAS for the device like supercapacitors at the 0 volt DC potential? And this question from Abur Rai.
Okay, so I'm not sure I've properly understood the question, but I think the person is referring to impedance going.
Real and imaginary part. No, he's asking why real part and imaginary part as negative indicators. Real part and imaginary part.
Okay, so the imaginary part could be negative depending on what you're studying. If you're studying a cylindrical cell, you will have some inductance that you're going to be measuring. First, because of your connections, everyone uses a cable to connect to a cell, so this has an inductance. And an inductance, I'm sorry I don't have a nice graph showing you an inductance, but an inductance typically gives you a nice tail that goes into the negative part of the imaginary axis. So I would not be too afraid to have a negative part on my imaginary axis. Similarly here, we can have, it can go to slightly negative. It's not a big problem. The problem you can have is that if you go to the negative part of the real axis, like 99% of the case, if you go to this part of the graph on the negative part of the real axis, it means that you have a problem. Typically, a supercap or a battery cannot have a negative internal resistance. What you are measuring here typically is the internal resistance of your battery or your supercap. And if you go to the negative parts, it means that you have a negative resistance. So basically, you are creating out of nowhere some energy, and this means that you have a problem. So if you have a negative answer on the real axis, most likely it means that you have a problem with the measurement. So the thing I would do is that I would look at the quality indicators the same way we have done there. I would look at the TSG, I would look at the NSD to make sure there is no problem with the measurement. Again, the most important thing is really to make sure your measurement is right before you go to the analysis. You can have a measurement that is very nice to look at, but at the same time, this measurement would be wrong. And you know, it can be a very smooth measurement, but a very wrong measurement at the same time. The first thing you should focus on is to have a true measurement, and having something nice is not something that would be very interesting for you as a scientist. And by the way, if I look at the graph here on this slide, you see that we are going into the negative part of the imaginary axis so it's minus the imaginary axis. So just take that in account, but this is the way we are representing usually in Nyquist. So I'm going in the negative parts, and this is just due to the inductance of the battery, because it's a cylindrical battery. It's wrapped around itself, and it generates quite a lot of inductance, more due to the shape of the system. Normal. Again, negative part of the real axis, you should probably question your results.
Okay, thank you. There is another question from Jatbox. Which frequency is best for supercapacitor?
Which what?
Which frequency?
No, they're asking the frequency range.
Okay.
So which will be the better for just a student?
Mail, sir, please read all questions, sir. So subject expert.
No. It is asking the frequency range. How do you determine the frequency range for a supercapacitor? Which is a longer frequency range or a smaller one is better or something? The student is asking.
Okay. It depends it depends on the chemistry of the supercapacitor and the shape of the supercapacitor. Usually the bigger is going to be your system. It's true for supercap or a battery. The lower you're not going to go as high in terms of frequency if the system is bigger. For smaller systems, you may have to go a little bit higher. It really depends on what you have inside the battery. But in order to determine for your samples, what is important to look at, you should run a first measurement. Usually for supercaps and batteries, like going above 10, 20 kilohertz is a bit rarer, I would say. If I look at these battery measurements, here, the last point you see is probably around 10 kilohertz. So I cannot check here because it's not. It's just a picture from the software. It's not the actual data, but I would expect it to be around 10 kilohertz down there. And you can see that from this measurement, I can already see all the things that are important for me. If you go to like let's say one megahertz on your supercap, and you see that you have a point that crosses the real axis here around 5 kilohertz, and then after that it goes like a very long tail to the bottom of your graph. There is no interesting data for you to look at there, and there is no need to go there. It's the same for the lowest part of the graph. If you look at the lowest frequencies, in this case, we are seeing a lot of interesting things. So I am actually interested going to low frequencies. This is an example at 10 millihertz. So we are going down to 10 millihertz. But if you see that at 10 millihertz, you're not getting more information than you already have, there's no need to go down to 10 millihertz. So visually on my graph, I can very quickly see which range I have to use. So if you really don't know, you can scan first over a long range of frequencies, typically starting from 1 megahertz and going down to 10 millihertz. And from what you see visually, you would say, okay, I don't need to go to 1 megahertz, and then I can probably work from 10 kilohertz down to 10 millihertz or 100 millihertz. Really depends on the sample. If I look at this sample here, I get all my information between 5 kilohertz and 10 millihertz. This is good for me. I don't need to go any further.
Thank you, Dr. Thomas Gullian, for a nice presentation. And Prakash, you want to say, you can continue, no?
Okay. I think we can. There is no more questions. We can stop this session, and tomorrow we will continue with the new sessions.
Yeah, thanks for all the participants. And tomorrow we'll again the session starts at 9:30 a.m. So please kindly join before 10 minutes, 15 minutes before the session. So attendance is mandatory for 3 days actually. For the certificates, attendance is mandatory.
Thank you, Thomas, and thank you, Mailka.
Thank you, Dr. Thomas, once again.
Thank you for the invitation. Thank you very much. It was a pleasure.
Dr. TM, is the session over for today? Sir, you're muted. I can't hear you properly.
Yeah, the session is over today actually.
Yeah, I will give 5 minutes so that all people can see the messages you have just dropped in the chat box, and I will end the session because another webinar is starting soon.
Okay.
Okay.
Okay, just give me 2 minutes.
அது க்ளோஸ் பண்ணாதீங்க ஒரு 5 minutes வெயிட் பண்ண சொல்லுங்க.
All the participants, the Google form link has been submitted for the whole day. So this is only one feedback link for a whole day. So kindly fill it up and submit it.